moderators, presenters, educators, and all participants. Welcome to ICPIAM 2025.
To begin our ceremony, we invite all distinguished guests and participants to please stand as we listen to the national anthem of Indonesia, Indonesia Raya, followed by the hymn of Ireland. Thank you. Ladies and gentlemen, please be seated.
Ladies and gentlemen, we will now proceed to the committee report. We would like to invite Dr. Siswanto, Master of Science, as the chairman of ICPIAM 2025 committee to deliver his report. To Dr. Siswanto, the floor is yours.
Thank you. MC. Good morning, ladies and gentlemen. Distinguished guest Prof. Muhammad Zaki, Pakli, Master Science PhD, Vice Dean for Academics, Student Affairs and Alumni, who represented the Dean of Faculty of Science and Technology, University of Langgar. Distinguished keynote speakers, respected participants, and colleagues. It is my great pleasure and privilege to welcome all of you to the International Conference on Physics of Instrumentation and Advanced Material, ICPIAM 2025. On behalf of the organizing committee, I would like to express our sincere gratitude for your patience for in-person and online at this important scientific gathering. We begin by giving thanks to Almighty God for it is through His blessing that we are able to convene today to share ideas, research finding, and innovation in the exciting field of instrumentation physics and advanced material. Ladies and gentlemen, this year conference carries the theme Smart Material and Instrumentation Technology for Sustainable Growth. This theme reflects our shared commitment to addressing global challenges through science and innovation. The development of smart material, advanced instrumentation technology plays a vital role in achieving sustainable progress, enabling efficient, eco-friendly, and intelligent solutions across industries and societies. Ladies and gentlemen, ICPIAM 2025 is held in collaboration with the University of Jember and the Sumatra of Institute ITERA. And it is expected that next year UPN Veteran Surabaya and General Sudirman University Purwokerto will join as well. ICPIAM 2025 is led by 60 participants with about 33 papers from 8 universities. We are truly honored to host for distinguished keynote speaker, Prof. Gunther Anderson from College of Science and Engineering, University of Australia, Prof. Sutomo Terada from Department of Electrical and Electronic Engineering, Graduate School of Engineering, Kobe University, Japan, Prof. Pat Giller from Faculty of Engineering, University of Nottingham, UK, and Associate Prof. C. Asura from Institute of Nanoscience and Nanotechnology, University Putra, Malaysia. We believe that their contribution will increase this conference and inspire fruitful discussion and collaboration among participants. On this occasion, I will also like to express my deepest appreciation to all members of the organizing committee, the lecturers, staff, and students who have worked tirelessly to prepare every detail of this event. Your commitment, creativity, and teamwork have made it possible for us to gather here today. And of course, to all participants, thank you for joining this conference. Your active participation through presentation, discussion, and idea exchange makes this conference truly meaningful. Here, this conference will serve as a platform not only to deserve research funding, but also to find collaboration, friendship and network that will continue long after the conference. Once again, thank you to everyone who has made this event possible. Maybe all enjoy a successful and memorable conference. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Siswanto, for the comprehensive report.
Next, we will have the welcome speech. It is our distinct honor to invite Professor Muhammad Zaki Fahmi, Master of Science PhD, the Vice Dean I of the Faculty of Science and Technology Universitas Airlangga, to deliver his remarks and officially open our conference. To Professor Muhammad Zaki Fahmi, please welcome.
Okay, thank you, distinguished keynote speaker, distinguished professor, all esteemed guests and researcher, dear participants, and ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh and good morning. This is our big pleasure and honor to be here and welcome all of you to join this conference, international conference of physical instrumentation and advanced material. In an era of high technology and innovation, we believe that the theme and discussion on this conference will inspire many people to have a high innovation and collaboration, and also we are very delighted to be part of this conference, and this is proof of our university and our faculty is committed on advanced research and also global collaboration. We hope that all participants have getting insight in academic and also networking and meaningful partnership. And we also like to express our gratitude to all keynote speaker or committee participant and sponsor who that support this conference and very well. And then finally, I hope all participants is engaging and also productive and inspiring conference. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Muhammad Zaki Fahmi, for the warm welcome and officially opening the ICPIAM 2025.
Distinguished guests, to bless our event today, let us pause for a moment of reflection and prayer. We would like to invite Professor Dr. Kusnul Ain, Bachelor of Engineering, Master of Science, to lead the prayer. To Professor Kusnul Ain, please lead the prayer.
Assalamualaikum warahmatullahi wabarakatuh. Honorable to Professor Muhammad Zaki Fahmi as Vice Dean of Faculty of Science and Technology, and Honorable to Dr. Siswanto as Chair in 6th Conference ICPIAM, and all participants both join in online or offline. Let's do pride so that this conference can be done well. I will lead a Muslim to pride, and not Muslim can do according to the religion. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin, hamdan yuafi ni'ama wa yukafi mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhika wa 'azimi sultanik. Sallallahu alaihi wasallam Muhammadin walhamdulillahirabbil alamin. We thank you, O Allah, for gathering us here today in this blessed assembly, the 6th International Conference on Physical Instrumentation and Advanced Materials. We are grateful for the health, knowledge, and opportunities you have passed out upon us, allowing scientists, researchers, and scholars from various parts of the world to unite in the pursuit of wisdom and innovation. O Allah, the source of knowledge and light, grant us clarity of mind, sincerity of purpose, and humility in our hearts as we share and discuss our works. Bless every presentation, every dialogue, and every idea exchange in this conference so that they may contribute to the advances of science and technology and ultimately to the benefit of humanity. O Allah, make this gathering a means of strengthening collaboration, deepening understanding, and inspiring future discoveries. Protect us from arrogance and ignorance, and guide us always toward truths and written knowledge. May our effort today be counted as act or worship, done with integrity, compassion, and a sincere desire to serve your creation. O Allah, bless our leader, our institution, and all who have worked tirelessly to make this conference possible. Grant them continued wisdom, patience, and reward them abundantly for their dedication. And when this conference comes to end, O Allah, let us pass this heart enriched, mind enlightened, and spirit renewed. Unite us again in future gathering filled with peace, respect, and shared purpose. Rabbana hab lana min azwajina wa dhurriyyatina qurrata a'yun waj'alna lil muttaqina imama. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Subhana rabbika rabbil izzati amma yasifun. Wassalamun alal mursalin walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Amin. Thank you, Professor Kusnul Ain.
Before the first session begins, there will be a documentation session starting with the offline audience, followed by the online participants. For the offline audience, please welcome to the front. Yeah.
For the participants joining us online, you may turn on the camera for documentation session.
Ladies and gentlemen, we have now concluded the opening ceremony. We will now begin our first main agenda, plenary session 1. This session will be guided by our moderator. It is our pleasure to introduce Mr. Heri Trilaksana, Bachelor of Science, Master of Science, PhD.
Mr. Heri Trilaksana will introduce our first keynote speaker, Professor Gunther Anderson from Flinders University. To our moderator, Mr. Heri Trilaksana, the session is yours.
Thank you very much, MC and my students. Morning to all of the colleagues, morning of all of the collaborators. Also, our fantastic keynote speaker, the first one, Professor Gunther Anderson from College of Science and Engineering, Flinders University, South Australia. I'd like to mention a very brief view about him. And he's actually the great scientist focusing on the electron spectroscopy and ion scattering to understand surface and interface, and to use of the techniques to understanding the development application of the materials. So this is kind of the engineering for the surface science, but it's actually very, very beneficial for the materials advance. And then his educational background, he's graduated from the Dartmouth University for the degree of physics in 1994, then continuing with the master program in the Institute of Higher Frequency Technology in Dartmouth University, together with Professor Forges, and collaboration with the KPH in 1994, and then the PhD in Renata University of Witten-Herdecke, the Institute of Physics with Professor Mogner in 1998, and then continuing for postdoc, I think, in the UK. The honors award and grants, actually, I just mentioning for the last 5 years, Professor Gunther Anderson is actually very popular and very, very productive research with our Australian Research Council in 2023, 2025, and then spark hydrogen concentrated for solar thermal photocatalytic water splitting in 2021 to 2024. And then before that, it's chemical signature analysis surface from the ARC again, in 2019, 2020, and the ARC also with the unrevealing determinant drivers of ion specificity in 2019, 2021. So that's all of the productivity and also a couple of the publication from Gunther Anderson. And today we will have the topics and sharing from him. And also for all of the collaborators, for all of the participants, for all the students, master and PhD degrees who are very interested to this topics, you are very, 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 very welcome to join, so very, very welcome to ask some questions, so very welcome to share, and also to express all of the intentions how to collaborate with Professor Gunther Anderson in Flinders University, South Australia. And I think I think he's actually for the deputy director for Flinders University for nanoscale science and technology. They will be very happy to collaborate, and everything is very welcome. For the screen and times, time is your Professor Gunther. Can you hear me very well?
Thank you, Harry, for the very kind introduction.
Yeah, but I'm so sorry, it's not very, very clear. Can you bring up the volume a bit?
Let me
Gunther?
see.
Yeah.
Is that any better now?
Yes, that's better now.
It's better now. Okay, so just
Okay.
in case it becomes worse while I'm talking, just let me know and I will try
Sure.
to find a way of improving
Yeah.
it. Okay, so start sharing screen now.
Yes, please.
Okay, I assume you can see my screen now?
Yes, I can see it very clear.
Good. Okay, again, Harry, thanks for your very kind introduction. And yes, so the topic for my presentation is surface and interface science using spectroscopy and ion scattering techniques for materials and environmental applications. So as Harry has already pointed out, I'm from Flinders University. We have at Flinders University the Flinders Institute for Nanoscale Science and Technology. And that's where I'm located. So let's see. No, it's working. Yeah. So first, I want to give you a brief overview over the presentation. I want first to introduce our Flinders Institute for Nanoscale Science and Technology a little bit. And then I have selected two subjects about which I want to talk. The first one is metal clusters on surfaces for photocatalytic water splitting. And because it's related to spectroscopy and techniques, I have listed here the techniques which I will be introducing for the subject. So one is just how to make materials. This is metal cluster generation. And then analytical techniques, electron spectroscopy. And here we'll cover X-ray photoelectron spectroscopy and a not very well-known technique, so metastable induced electron spectroscopy. Harry is very familiar with that. Harry has used all of that in my lab, so he knows very well how these techniques work. Then I will also use and briefly introduce electron microscopy, and then another surface analytical technique, which is called ion scattering spectroscopy. So this is the first subject. The second subject is called specific ion effects at liquid surfaces. And here will be the focus on one single technique that has this very long name, and we just called it NICS. And again, Harry is very familiar with that. So can you still hear me well from my microphone?
Could you please crank up a bit more, Gunther?
Let's see.
Because about our problem for the microphone, is that?
Yes, I'm sitting here with my notebook and just need to see whether I can.
Okay, this is already maximum here. If you can crank up a bit, then it's much better.
Yes, let me see whether I can adjust microphone.
Usually the sound comes to the what is the kind of different speaker, I think.
Is it working better now?
Yes, so.
Yes. Okay, it's I don't know why the microphone's.
Are you in your office or are you using your own laptop?
I use my own laptop.
Yeah, that's fine. Is that
better? Is it okay now?
Yes, that's okay now.
Good. Okay, then let's keep going. Okay.
Okay.
Good.
Yes. All right. Thank you.
In case it's getting worse, just let me know again. Just
I don't know. Maybe you're talking too close to the microphone now.
Yes, maybe. Yeah. Okay. Good. Let's keep going.
Yeah, that's good.
Good. So here's our Flinders Institute for Nanoscale Science and Technology. There is 16 members, and we have an institute director, institute manager. Sorry, that's Dr. Martin Cole. And so we have activities across physics, chemistry, and biology. And the themes we are covering in the Institute are spread over 4 different themes: environment, energy, security, and bionano. So on the left side, environment and energy, they are the dominant ones. So this is where the main activities are. So it's protecting of finding ways of doing processes environmentally better. This is very much linked to energy as well, to renewable energy. So here we work on solar cells, solar thermal energy, hydrogen production, batteries. Security is a small portion of the institute as well. And then also bio-nanotechnology. So there is, for example, model membranes or sensor technologies which are relevant. So my main activities are here in energy and to some degree in environment as well, and also a few other things. So the second subject is not quite covered here. Okay, so let's start with that first subject. Let's start with the first subject. So metal clusters on surfaces. So they have a specific purpose why we do that, and it's related to photocatalytic water splitting. So the reason why we put them on surfaces is that we want to tailor the electronic structure and the geometric structure of surfaces. And that is, and I will explain that in a minute or two, is related to our specific purpose, so in developing photocatalysts for water splitting or to improve them. The interest we have in that field here is that we want to attach these clusters onto surfaces. We want to measure their electronic structures and also the electronic structure of the substrate. And we are also interested to determine the geometric structure of the surface. One of the main challenges here is to stabilize the clusters against agglomeration. And again, I will explain that a bit, how that happens and why it's relevant. So here's a schematically shown a photocatalyst. So photocatalysts, as we use them, they are made out of semiconductor particles. So this is here. So the yellow is symbolizing a metal oxide nanoparticle, a semiconductor. The semiconductor is able to absorb light, and they have typically a diameter of about 100 nanometer. When you shine light on these semiconductors, you generate a so-called electron-hole pair. And then the electrons and holes, they have a certain energy, and they are then to be used for running specific reactions. So the reactions we're interested in is to oxidize oxygen to form O2 and to reduce hydrogen to form H+. So the electrons have to move or will move to the surface, same the holes. And the reason why the points they choose is these specific co-catalysts, which are indicated with HEC here. These are the co-catalysts for the hydrogen reduction. And here's the co-catalyst for the oxygen oxidation. So the protons, so the holes go to this place here, and the electrons move to this place here. And the energy they have gained through the absorption of light, that is then used for this reaction. So now, why do we put these clusters on surface? And I just want to briefly go back. So these clusters on surfaces, they have the function which is now indicated here with the co-catalyst. So these co-catalysts, for these ones we want to use metal clusters. And just want to briefly explain why that is actually reasonable. Why are we doing that? So here's a schematic for a semiconductor. So here's just a plain semiconductor. Semiconductor has a band gap. You have the valence band here, the conduction band here. And between them is a gap. That's a so-called band gap. When you now put a nanoparticle, a metal nanoparticle onto the surface, this metal nanoparticle, because it is metallic, is electronically structured such that the conduction band and the valence band come together. So the electronic structure of the nanoparticle as such will not help in the catalysis. It will only help with its geometry for reducing the energy barriers for the catalytic reaction you have in mind. Now, we want to use the electronic advantages of these particles as well, but for that purpose, we can't use these metal nanoparticles. we have to go to a smaller size, and that's illustrated here. So here's a schematic for a metal cluster, and if you would count, you would find here schematically 8 atoms, and you would find 9 atoms, and all this is just schematically showing what that means. So you have valence band and conduction band. Because these clusters are so small, they induce new states in that band gap. Because the clusters are small, these are discrete states. So you have close to the valence band, you have these states here, and close to the conduction band, you have these states here. As I said, this is not any method structure, this is just to illustrate it. But importantly, they're not only discrete states, because these clusters are so small, they also change in case you change the number of atoms. So if you add another atom, then you get a different structure of these energy levels here. And that now can be used as an additional function for a co-catalyst. So now we not only have the geometric structure, which is an advantage for the catalytic reaction, here we also have an advantage that they have a certain electronic structure which will help. So this is the advantage. And just again checking in, the volume is okay? You can hear me well?
Yes, that's okay.
Good, fine. So, and what we want to do, so here is now a bit more detailed for the photocatalysis. So this is the schematic of the photocatalyst as we saw it before with the electron hole separation. Here's now on an energy scale shown the conduction band and the valence band. And here are the energy levels for the specific reactions we're interested in. So here's hydrogen reduction. This is on the normal hydrogen electron energy scale is at 0 electron volt, and the oxygen oxidation is at plus 1.23 volt or electron volt. Now the semiconductor which you want to use must be structured such that the valence band is below this level here. So the level for the hole must be below that level where you have the oxidation happening, because the hole is running the oxidation of the water molecule. The conduction band must be above that level here, because that electron which you put in the conduction band has to drive the hydrogen reduction. So the clusters we put on the surface, they can induce then additional states here and then help to make these reactions more efficient. So the current state of the technology, which are the best catalysts and almost commercially available, they have a so-called solar to hydrogen efficiency of 1%. Solar to hydrogen efficiency is the probability that you turn a photon into a hydrogen molecule, and that includes all photons which you absorb. So if you use solar radiation, that goes from the UV light to the infrared. Unfortunately, these photocatalysts are only active in the UV light range. That's the reason why the efficiency is so small, but there have been demonstrations plants of 100 square meter in Japan, and they have been operating for 9 months and continuously produced hydrogen. So the technology as such is working. And I want to show you a video which is taken in the lab of my collaborator from Adelaide University, from Professor Craig Mather. What's done here, so the white part here is a photocatalyst. Here's now UV light shining onto the photocatalyst. There's water on top of the catalyst. And you can see that from the purple irradiation here. So the purple indicates we have no UV light coming in here. Now you see with increasing light intensity, there's more and more gas bubbling off the surface, and that gas is the combination of hydrogen and oxygen. So the technology is working. The question is now, how can we make it more efficient? How can we now go into the solar, in the visible part of the solar spectrum, and use also this energy for running this reaction? So when it comes to semiconductor, which have a smaller band gap, then the exact structure becomes more and more relevant. So when you use UV light, then the band gap is around 3 electron volt, and this is much more than the required energy of 1.23 electron volt. So you put in much more energy and you have an almost certain occurrence of that reaction. When we now go to a smaller band gap, being able to absorb more light, so up into the visible part of the spectrum, then the exact position of valence band and conduction band becomes more important. There's other effects which come even more important as well. So this is here now a schematic showing an effect which is called band bending, and those who have studied solar state physics are probably very much aware of what band bending is. So here you have a semiconductor with its conduction band and valence band, and if you put a metal particle onto the surface, then you will just have a continuation of that Fermi level of the metal nanoparticle into the middle between conduction band and valence band. So that will align just very well. Now, most of the semiconductors are not just intrinsic semiconductors, they are the N-type or P-type dop. When you put now metal particle onto that surface here, then depending whether it's an N-type or P-type, this band here, so the Fermi level here will adjust to meet the Fermi level of your particle here, as it's schematically shown here. And what you then get is a bending of the conduction band and valence band. If you have now the opposite of a P-type one, then it's dragging down and you have the opposite band bending. So the reason why I show that here is now that I want to illustrate that these interfaces, they can be quite complicated. And for optimizing a photocatalyst, we actually need to understand how these structures are in a given arrangement of a photocatalyst such that it can be modified to be better suitable for the actual purpose. So I won't show how to measure band bending, but one of the technologies or one of the techniques which I will be introducing, electron spectroscopy, is the technique for which you can actually use, to measure this band bending. So we are in the process for our photocatalyst to measure the band bending, but because the results are not yet finalized, I'm not able to show them here. So let's go back to these clusters. So there are two different types of clusters. There's so-called ligand-protected clusters, and there's another type of clusters which are called gas phase generated clusters. Ligand-protected clusters are made chemically. You can put them on surfaces by immersion into solution of the clusters, or you can use pulse nozzle deposition or evaporation in some cases. This is a chemical process, which is, because it's chemically done, always has the problem to have some inherent, can say dirtiness in it, because you also get solvent onto the surface and other things which are potentially in your solution. So the advantage is for this process, you can do it on large scale. You can coat porous surfaces, nanoparticles, large surfaces you can coat with these ligand-protected clusters. The downside is it's not as clean as you might want to have it. These gas phase generated clusters, this is a physical method. This is very clean. However, you can only deposit line of sight, so you can only deposit on a solid, on a flat surface. You can't deposit them on nanoparticles, and you can't put them into porous structures. So the method which we're going to use for this purpose is electron spectroscopy, and that's what I will show you results. So this is what we're going to do. We will want to measure the electronic structures of these co-catalysts. So these clusters, they are the co-catalyst, and we want to measure their electronic structure when they are sitting on a surface. So the challenge now, however, is with these clusters, if they go onto the surface, they're thermodynamically not stable. So this is the situation you actually want. You want to have a semiconductor, you want to have these clusters, these metal clusters with a few atoms on the surface. And if you could arrange that, then you would be fine. Then you would have achieved what you want to achieve. However, these clusters could be mobile. They could move around. They could aggregate and then form a nanoparticle. And then the purpose, what you wanted to achieve, what I have further earlier illustrated here, that you want to introduce additional states close to the conduction band or valence band, that will be lost, and you will be back to the nanoparticle. And the advantage of the modification of the electronic structure of conduction when valence band is gone. So we need to find a way of avoiding that. So I skipped this slide here. Yes, I've mentioned already. So this technique here is for large scale, so ligand protected clusters, but it's not as clean as you always want to have it. This is for clean samples, but it's only line of sight. So here's some examples for ligand protected clusters. Here's example for gold 8, 9, and 11. And if you count, you find here schematically 8 gold atoms, here 9 and here 11. They are surrounded by these ligands, and these ligands protect them from agglomerating. So once you make them, they are stable. However, when you put them on the surface, you need to remove the ligands, and then you're back to the problem that these clusters want to agglomerate, and we need to protect them against doing that. So here's a schematic how you make clusters in a gas phase. The method is you evaporate material, and that material can agglomerate in the gas phase here that can grow to larger particles. And then with a quadrupole mass filter, you can select the specific size you're interested in, just deposit these ones here. And as you can see here, because it's vacuum-based technique, this is a very clean way of generating the surface clusters. I want to briefly introduce photoelectron spectroscopy, which we use for analyzing these clusters on surfaces. Some of you might be familiar with the technique, some not. So there's two different ways of running this technique. Sorry. One so-called X-ray photoelectron spectroscopy, use excitation energies of about 1000 electron volt. The other one is UV photoelectron spectroscopy, use excitation energies around 20 to 50 electron volt. So if that's your sample here, you have certain energy levels. So here's your valence electron structure here. Here's the vacuum level. Here's the Fermi level. Here are the core energy levels. And what you do in photoelectron spectroscopy is you bring a photon to the surface and you basically lift these energy levels. In the schematic here, they're now lifted up to here. And all the energy levels which get above the vacuum level, they can potentially escape the surface as long as the atoms are reasonably close to the surface. So that's what photoelectron spectroscopy does. And here's now a way how we have measured these clusters on the surface. So here's gold 8, gold 9, gold 11, gold 101 clusters. Here's the binding energy. And there's an effect which I want to briefly illustrate how we can identify from the spectra which size of clusters we have. The typical bulk binding energy for gold is here, and gold 101 is large enough. It's almost a nanoparticle that behaves like bulk gold. However, if the clusters get smaller, we can see here a shift to higher binding energy, and it is a so-called final state effect. So the emitted electrons, they are aware of how large the cluster is, and they shift slightly their binding energy. It is not the so-called chemical state effect, so they're not changing chemically. There's only the final state effect. And here's a plot for this binding energy. So here's large particles, but if they get smaller, the binding energy increases. And this is now important because this allows us to determine what size of the clusters we actually have, or are they small enough such that we can still have clusters on surfaces. Here's after, so this is as deposited, here's after calcination. You can see an even larger shift here. There's now a bit of a substrate effect as well, but this portion of the clusters is kept small. These ones are kept large. So some of them have agglomerated actually and some not. Good. So we can identify pristine clusters after deposition. However, we still don't know the exact electronic structure. For that, we need a different technique, which I will explain very soon. Here's now a way to visualize the clusters and surfaces. Many years back, we had a chance to use these so-called titanium nanosheets. Here's an electron microscopy image of them. When you put, and these nanosheets have a thickness of just one monolayer of titanium dioxide. They're very thin, so it's 1.2 nanometer. Now we can put clusters on the surface of these nanosheets, and you can see them here. And if you count here correctly, you find 8 bright spots. This spot is very bright, so this counts for 2, and you would actually find 9 bright spots then. This is illustrating a gold 9 cluster on the surface. Because it corresponds to the structure of the protected cluster, we think This was a cluster which was protected with ligands. This one here is distorted, so it's interacting with the substrate. It has a different structure, and there's now a cluster substrate effect, the same here. So these clusters are interacting with the substrate after the ligands are removed, but they stay small enough. If we zoom out, we see that electron microscopy is unfortunately also destroying clusters. So this is zoomed out image. You see large bright spots here. This is where clusters have agglomerated. Here's other small spots here. These are destroyed clusters. So electron microscopy is actually quite energetic technique, and it's basically destroying also clusters. To be very careful how to analyze them. Good. So now comes a different technique here, because I promised to say we want to investigate the valence electron structure of this cluster, so-called metastable-induced electron spectroscopy technique. What we do here, we don't bring a photon to the surface, we bring a metastable helium atom to the surface. This metastable helium atom brings an excitation energy of about 20 electron volt, and it can excite the electrons in the sample. So you get emission of electron, same as in photoelectron spectroscopy. The only difference is that this metastable helium atom has to transfer its energy to the first electron density which comes across. So it's absolute surface sensitive, basically the electron density which is forming the outer layer. That's the only electron density you see. So if a disordered molecule on the surface here, and schematically showing a red, a black, and a green part of the molecule, and then if we make up a spectrum of that, this is just a schematic, this is not a measured spectrum, then you get all the contributions of all the orbitals which are forming the outer layer. In contrast, would have a perfectly ordered sample, or the outer layer is perfectly ordered, you would see only that specific orbital pointing out from the surface here, and now you could measure that. So this is relevant because what we want to see is the electronic structure of these clusters on the surface. Good, here's a photo of that equipment. It looks quite complex. So we have a training program for 3 days. So new users get a training program for 3 days. So while it looks complicated, it is not too complicated. So within 3 days, people can learn how to use the equipment and use the equipment on their own. So again, here's the schematic. So if now clusters on the surface, on the titanium dioxide surface. So the red and white is a schematic for titanium dioxide surface. Here are gold clusters. Metastable helium atoms coming in can either interact with the gold clusters, get that spectrum out, or interact with the substrate, and then get electrons out from the titanium dioxide. Now here's a set of spectra of gold non-clusters on titanium dioxide with an increasing loading. So the concentration here is the concentration of the solution which we used for immersing the sample into. So we see an increase in loading, and you can see a change in the spectra of the substrate. Now the question is, can we now find the components contributing to the overall spectra? And the answer is yes, we can. So there's a process involved which is called component analysis. So we now can decompose into reference spectra, and each reference spectrum represents one part of the surface. And after all the analysis, we came to the conclusion that the red line here, that's representing the titanium substrate. The blue one here is representing the ligands, which are still after the removal to some degree on the surface, most likely. But most importantly, we have now here also a spectrum of the clusters. That's the black line here, the spectrum of the clusters on the surface, and that's the density of states. So 0 means here Fermi level. So here's where the states of the gold 9 clusters are when it's on the surface. And these are the states where the gold 5D would be found. So it makes sense to assign the spectrum actually to gold. So why is it now relevant? So I was telling you we want to induce states in the band gap. So if we have plot the binding energy here, so here's the Fermi level, here's the valence band edge for titania, and now that reference spectrum 2, which we assign to the gold clusters, this has electron density which is above the Fermi level, above the valence band, so between the valence band and the Fermi level. And so we believe these are additional states which the gold-9 clusters induce on the titanium surface. And this corresponds also to computer calculations. So here's the valence band edge according to computer calculations. The green is the calculated gold 5D of the clusters. And again, we can see here as well, there are states above the valence band edge. And in this schematic here is the Fermi level here. So between the Fermi level and the valence band edge, there are additional states now, which we then can find here in the spectrum as well. Okay, so here's now a different cluster size. Here's now gold 13. It looks similar to the gold 9. However, the contributions are slightly shifted. So it's slightly shifted to somewhat lower binding energy. So the gold 13 has a somehow different structure. Now here's a completely different cluster. There's now a ruthenium cluster. It's ruthenium 3. This has, we found the states in this region here. Here's again Fermi level. And here would be somewhere the valence band edge of the titania. Now, this is a quite clear structure here. However, this is now what a nanoparticle would do, because we don't get discrete states. We get states up to the Fermi level. And this is because these ruthenium 3 clusters have agglomerated. They have formed ruthenium nanoparticles. And this is not what we want to see. In electron microscopy, we then found also these nanoparticles. This is scale for 10 nanometer. So these green dots here, they are the ruthenium particles, and they are definitely not ruthenium 3 clusters. They are larger than ruthenium 3 clusters. So in this case, it did not work to keep them small. We got ruthenium nanoparticles. Now here's now a different cluster. That's a platinum 3 cluster. In this case, we found, so here's now two different electron spectroscopy techniques. It's the MEES technique, which I have introduced. Here's the respective UV photoelectron spectroscopy technique. On these energy scales here, we always have the Fermi level here and the Fermi level here. And here's gone towards the valence band edge. In both cases, both spectra actually show us states in that valence band region here. So both the MEES spectra show that, as well as the UPS spectra, but these are now discrete states. So platinum 3 in both UPS and MEES shows discrete states, and that's what we actually want to achieve. So in contrast, again, show the ruthenium 3 clusters, which show this very broad distribution here, which have now formed nanoparticles. So it's critical to be able to keep the cluster small, to have this modification here of the surface electronics. Good. And in the interest of time, I think I will maybe just briefly about this one here. So one way of protecting these clusters is to put a thin overlay on top, and this is your chromium oxide overlayer. This can be done chemically. You don't need to understand the procedure in the little time I give you to do that. It's just illustrating there's a chemical procedure to put the chromium oxide layer on top. And what we then get is now here with the electron spectroscopy. So here's a substrate. This was in this case barium lanthanum titanium oxide. This is up to here. The green is the chromium, so that's the chromium overlayer. And then you see very small gold clusters. So this chromium oxide layer is able to retain the small size of these clusters. And the systems, they in fact also produce, can split water as shown here. So this is not from our own work, that's from colleagues. And these systems, these gold 25 clusters, they can actually be used to generate hydrogen and oxygen. So I want to conclude this first chapter here, saying we have investigated this valence electron structure of various clusters, gold 9, gold 13, ruthenium 3, and platinum 3. For the gold cluster, we are able to show you that we can remove the ligands, but we also were able to show that some of these clusters stay unagglomerated. So the gold clusters did not agglomerate. Ruthenium 3 did agglomerate, the platinum 3 not, and they are potentially useful for photocatalysis. Now I want to comment on a different subject. That's a really quite different subject. So it's introducing a new technique, but also introducing a quite new subject. So this goes from semiconductor surfaces, it goes to liquid surfaces. And we will use a very different spectroscopy technique to analyze these liquid surfaces. So here's an illustration for how liquid surfaces behave when you dissolve simple salts in them. And the simple salts are illustrated here. Here's plotted the change in surface tension over the salt concentration. And if you look in physical chemistry in the so-called Gibbs equation, you would find that when the surface tension increases, so you take a substance, you dissolve it in your substance, in your water, for example, when the surface tension increases, then the substance you dissolve in water is depleted at the surface. It doesn't go to the surface. And that's pretty much true for all ions you can think of. So the problem is only that surface tension is only a macroscopic technique. So it can't tell you where the ions really are. They are in the surface region somehow depleted. But where are they really depleted? At the outermost layer, subsurface, or further inside the bulk? Also questions are, is that happening for water only? What are other solvents doing? So it's a whole range of questions coming with that. And this is a 100-year-old question, which was became new attention by people starting computer simulation about 20 years ago. Here's now a surface simulated. So the little things here, the little entities, they are water molecules. And this is a slab of water, which is about twice as this thickness here. It's about 32 angstrom. In that water, they had then put in sodium ions and fluoride ions. And in the other case here, they put sodium and iodide ions. Here's the surface, here's the bulk of that slab. Sodium and fluorine in the computer simulations did stay away from the surface. Iodide, however, did not stay away from the surface. So iodide went to the surface despite overall being depleted. And there's here also in the computer simulation a depletion below the surface. So is there a chance to measure that? And the answer is it's difficult. It's very difficult. The surface tension already introduced. This is a macroscopic technique. It can't tell you where the ions are. Is it outer layer? Is it subsurface? Another class of technique which actually can say something about the surface, so-called nonlinear optical techniques. They have a probing depth of 4 to 6 angstrom. They are mainly sensitive for the solvent molecules. It's a bit difficult to find information about the actual ions. So a technique technically useful, but in most cases practically didn't provide the answers we were interested in. Electron spectroscopy, synchrotron-based, can do something. If in particular when you go to the high pressure version, so water has a high pressure, and electron spectroscopy you usually have to run in ultra high vacuum. It's a bit of a contradiction. However, you can now structure set up such that you can run electron spectroscopy also at higher pressure. So they have a probing depth of 20 to 80 angstrom, about the range we're interested in, but it's difficult to determine concentration depth profiles. Now it's a different class than ion scattering spectroscopy, and that's what we do in our lab. And with this one, we can measure directly concentration depth profiles. And this is the one I want to introduce now. The techniques work like this. You have a sample here. Here's the inside of the sample. Here's the surface. We bring a projectile in. We get backscattering of some of the elements in the sample. For example, backscattering from the blue species here. That's schematically just illustrating an atom. Then you lose energy in the backscattering process, or you can have backscattering here. So when the atom you hit is heavy, then you lose little energy. When the atom you hit is light, then you lose a lot of energy. In this way, you can distinguish from which atom you're actually backscattering. Now there's another effect, and that is when the projectile hits the sample surface, the projectile also can penetrate into the sample and backscatter from the deeper layer. Now, on that path from the surface here to the place where it's eventually backscattered, it loses additional energy, and it's so-called stopping power. So it's small angle scattering and electronic excitation. And this gives us an additional information. That's very crucial now for this technique. So this additional energy loss tells us from which depths the product ion is backscattered, so we can identify from which element it's backscattering and from which depth it's backscattering. So that's what we need to determine concentration depth profiles. So that's how it works. We come in with a product type, backscattering from the surface, or you get backscattering from a deeper layer. You have that additional energy loss. Then you get these concentration depth profiles. That's a schematic, not a measured one. You have this concentration here the depths. But what is well illustrated here is the depth resolution we can achieve. So we get a few angstrom resolution at the surface. So we can distinguish, is a species adsorbed at the surface or not, or is it depleted? And that's what is important here now. So here's now measurements, and I will start with one measurement here and show you the entire spectrum. So that's the entire measured spectrum. We use so-called gas phase measurements to gauge the depth scale. So here we backscatter from iodide, and we know at this time of flight we get backscattering from iodide. This way we can calibrate our depth scale. Now these measurements are then converted into what we show here as concentration depth profiles. So here's the concentration shown, here's the depth shown, here's zero surface, here's goes into the bulk, here's below the surface, here's above the surface. The measured spectrum is the red one. And then we have to deconvolute to get a bit more information. And the deconvoluted spectrum is the blue one here. So I won't go through the process we do for the deconvolution. But what we then can identify is then enhancement at the surface of that bromide or of the iodide in this case here. Is there depletion below the surface? In this case, yes, it was. So we don't take the enhancement too literal here. So in this case, we just say it's enhanced, not how much enhanced. In this case, we say it's depleted and not how much it's depleted. So this we have done now for 4 different solvents: glycerol, formamide, propylene carbonate, benzyl alcohol. Glycerol and formamide are polar solvents. They are protic solvents. They have high surface tension. Propylene carbonate, benzyl alcohol are so this is an aprotic solvent, this is a protic solvent, but they have lower surface tension. So technically can investigate aqueous surfaces, and but that requires a long time for measurement. So what I will show you now are measurements with all these salts here. I will pick some and come to the conclusions. I think I still have about 5 minutes for the presentation, if I'm correct.
Yes, this is the
Okay,
last
good.
one.
Yep, good. So start with the glycerol solutions here now. And here are now concentration depth profiles for the N-ions chloride bromide iodide. Here's the depth scale. Here's surface. And you can see bromide and chloride, so iodide and chloride are enhanced at the surface. Bromide is not as much enhanced at the surface, and they're all depleted below the surface. Bromide is actually dependent on the cation. So it depends which cation you take, lithium, sodium, or potassium. In case of lithium, it's enhanced at the surface. For potassium, it's depleted at the surface. Chloride and iodide don't do that. They're always enhanced at the surface. Cesium as a cation is, in some cases, it has some presence at the surface. In other cases, it's depleted, so it's also a counter-ion effect. And here I summarize the results. So we can come up with an order. So for bromide, we find an order, depends on the cation. So bromide with lithium is enhanced at the surface, bromide with potassium not. Iodide is always enhanced at the surface, chloride is always enhanced at the surface, and that is shown here. So chloride is always enhanced, same as iodide. Bromide in some cases enhanced, in some cases not. So let's just keep that in mind. And so bromide has a cation effect. So this is for glycerol. Now we go to formamide. Sorry, I just want to briefly say what that with the cation effect, how we can illustrate that. So if bromide is together with lithium, bromide comes to the surface. If it's together with potassium, it doesn't come to the surface. So here's formamide results now. Formamide we found for all cations, so for the anions, irrespective of which cation they come together, they show this order. Chloride enhanced at the surface, bromide, it's there, and iodide is depleted. So this is independent of the cation. There was no cation effect. Iodide, for example, is depleted with all cations. And same as potassium is also always depleted. So here we find an order which is similar, but not exactly the same as for glycerol. So chloride is at the surface, bromide is to some degree at the surface, but lithium is depleted at the surface. And there is an, so that's the net effect. That's the same here for lithium and for sodium, and also for potassium. So formamide always does it exactly this same way. We then can come up with this order here. So chloride is always the same at the surface, bromide always the same, iodide always the same at the surface, and we find this trend. So where's the trend? The trend is shown here. Yeah, so chloride is enhanced at the surface more than bromide, and again, bromide more than iodide. So this is now formamide. Now, the two other solvents, propylene carbonate and benzyl alcohol, they behave very different. Firstly, we can only dissolve a few of the salts in them. But for these solvents, we found everything is depleted at the surface. All the anions, all the cations, everything is depleted at the surface. So then we put this together with the existing concept for explaining these ion-specific effects. I just list them and don't explain them. Law of matching affinities, polarizability of the ions, cavitation energy, dispersion interaction, hydrogen bonds. And we went through all of them. And for each of them, trying to explain this effect, we found a counterexample. None of them work. It was a bit disappointing, but on the other side, it leaves room open now for coming up with a new concept. And what we think is what's happening is that the overall concept, which we eventually will have to describe, will be a combination of these individual concepts. And in some cases, the one will be dominant, and in another case, another one, and will be important to find out why, in which case, which concept is actually relevant. The one common denominator, however, is that with increasing surface tension, we actually find an effect that an anion goes to the surface. If the surface tension is low, everything is depleted. And formamide was the one case where we found a glycerol was one case where we found a counter ion effect. Formamide didn't show any such exemptions. So future questions for us are, where's lithium? So I didn't show you anything about lithium. We're currently working on that. Which role does the surface potential play? Again, so we have a student working on that. Where are larger ions and multivalent ions located? And most importantly, what's about aqueous solutions? We're trying to modify our setup such that we can actually go to aqueous solutions now. And with that, I want to acknowledge the persons involved. So we have people from Flinders University, from University of Adelaide, Tokyo University, University of Utah, and Canterbury University. These are mainly the people who were for the photocatalysis involved. And here are those who gave the money for that, for whom we are very grateful, because they allow us to run this analysis, these measurements. And with that, I want to thank you for your attention. And Harry might actually be familiar with these places. So this is how our beaches look like in Australia. And I want to thank you for your attention.
Thank you very much. You look so very, missed the beach there.
Yeah.
Yeah. I just remember the international conference we ran a couple of years back in 2014, right? That was, and that's what kind we learned from. That we need to get a consistently international conference. Either it's every year or so. And we're just struggling with the 6 ICPIAM now. I'm pretty much sure that all the colleagues here are very competent and very high intention to continuing of the 6, 8, and so forth. So what until now, that's international conference now, around 40 something or maybe 50, I believe. Is that
Say it
correct?
again. So okay,
The
yes.
IS, yeah.
Yeah.
Must be around 40 something or close to 50, I think, because in 2014 it's around 42, I think.
Yes, that's true. Yeah.
Yes. So yeah, we are still the 6 ICPIAM conference, but we are pretty much sure we will continue regularly from that point. All right, so let's initiate the question and answer sessions. For all of the participants online or offline, you can really ask some questions about very super sensitive techniques to investigate your substance or your interest in your experiments or in your case. If it's very interesting for you, you can come up to the chat box as well, or you can just raise your hand and contribute your questions. Please. Any questions? Yeah, I think 120 participants. Yeah. While we are waiting for all of the participants, I make little questions to respond the special techniques on the basis of the synchronous techniques, which is we are using the ions, we are using the photons, sometimes we are using the electrons.
Yeah.
And in your subjects, I mean, our research groups in this university, we focusing on the energy, we focusing on the health as well for the last. But
Yeah.
you are focusing on the first two, environments and the energy.
Yeah.
And the other way, in Airlangga University, or maybe most of the university in Indonesia, they get interested to the health and medics or something correspond to the medical sciences, and they are working on the like the phenomena like the membranes will be very activated or very efficient in terms of the drug delivery or drug kinematics. So in which techniques that is going to be very suitable with the research of the medical things, because yes, we are very excited to use in the energy and environment, but we are also getting very interested to the medical sciences.
Mhm.
Could you please
Yeah.
respond on this? Peter, could you please respond about this? What kind of the techniques like? I'm not quite sure because I'm working in energy and environment as
Yeah.
well for the renewable energy. But some guys and some collaborators, some research group are working on the medical science. It's like
Yeah.
in which functional group they need to get interested and what techniques that they can investigate very clear to distinguish whether this functional group is going to be more efficient rather than the other functional groups.
That's a question, not a statement, Harry.
Yeah, that's actually my statement. But
Yeah,
in terms
okay.
of the in terms of the research, would it be possible for all of the collaborators or for all of the research groups if they have to? Because sometimes they ask me about this is my samples, and I have no idea what should we do. But my opinion is just send this to the XPS or NIS or PS apparatus. And now Indonesia has already purchased one of the UPS. This is quite similar to what we had, and this is just last year. So there's kind of the option of that we can go to overseas collaborators or in Indonesia as well. But I just contacted the Indonesian research bodies, and we just bought it, and we just not very expertise on that side. So this is kind of the ambiguous whether we are going to send internally in Indonesia or send back. But this is possible for us to send it to Flinders University. Now it is that we write the result and look at a bit more detail. Is that possible?
It depends on the application always. So is the outer layer relevant or not? In a number of cases, it's not that relevant what the outermost layer does. It's just when you have reactions which are very surface sensitive, yes, then the outer layer is very important. And if not, then it's just not relevant for a specific case, and then you just don't apply it. It's fine too.
Yeah. So that basically that's just a bit very brief information for them.
Yeah.
Whether because sometimes they just very excited. You get that published article with very rare explanation that you can discover about this about the concentration depth profile, which is not everybody gets.
So the technique which maybe would have a bit more relevance for other samples is the depth profiling, because there you can look deeper into the sample and you get from across a range of depths, you get the information. So electron spectroscopy, while it's better known, and that's often applied. So people want to do surface analysis. The first thing they have in mind is doing X-ray photoelectron spectroscopy, but it often doesn't give you the information which you really are interested in. So the depth profiling technique is in that regard often more relevant. And there we, for example, also have investigated biological membranes. So where we then investigate what's the outer part of the membrane, what's deeper inside. Biological samples are certainly a bit more challenging because they usually come with a degree of water. Then it's, that is harder to investigate in a vacuum environment. So you need to take precautions to allow to handle that.
Yeah. All right. Is there any questions from the chat box? No? So I think we still have another 1 minute small. Wait, answer the ones. Or maybe in this room, there's some collaborators or some colleagues will ask. There's no silly question you can ask in Bahasa Indonesia if you want, and I will translate to Professor Gunter.
Yeah.
Yep.
So maybe it's worthwhile mentioning, so we currently have a visitor from your place.
Yeah, it's Anga is still there, right? How is everything going there with Anga?
Yeah, so he's here at Flinders and he's undertaking research as a postdoc.
Yeah.
It's quite nice. I mean, he does theoretical calculations, so he's not as much involved with me.
Yeah.
Maybe that
With
gives you...
Takla, right? He's working with Takla, right?
Yes, he's working with Tangnao. And
Yeah.
but it gives maybe people at your place a bit of an idea what's possible. So it's possible to reach out to other places and to go overseas in case you're interested.
And the third stage is going to be ready for next, I think, January then. So maybe all others will be ready, and Gunter will be so happy to welcoming all of us to apply at least the first stage in 2026.
There's several calls for these applications and proposals per year. So I think it's more than one per year.
Yes, I think it's twice per year. The first one, it failed, but we just wanted to make sure.
Persistent and applied again and was successful.
Yeah. That's a good example. So that's going to be a role model of all of the applicants from our university, because it's not quite mandatory, but it's you will be better if you can do it, right?
Yeah, exactly.
All right, thank you very much, Gunter, for your sharing, and we will be very happy to hear any collaboration from Erlangga University with Flinders University in Australia, and also could you please say convey my regards to Professor Greg Mita and who's the guys from the UNESCO, but UNESCO is unite with the Adelaide University right now.
Greg Mather, you mean?
Yes, Greg Mather, another one from the UNESCO. Who's the one? Thomas Nan, right? Yes, Thomas Nan.
Thomas Nan, yes.
All right, thank you very much.
Thanks for the kind invitation, and it was my pleasure. Good. Good, thank you.
You're welcome, my pleasure. Thank you very much for all of the colleagues. This is the first session. This is with the first keynote speaker from Good to Understand from Flinders University, South Australia. Now we come back to the MC to start with the second session for the keynote. Thank you very much. With my pleasure, and Dr. Fernand.
Thank you very much, Mr. Heri Trilaksana and Professor Kamran Anderson, for a very insightful first session. We will now continue directly to plenary session 2. This session will be led by our moderator, Ms. Intan Firdausi Wardani, Bachelor of Engineering, Master of Science.
Ms. Intan Firdausi will introduce our second keynote speaker, Professor Sutomo Terada from Kobe University. Ms. Intan Firdausi, please welcome.
Okay. Good morning, everyone. Before we start our second keynote speaker today, I would like to greet Professor Terada. Have you joined us already, Professor? Good morning, Professor. How are you?
Good. Oh, okay. Say good morning. Yeah.
Okay. So before we start, I would like to introduce Professor Sutomo Terada. He graduated from the bachelor, master, and doctoral degree in engineering from Osaka University in 1997, 1999, and also 2003, respectively. He has been deeply involved in research on wearable computing, ubiquitous computing, and also entertainment computing, applying these technologies not only for human sensing, but also creative performance contexts, including the stage and entertainment. And Professor Terada is also an executive board member of the Wearable Computer Research and Development NPO and an honorable visiting researcher at Lancaster University. He is now a member of ACM and ICPIAM. And today, Professor Terada will share with us his insight on wearable sensing for a deeper understanding of humans. Please join me in welcoming Professor Terada. Okay, the floor is yours.
Okay. Yeah. So, can I start the presentation?
Yeah, sure.
Okay. Okay. So I think you can see the slide. Okay. So hello. Yeah, I'm Tsutomu Terada, a professor of Kobe University in Japan. So I'm very happy to serve as an invited speaker in this event. So today's presentation title is Wearable Sensing for a Deeper Understanding of Humans. Okay. Okay, so yeah, there are already many commercially available wearable devices in the world. So yeah, I would like to begin by introducing a few of them. So what is the Apple Watch? It's like this. Okay, like this. So I believe many of you are already familiar with this device. And in addition to it, many other smartwatches have also been released. So nowadays, smartwatches have a variety of functions, so making them seem as if smartphones are attached to your wrist. And so this device is a wearable device released by Epson company, so that can continuously measure blood pressure. So this one is a wearable, and also this one is a wearable camera that can continuously record the user's field of view as a video. And also, this device is a bit interesting, equipped with a contact microphone, and it can detect early symptoms of COVID-19. So, specifically unusual coughing sounds, strange coughing sound, at them indicates the possibility of infection. Okay, and also, yeah, this device is an interesting one. So it is a helmet type device used by motorbike users, and has functions such as navigation. So what makes it particularly interesting is its feature that notifies the police of the user's location when an impact is detected by the helmet. So in other words, if a traffic accident occurs and a strong impact is applied to the helmet, the device can automatically inform the police of the accident location immediately. So such kind of convenient devices exist in the world now, currently. And also, there are so many wearable sensors in the world. By wearing these sensors, various human situations and behaviors can be measured, and these kind of sensors realize various services. Okay, so actually, yes, you can you can know the Apple Watch, and Apple Watch has found many irregular heartbeats called arrhythmia. So that has a very high heart rate when they have an attack. So, but when they go to the usually when they go to the doctor by feeling the arrhythmia, but they are not in an attack state in the hospital. So it's very difficult to diagnose arrhythmia. So, but Apple Watch automatically records arrhythmia while you are sleeping or at any time. So Apple Watch can record automatically arrhythmic state. So you can go to the doctor with the data recorded by Apple Watch, so the doctor can make a decision based on the data. And many patients with arrhythmias have been found like this in Japan, in US or something. So it's very good service. And okay, and there are many well-known sensors in the wearable sensing area. For example, accelerometers can detect the human movement behaviors and where they are on. Such as riding a bus or riding a train or something. So this kind of context can be recognized by using the accelerometer. And also, pressure sensor. Pressure sensor can sense the pressure data. For example, foot pressure can be acquired, and seating pressure can be acquired. So it's very important information for knowing the user context. And also, photoreflector is measuring the distance. So the photoreflector can detect the heartbeat. Heartbeat and so on. Yes, there are many applications here. And also the EEG. So this is a kind of brain sensors. So it can detect the drowsiness, stress, and the concentration, which are the situation related to the brain condition. Okay, and also, EMG sensor, muscle sensor. So it can detect the force application of the user. So on the muscle. Okay, here for example, this is an example of using accelerometer. Okay, you can see the waveform like this. So this is an accelerometer for axis X, Y, and Z. So if the people is walking, I think repeated waveform can be seen like this. And if she's running, yes, the shape of the waveform changes drastically like this. So by seeing this information, you can think that properly calculate the characteristic values from this data, so the system can classify the types of human movements. And also, so this is an this is an example of using foot pressure sensor. Here, this is a very thin insole type device that is very thin. So inside the shoes. So and like this, yeah. So there are more than 100 pressure sensors, 100 pressure sensors like this. And this data can have really detailed information of walking. For example, this people is a heel strike type walking. Yes, so run at the heel. Yeah, so people is a heel strike type. You can see that point. This person has a walking style where they land on heel and release with a toe or something. So this kind of pressure sensor can be used for analyzing the walking style and the running style for the athlete. So okay, such kind of various types of information can be acquired using wearable sensors, and we can apply this data to various wearable computing services. Okay. Okay, so yeah, by showing the examples of wearable sensors, so I'd like to say that what is the essence of such wearable sensing and wearable computing? I believe that the essence of the wearable computing is to realize personal design. So personal design is a term I made as a, actually, yes, personal design is a term I made as a contrast to universal design. So nowadays, the term universal design is used in a very broad sense. So, but in a narrow sense, universal design means that everything should be designed to be usable by everyone. Yeah. So everyone means that a right-handed person or left-handed person, a tall person or short person, a male or a female or something. So this is a great idea, but I don't think it's the final goal. So in fact, the best design is one that is the best suited for each of us. So yeah. So this is this target of the personal design. So for example, you are probably using a laptop right now. Yeah, right now. I use a laptop now. But which has a fixed design with a fixed size display and a keyboard for input or something. So with wearable computing, if you want to see information all the time, so you can use a head-mounted display and see information all the time in front of your eyes. Or if you don't need to so much information, so you can use a watch-type display and see information only when you need it. So if you don't need visual information, yeah, you can remove the display from the wearable computer, and you can use only the earphones, headphones to receive services using only audio. So you can input information to computer by keyboard, voice, and gestures, or anything else as you like. So this is one kind of personal design is realized for by using wearable computing technologies. And so what is the application for personal design? Is, for example, the most obvious example is to overcome a handicap, as only the parts of the body that are weak points can be overcome by wearable devices. We will discuss some examples of this purpose later. Not to overcome a handicap, wearable computing can also be used to enhance your strengths. Furthermore, wearable device can change their functions. Just as you change your clothes, yeah, making it possible to change their functions to suit your daily tasks and objectives. So this means that, yeah, a kind of personal design. So this is a kind of world we are trying to achieve in the next 5 or 10 years. Yeah, 5 to 10 years. Okay, so this is target of the wearable computing. And here is a video as an example of personal design. So actually, this is not my project. This is the Microsoft project, but it is one of my favorite studies. It helps people with Parkinson's disease to eat.
Mealtime brings people
Please
together.
see. Yeah.
It's more than a time for nourishing the body. We nourish our spirit and our relationships. But tremor, whether from essential tremor or Parkinson's disease, takes away from this experience, forcing people to focus instead on the basic task of eating. We decided to create something that would allow people to go out to restaurants or simply enjoy a meal without stress. We invented a liftware stabilizer to make it easier to eat with hand tremor and take the frustration out of eating. For the first time, we have the technology to actively stabilize a utensil in a device so small it fits in your hand. The liftware device works by sensing a person's tremor and intelligently stabilizing itself to make the food's journey from the plate to the mouth much easier. Liftware is designed to be a part of your life. The device is small and portable so that you can easily take it with you when you go out to eat. It's comfortable and effective because liftware allows the hand to shake while the cancellation technology in the handle stabilizes the spoon. In a clinical trial, we measure an average of 70% reduction in spoon tremor in individuals with essential tremor during 3 different eating-related tasks. It's easy to clean and hold.
Okay, so just a bit. I believe that you can hear the voice from the video. Okay. So yeah, what do you think about it? So I like this study very much. Yeah, it pinpoints and solves a person's weak point with computer technology. So I think this is an example of personal design. Yeah. Okay, so another example is a D-free device. So okay, you can see the device form, very small. This device will be available in Japan soon. So it looks like this, and it attached to the abdomen. So yeah, what is this device used for? Okay, so actually this device is an excretion prediction device. So when you wear this device, your smartphone will be notified that you will need to go to the toilet. Yeah, after 30 minutes or after 15 minutes or something. So for example, okay, technically it is a simplified version of an ultrasound echo device. The device scans your abdomen and recognizes the state of your excretion. Yeah. So what this device can do is, for example, it will be used for help care for people with dementia. So failure in the act of excretion makes it difficult to care for the patient at home. So the dementia patient may not be aware of the need to defecate to. So the device sends information to him or her. For example, you will need to go to the toilet in 30 minutes or something. So that the patient can live his or her life mindful of the need of defecate. Yeah. Of course, notifying caregivers is also a powerful use of this device. Okay, so yeah, this is one of the example. Yeah. Okay, and the following is an example of our research. So we sometimes, I sometimes went to rehabilitation facilities for handicapped person to discuss with people with ASD, autism spectrum disorder, and interview them about what they are having trouble with. Yeah, the most common problem is that they cannot read other people's facial expressions. So for example, one person says that it's hard to know if the other person is really smiling when he is laughing. And it's hard to be careful. Okay, yeah. And another person says that I'm not good at looking at people's faces. When I speak, so I look at their necks or their chest. So because it's very difficult to read the facial expressions. So to address this problem, yes, to realize the personal design for resolving this problem, we have developed this device, like this device, in the form of glasses. So this device has a camera on the forehead and analyze the facial expressions of the other person using AI. The results are secretly communicated to the user using with LED. So using this function, this device allows a person with ASD to know in real time what kind of emotions the other person is feeling. So the important point of this research is that this device improves the ability to recognize facial expression in SD person. So when wearing the device, users can always compare the emotions that the user has recognized with the emotions the device presented. Yes, so they are always aware of the differences, from my feeling and output from device. So living with this device, the user's ability to recognize facial expressions gradually improves. So, so it's very good device for the SD person. Okay, from now, so I will show several our research examples for wearable sensing technologies. Okay, at first, so I'd like to talk about sensing devices, sensing chips for 5 senses. So so we developed five kinds of sensors, including light sensor to get the visual information, and the sound sensor to get the sound information, audio information, and touch sensor, vibration sensor to get touching information, and the scent sensor, including the gas sensor, to get scent information, or taste sensor. So that's a very primitive. So that will sense the salt and sugar parameters. So this kind of sensors can be applied to various kind of fields, and also this is the sensing technologies, but these chips has an actuators. So for example, vision sensor have an LED or something to inform the visual information. Sound sensor has a speaker, and touch sensor have a vibrator. And sense sensor has an scent source, scent leakage to output the scent data. Or taste sensor is have something to output. Yes, salt unit and a sugar unit or something. Okay, I'd like to show some demonstration video here. So this is a scent sensor, so gas sensor example. So this is a very small pendant shaped device, including 3 gas sensor, air contaminant sensor, and methane gas sensor, and CO2 sensor. So, and the data can be acquired. So, this is an accelerometer data. So, this scent sensor can recognize having a meal. So this is very interesting application. So this pendant, this small 2 centimeter pendant, automatically recognize the user having a meal, like this. Yes, and it also can the device can recognize going to the toilet. So this is there's a methane gas sensor. So it's very easy to recognize to go into the toilet and so on. So, so what is the purpose of this application? Is that, yeah, actually, it's what is a healthy living, healthy staying in the home. So it's very important for elderly person. So it's very important to recognize the appropriate timing at the appropriate timings. The people having a meal and the people going to the toilet. So it's very important to check the people having a good healthy staying in the home and so on. So just wearing the pendant, including the 3 gas sensors, so it can be checked, and so without any camera and microphone and so on. Yeah. Okay, this is an example of sensing of the human facial expression. So the system, the glass type device, identifies and records smile and laughter with small sensor on eyeglasses. So I showed the video. Yeah. So this is a very simple device. The wearable device can recognize the wearing people make a smile. Yeah. Smile like this. Yeah, like this. And yeah, if the people make a laughter, well, ha ha ha, it will make laughter. So separately the device can recognize.
Recording in progress.
So yeah, the system is very simple. So just measuring the distance between the glass frame to the cheek. Yeah. If you usually, yeah, if you make a smile, the position of the cheek is a bit moved, so the device can measure the distance and recognize the making smile. So okay, so what is the purpose of this device? Yeah, frequently we made a smile. We made many smiles. So for example, when meeting a new person, so usually we make a smile. And for example, yeah, paying coins to the public bus driver or something. So, or okay, find the good things in the shop or seeing a pretty cat or something. So frequently we made a smile. And so when we smiling, when we make a smile in front of the you, so there's a important things happens usually. Yeah. So record what happened when you make a smile is a total of the recording data is a very good life log of you. So this kind of device is a very helpful to construct a life log. The next is very similar, so glass type device. So but it's a negative one. So recognizing the psychological stress. So with the glass equipped temperature sensors. So one of the things in medical area that is comparing the nasal surface skin temperature and core body temperature. So comparing these two temperatures, so we can the system recognize the stress level. Of course, so more accurate recognition. So it's better to use the heart rate data or something. So, but using this device, all the time the device measures the stress level. So, integrating with the wearable camera. So, what kind of timing? What kind of things? So we will have. We will feel the stress. We will feel the psychological stress. So, for example, yeah. So actually, using our device. So for me, so male reception in midnight is a very high stress. Okay, so the waking up timing is okay. I feel so very strong stress and so on. So wearing this device, yeah, all the time the stress level can be recorded. So it's very important and useful to know what kind of things I'm not good at or something. Yeah. Next one is also the wearable device to recognize something. So this is an sleep tracker. So eye mask shaped sleep tracker. So there are many commercial devices to track the sleep state, sleep level. So but most of the commercial device has very low accuracy. So for example, 4 level sleep level. So they're about 40% accuracy. So it's not very low. So I made new device for sleep tracking. So basically, the basic idea is okay. So do you know that there's a REM state, REM sleep. REM sleep means that very shallow light sleep. So REM means that rapid eye movement. So rapid eye movement means that even in the shallow sleep, uh, so the eyeball, even the people close their eyes, the eyeball moving in small increments like this. So so the definition of a REM sleep is that rapid eye movement. So okay, so it's better to recognize the eye movement directly. So I developed this eye mask shaped devices. So please see the video. So smart eye mask. Okay, the next topic is a research on what happens when stethoscope is worn all the time. Yeah. So I think you know the stethoscope well. So a stethoscope is an amazing device. Yeah, isn't it? So it can tell a lot of things. So therefore, we made it into a wearable device with 2 microphones, one inside and one outside. So when worn at all times, the inner microphone, for example, inner microphone acquires information on heartbeat, swallowing, and breathing, and so on. So there are many information can be acquired on by the stethoscope. And on the other hand, the outer microphone acquires body movement sounds, speech sound, and the environmental sounds. So it's very convenient device. So these contexts can be used for various purposes. For example, we believe they can be used to detect sleep apnea syndrome. So when a person sleeps while wearing the device, information on swallowing and breathing, which is necessary for the diagnosis of sleep apnea, it can be easily obtained by the device. And of course, the device can also be used while awake. So, but in sleeping state, it's very convenient to detect the sleep apnea. This is the example video of using our stethoscope device to detect apnea. So it's a very initial one, but I think you can imagine so how to use the device. In this way, our device can detect apnea condition. So I think in current situation, it's a bit annoying to wear the devices. So, but yes, we will improve that. A device easily wear at the night. Okay, the next is the stress sensor. Stress sensor is a closed type device, closed type sensor. So the sensor can measure how much this cloth is stretched. So like right in the video. So there are many applications using stretch sensors. Yeah, as you can imagine. So there are many applications, I think. And if you attach the stretch sensor to your arm, so by wrapping it around, so it can measure the circumference of the body parts, and so it means that the value means that how much power you emitted. Yeah. So yeah, this is very convenient and flexible, good sensor. So the next two slides, there are none applications utilizing the stress sensors. Okay, the first example is recognition of swallowing and its intensity using stress sensors like this. Yeah, I showed the video. Okay, so dysphagia, trouble swallowing, has become a major problem in recent years. And aspiration problems caused by dysphagia and are becoming a leading cause of death among the elderly person. So currently, the analysis of swallowing status is not easy. It's very difficult in the hospital. So as it involved the use of X-rays and contrast media, so it's very hard to do. So swallowing ability varies from so swallowing ability varies from morning to evening, and it changes even during meals. So continuous evaluation is very effective to evaluate the condition of the swallowing capability, and the device. So developed by, in conjunction with a doctor and a rubber material company, is choker shaped and it can record the timing and intensity of swallowing. So as well as coughing by aspiration or in a smartphone application. So this data will be recorded all the time. So various kinds of information can be presented to the doctor. So this is one possible solution to evaluate the swallowing ability. Okay. So the next is an example of stress sensor attached to the knee supporter. So like this. Oh, sorry, it's in the Japanese transcript. Yeah. So a knee injury can lead to a long withdrawal for an athlete. So it's a very big problem. Knee injury is a big problem. So we have constructed a system that constantly measures the knee flexion angle by attaching a stress sensor to a knee supporter. So in general, the knee flexion angle indicates whether the athlete is running with a correct form or not, or whether there's a strong impact on the knee or not. Something. So in addition, so our system can measure the internal and the external bending of the knee. So it's possible to evaluate the risk of ligament damage in advance. So in the training timing, if you use this kind of device, a supporter type device, so you can avoid the serious problem of the knee. Okay. And also the next is the sensing system in the nostril. So I will explain why we need these sensors. So so do you know why you have two nostrils? Yes, hole. There's two hole on the nostril. So the reason for having two eyes and two ears is very clear. Yeah, to get a three-dimensional sensation. But as for the nostril, we don't have the ability to identify the direction of the smell. So on the other hand, the nose has a phenomenon called the nasal cycle. So this is a phenomenon in which a person uses only one of the nostril as a main nasal passage. Yeah. And the main passage changes every few hours, including 7 or 8 hours. The main nostril changes. Yeah. So although this fact is known, the cause of this phenomenon has not been investigated well. So this is because there is no system that can measure which nostril is being used continuously or all the time. So our device may be able to solve the mystery of the nasal cycle. So we are currently conducting such research. So please see the video. Yes, this is a device with a small temperature sensor, 1 millimeter. Yeah. And you can wear the device like this. Yes. It's not so hard to wear. Yeah. So by wearing this device, the airflow for each nostril can be recorded all the time. Yeah. So I think it can resolve the problems of the mystery of the nasal cycle like this. Okay. Okay, the next system to apply wearable sensor to the beauty field. This is a research we are currently working on with cosmetic companies. This is measures the amount of moisture evaporation from the skin. So the amount of water evaporated from the skin is different from the amount of water the skin contains. So it's a different thing. And it indicates how strong the skin's barrier function. So yeah, so it indicates that how strong the skin's barrier function is here. So if the barrier function of the skin is excellent, water evaporation from the skin will be very low. And if the skin is rough, water evaporation will be high. Yeah. So therefore, by measuring the amount of moisture evaporation from the skin, so we can measure the barrier function of our own skin. And we can also determine what our skin is affected. For example, the barrier function of the skin decreases when exposed to the wind from the air conditioner or something. So it is a little different to explain the measurement principle. So, but basically, multiple humidity sensors exist in the chamber. Yeah, like this. Yeah, like this. So as shown on the left of these chamber figures, when moisture evaporation is low, enough low, all sensors show close values. It's almost the same values. And when moisture evaporation is high, so the value of sensors close to the skin differ from those far from the skin. So the moisture evaporation of the skin is measured by capturing these changes in value. So yeah, so this is a bit big, but so collaborated with a cosmetic company. Now we are developing this very small device to catch the skin condition all the time. Okay, so okay, it's not so much time. Sorry, I will skip some of them. Okay, so the following is an example of sensing in the sports field. So this is an example of the application of sensing technology to the Japanese national team of Paralympic athletes. Yeah, so he's a Paralympic athlete. So we supported the players in the training camp for the Japanese national bocce team. So we use a variety of sensors to record their play and used the result for training. So here is an example. Yeah. So this player tended to score a little worse in the second half of the games. So, but they didn't know why. Yeah, why my score get worse in the second half of the game. So, however, one of the sensors we had prepared, a seat sensor. So this is a seat sensor, a seat with many pressure sensors. Yeah. So yeah. So a game progressed. According to the game progressed, the center of gravity shifted a little to the right, like this. Yeah. So the center of gravity is actually placed at the center at the beginning of the game. So, but as the game progresses, the center of gravity shifts to the right. So it's a very small difference. So, but a very big impact to the score. So the players themselves were not aware of this change because of their disabilities. Yeah. So based on the result, we conducted with team coach, and made some training adjustments, including the placement of the equipments. Yeah. So and the problem was solved as shown in the figures below. So this is the same person, and as the game progresses, there is no change in the center of gravity. So we can improve the ability of the sports for him. So as a result, this athlete won a silver medal at the Paralympic. So it's very effective example using wearable sensors to the athlete, to top athletes. Okay. So there's okay, because there's not so much time. Yeah, okay. So yeah, I will skip most of them. Yeah. Okay. Okay, so the next example is a system for preventing dry mouth. Yeah. So dry mouth is a condition in which there is a continuous lack of saliva in the mouth. Yes. So our system senses the state of saliva in the mouth. The sensing mechanism is that by shining infrared rays of the specific wavelengths at the temples to the inside, so we can estimate the amount of water in the salivary glands inside the face. Yeah. So so that point, that place is where saliva is stored, and can determine how much saliva is in the mouth. So when the system determines that the amount of saliva is too low, so it will stimulate the salivation by emitting an odor stimulus such as a lemon odor or something to increase saliva secretion. So in this way, the combination of sensing and actuation make it possible to keep people healthy. Yeah. Okay. So here I'd like to summarize the sensing technology. So how will our lives change when such a world arrives? So we have so many wearable sensors. So first of all, we can say that we can develop sensors to measure almost any information you want in several years. Yeah. So then, using such kind of sensors, how will sensors change medicine? So we think that the medicine will change from point medicine to line and aerial medicine. So until now, people have gone to the doctor once a week, for example, once a week for advanced measurements to check the progress of their disease. During the remaining 6 days, during the remaining 6 days, by using a wearable sensor to take measurement, even wearable sensor take the data, even simple ones, and giving the result to the doctor. various problems can be solved, I think. Yeah. So, for example, there's a nervousness in front of the doctor. So yeah. So I think it's important to measure the vital condition continuously at all the days. So this model is a kind of future medicine model. So continuous mediation. Yeah. Also, we can say that there are several types of sensors, some such as hearing aids and pacemakers, so must be worn all the time, while others such as clutches help to enhance the person's abilities. So when developing sensors, so we should consider which type of sensors we want to develop. Yeah. So yes, so finally, yeah, this is the summary of my presentation. Yeah, in this presentation, I present our work on the wearable sensors. So many. So it's a bit confusing, but yes, this is a state of the art wearable sensing technologies in the wearable computing field. So thank you so much.
Thank you so much, Professor Derrida, for very remarkable presentation, which we can learn a lot of wearable sensing devices. And I would like to invite the participants to ask a question. And we have one participant here. Oh, okay. Directly. Okay, so I would like to invite Professor Kusnul Ain to raise a question.
Okay. Thank you.
Mhm.
Okay. Thank you.
Because there's a trouble of sound. Yeah.
Okay, thank you. You hear my sound, Prof. Terada?
Yeah, I can hear. So
Yes.
it's a bit difficult, but it's okay. Yeah.
Okay, I'm Kusnul Ain, Prof. Terada. I have one question. I have interested with your sensor about pressure sensor. Okay. We know when we analysis in sport science and medical science, medical rehabilitation, we can use force plate. I think you know force plate itself a many expensive device. Okay, Canada. Okay. Could your sensor, pressure sensor, can analysis for sport science and medical rehabilitation analysis? Thank you.
Okay. Yes. Yeah. I think in future, I think this kind of pressure sensors widely used in the rehabilitation area, or yes, analyzing the many of human behaviors. So I hope we will develop many kind of systems to support medical and sports science. Yeah. Thank you.
Okay. Thank you so much, Prof. Derrida, and also Prof. Kusnul. And maybe we still have a little bit of time. So anyone would like to raise any question to Professor Derrida? For the online audience? Is there, there is one in the chat here. Okay. Maybe I will.
There's one people raising a hand.
Hey. Okay.
I'm sure. Yeah.
Wait. It's not. I think I will read one question from the chat from Ari. is it possible to create a heart rate monitor using a smartwatch? Using a smartwatch available in the market. In Japan, is this used by the doctor to diagnose the disease?
Okay. Okay, so there are many devices can detect the heart rate or heartbeat signal. So the detailed signal can be acquired. So, but yes, I think it's a bit difficult to use this data for the doctor to diagnose because there's a strict law. So currently, we cannot use the smartwatch data to medical purpose. So we act so such kind of wearable sensor data can be used for diagnosis. So I think it can change the medicine drastically. So, but yes, as you may know, under current condition, it's a very difficult to do in current hospital. Yeah, it's a very big problem.
All right, thank you. I hope that answered the question from Adi. All right, and we still have the time actually. Maybe we can go through another question from the chat box. Oh, all right. Rafi, do you want to ask a question?
Yes, yeah.
Yeah, sure. Okay, please, Rafi, proceed.
Thank you so much for the time. And thank you so much, Professor Terada, for your research and what you do. It's very fascinating for me, especially in sport medicine and in the future, I guess, which if we like to look at the current progress for the at least sensor for human being, Elon Musk, right? He also developed the Neuralink that connect the brain wave in with the how human body will work, and maybe with that plus something like your research can help also. But I'd like to ask about the future as well. What it will be for the human being? I guess like for the sports. For sport, okay, for now it's only for medicine and the disability, but is it possible to enhance a human being capability with the sensor and getting more uh, perfect result or more precise solution and training for them? Maybe not just for the athlete, maybe for the military as well. Yes. Thank you so much.
Yes. Yeah, I think so. So this is there's a research area named augmented human. So this is a very I think it's a kind of dangerous area, but yes, how to augment the human being. So like Elon Musk, so he's a bit terrible so purpose. So but I'd like to say that my research area is based on the wearable computing, and also Neuralink is about the area for implant technologies. So for wearable computing is and the implant computing is a bit similar, but the situation is quite different. So wearable computing, we can change the functions as you like. So for daily, you can change the functions by changing the crosses, right? Like changing crosses. So like changing functions by changing the wearable computing devices. But implant technology, so we cannot change the devices. So like pacemaker or some other kind of implant computing is so very strong purpose. But if you don't want to change the function all the time, I think implant technology should be used. And if you want to change the functions as you like, you can choose the wearable computing technologies. And I like the wearable computing technology side. So I think it's a bit different from the Elon Musk's comments. So, but yes, I think augmented human is a very strong field to apply the wearable sensing technology or wearable actuation technology to enhance the human capability. So now you can see the I think 3 or 4 kilometer to see some insects or something, and here the and automatically recognize the surrounding situation and advise you to do, so what should you do or something. So this is a main two different but the two main research area related to the wearable sensing technology. Yeah, thank you.
Yes, yes, yes. Thank you so much, Professor.
Thank you so much, Professor, and also for the participants that has raised their question. It's a very interesting one, but because we have a limited time, so I think we can conclude for this session from Professor Sutomo Terada from the Kobe University. And I would like to can we give a round of applause to Professor Terada?
Thank you. So if you have an idea, so please collaborate with me. Yeah.
Okay,
Thank you so much.
Thank you so much. I'm looking forward for the next collaboration, Professor. Thank you.
Thank you.
Okay, what an excellent presentation from Professor Sutomo Terada. Thank you, Ms. Intan Firdausi and Professor Sutomo Terada, of course. Ladies and gentlemen, we will now have a short 10-minute break. You may take your time.
We kindly ask all participants to return to this room by 10:45 a.m. sharp to begin the next session. Thank you. Welcome back, distinguished participants. We hope that you enjoyed the break. We are now ready to start plenary session 3. I would like to welcome back our moderator, Ms. Intan Firdausi Wardani, Bachelor of Engineering, Master of Science.
Ms. Intan Firdausi will be introducing our third keynote speaker, Associate Professor Cik Azra Hanim Abdullah from University of Putra, Malaysia. To Ms. Intan Firdausi, the floor is yours.
Okay, thank you. Good morning, everyone, and welcome back from our very short break. I would like to welcome Associate Professor Dr. Cik Azra Hanim Abdullah, or we usually call her Dr. Chacha here.
How are you, Dr.? Fine, thank you.
All right, so a brief introduction from her. She is from the Department of Physics, Faculty of Science, University Putra Malaysia, or UPM. Dr. Chacha is a biophysicist whose expertise lies in biophysics, material science, and nanobiotechnology. She got the PhD in biophysics from the University of Surrey, UK in 2012. And now, she previously served as the head of Nanomaterial Synthesis and Characterization Lab at ICPIAM Institute of Nanotechnology and Nanoscience. And now she also held international academic roles, including the visiting professor at Universitas Brawijaya, faculty exchange at Ajman University UAE, and visiting researchers at CISAM Jordan and Synchrotron Thailand. And her numerous recognition, including the L'Oreal for Women in Science Award 2023. And now she will share her talk with the title of Smart and Sustainable Scaffold Biomaterials, the Nanotechnology Advantage. Let's welcome Dr. Azra or Dr. Chacha. The time is yours.
So, Assalamualaikum and a very good morning to all participants physically here and also online. So, first of all, I would like to thank the organizer for inviting me for this session. So, today I would like to share with all of you in terms of smart and sustainable scaffold biomaterials, where I would like to focus on how can nanotechnology advance these scaffold and biomaterials. Okay, so while waiting for the technical, so I just would like to introduce yourself, although Dr. Intan already mentioned. My background is basically biophysics. So previously I received my degree in medical physics, and then I changed my research area during my PhD towards nanobiophysics. So at that time, I didn't know that, like whatever that we are doing now is booming. So at that time, I just continue learning about nanotechnology, and at that time, I'm thinking of we would like to bring like tissue engineering and regenerative medicine to Malaysia. So one of my mentor is also a Japanese. I'm not sure whether some of you are aware or not. And his name is Professor Kazunori Kataoka, who's in 2009. He already have like a vision that one day we can have what we call a personalized medicine. So since that, I really following him in terms of the research and everything. So in 2017, I able to meet him personally. So that's why I think once I'm back from my PhD, of course, due to our facilities limitation, so I hold for a while in terms of the research related to tissue engineering and regenerative medicine. But luckily, 2019, I came here as adjunct professor for FST. Then I think I collaborate with Department of Physics lecturers. So I think now I work with Dr. Aminatul. So I think we have created several scaffold for various applications. Basically, my talk today, I will share with you in terms of what is smart and sustainable scaffold. Then I will introduce to you in terms of the nanotechnology and what else that we can do in terms of the future research, in terms of how can we advance this field for various applications in the future. Okay, so let's have a look now. I think we have a lot of issues. That's why I also thinking of, can we heal tissues like nature does with smarter and more greener? Because if we have look now, we have a lot of issues related to the developing the tissue regeneration scaffold. And one more, we also need to have a look. Another issue is the cost of implant waste in traumatic orthopedic surgery and sustainability consideration. So this is the study conducted to have a look in terms of what is the current cost. So now when we talk about regeneration, it's no longer science fiction, it's basically material science. So we need more people in material science to have a look at how can we heal tissues like the nature does. So next, when we discuss about this topic, of course, I would like to start with, we have a lot of healthcare industry challenges. For example, the increase in the chronic diseases, antibiotic resistance, and also we also have some what we call social related limitation. For example, unequal access or ethical dilemmas, and sometimes the expensive nature of the advancement for the treatment. So that's why we need to highlight the how can we come up with more creative and enduring solution to enhance not only the patient care, but at the same time, can we improve the effectiveness and expand the healthcare worldwide. So next, we would like to focus on the nanotechnology. So nanotechnology basically provide more promising opportunity to tackle all these challenges by simply we can just tune the materials and device at the nanoscales. So basically the topic today, I will cover also tissue engineering, regenerative medicine, and precision medicine. Okay, so what is tissue engineering and regenerative medicine? Basically, we are focusing on how can we stimulate the natural tissue structures of the body by where the nanotechnology can use to fabricate the scaffold that stimulate the cell growth. And when we discuss about precision medicine, it's all about the integration of the genomic and nanotechnology treatment that we can customized to precise the genetic composition of the individual patient, thereby augmenting the efficiency or the precision of the medicine. Okay, so for the tissue engineering, when we discuss about tissue engineering, okay, so when we discuss about tissue engineering, in general, when we discuss about tissue engineering, we are focusing on the needs of to restore, to maintain, and to improve the disease or the damaged cells or tissues. And for this tissue engineering, we need to have basic principles. So to all researchers that would like to venture into tissue engineering field, they need to have the principles in material science. They need to know about cell biology. They need to also know about transplantation as well as engineering. And of course, there is a lot of challenges when we discuss about tissue engineering. We have challenges in terms of creating the biomaterials, the cell sources, the vascularization of the engineered tissue, and of course, now we also enter into what we call the design of the drug delivery system together with the biomaterials. And here I can see that as people or researchers in the nanotechnology, I can see there is a role of nanotechnologies in helping tissue engineering in the fabrication at the nanoscales? How can we fabricate more biocompatible scaffold? And how can we control what we call the spatial temporal release of the biological factors? And also, how can we resemble the scaffold that we create to mimic the extracellular matrix? Okay, for regenerative medicines, if researchers would like to venture to the regenerative medicine, they need to know the knowledge of stem cell therapy, gene therapy, and immunomodulation therapy. Apart from that, we need to know that when we join or when we get into this regenerative medicine, we need to have a look in terms of the challenges. It's not easy, but it's doable. For me, we need to also have a look in terms of the ethicals and the regulatory issues, where I think the researchers need to work with industry and the policymakers as well. So apart from that, we have some technical challenges, sometimes tissue or immune rejection, and of course, some will cause what we call cost and scalability. So I can see for this regenerative medicine, if we have the knowledge of nanotechnology, we basically can improve the treatment, the precision, the efficiency, and the possibility of less invasiveness. So basically, we can focus using nanotechnology in regenerative medicine in terms of how can we deliver the drugs, how can we create the environment that support both cell and tissue. Okay, so why we would like to focus on these smart materials or biocompatible scaffold? Basically, because we know there is healthcare needs and sustainability challenges. So now there is a lot of issues related to the cases of the tissue damage or organ shortage as well as chronic wound. So that's why for those in material science, now we would like to focus on creating biomaterials, either synthetic polymers or metals or ceramic, which is non-sustainable. So that's why we would like to focus more on, in the future, more on the smart and sustainable, where we can have the future of regenerative medicine. Basically, we would like to move from the traditional implant to the more bio-inspired scaffold. Okay, so here I try to enhance how nanotechnology can be used to help us to achieve this mission. So basically, we can see that the nanostructuring will enhance the surface roughness so that we can have better cell adhesion. And of course, we can have increase in terms of the mechanical reinforcement and control degradation. So now the issue is the scaffold have short times. So that means fast degradation. So at the nanoscale, basically the cells feel difference. So that's why we would like to focus in on embedding or looking at the advantage of nanotechnology in this field. Next slide. So when we discuss about nanotechnology, of course, we're focusing on how can we manipulate the materials at the nanoscale level. And when we discuss about nanomaterials, we are focusing on the tiny pieces that we utilize in the technology. And we have another term called nanomedicine. So nanomedicine basically using these small wonders of materials to treat and sustain the life in the novel ways that are still being investigated. Okay, so I think I just would like to share briefly with all of you in terms of what is nanomaterials. So nanomaterials, basically we are focusing on the material in the size of 1 to 100 nanometers. So basically for these nanomaterials, they can have various dimensions. We can create them using various methods, and we can use them for various applications. So next, I just would like to share, when we discuss about nanomaterials, basically, we can categorize them into not only the shapes, but also in terms of the dimension, whether the nanomaterials is in 1 dimension, 0 dimension, 1 dimension, 2 dimension, or 3 dimension. Apart from that, we can also classify them based on high or low aspect ratio or the state of the materials, and finally based on the chemical composition. So next, apart from the categorization of nanomaterials, I also would like to share later on with you, because previously I'm focusing on the carbon nanotubes. So during my PhD, I used single wall and multi-wall carbon nanotube and looking at how cells basically sensing the arrangement of the carbon nanotubes. And we also put, like some of the growth factors, and we try to give like certain direction to the cell, and we try to study how basically cells seeing the materials at the nanoscale level. So for that, we also using, at that time, I'm focusing on the liver cancer. So we would like to see what happened after you put liver cancer on our scaffold, and then we try to have a look in terms of certain protein that been produced by the cell. Okay, so apart from the categorization is based on the dimension, shape, size, or in terms of the composition, we also can divide nanomaterials into organic nanoparticles or inorganic nanoparticles, or like the combination of organic, inorganic, or the hybrid of organic and inorganic. So basically here I would like to share there is a nano-sized scaffold that suffices traditional materials in promoting tissue growth. So here is one of the example, the work by Akursani in 2022. So basically they are looking at the biomaterial composition and scaffold architecture for the periodontal regeneration. So the bioactive molecules and drug delivery can also be controlled by this scaffold. Okay, next, we also have another study by Anchum et al. So this one is focusing on the electrospun biomimic nanofibrous scaffold. They are looking at the affinity for the cell binding, the appetite mineralization, and osteoblast differentiation. So why we would like to focus on the advantage of nanotechnology? Because it enables the precision at the molecular level, facilitate the functionalization. And when we discuss about functionalization, either we as a researcher would like to study in terms of changing the growth factor, changing the drug loading, or the bioactive coating. So here is the example. For example, nanohydroxyapatite, nanosinoxide, graphene oxide, or biogenic magnetite. So in our group, we are focusing more hydroxyapatite and nanohydroxyapatite. But also for your information, we try to also take the hydroxyapatite utilizing from the marine waste. So later I will share with you. So next, when we discuss about smart scaffold concept, what does it mean by smart scaffold concept? So basically, smart means responsive to stimuli. Basically, you can create a scaffold that responds to, for example, the pH, the temperature, or the light, or the electric field. Then the application, for example, for the electric field, you can use in the nerve regeneration. So this one, basically, for the nerve regeneration, we need what we call conductive scaffold. And for the bone healing, we need what we call mineralized nanostructures. So basically, by having nanotechnology, we can add intelligence to our passive biomaterial. Apart from that, I would like to share also with all of you about concept of green nanotechnology. So currently, my focus in terms of the synthesis of nanomaterials using green synthesis. So basically, the green nanotechnology, we are focusing on the extra-friendly synthesis using plant extract, biopolymers, or marine resources. So by having green nanotechnology, we can eliminate what we call waste or the toxic chemicals, and these align with UN SDG 3, 9, and 12. So for for your information, currently in our group, we are focusing on the green synthesis of zinc oxide nanoparticles or nickel-derived hydroxyapatite. So this is what we can say that our group focusing on the nanotechnology and nanomaterial synthesis using biological synthesis of nanoparticles for various applications, but mainly for medical and environmental applications. So I just would like to share with you for the green method, green nanotechnology is very simple. And in our group, we are focusing more on the plant and plant extract. So for your example, maybe if you go into your kitchen, you can see sometimes you have already onion, right, that you didn't use. So basically, you can use that also in creating green nanomaterials. Okay, so very simple. You have the plant or the food scrap, so you can just ground or cut them and then immerse in the hot water. So you get the extract, and the extract you just basically mix with the salt of your interest. If you want to make zinc oxide, for example, you can use the zinc-based salt. Okay. So here are various type of one-dimensional nanomaterials that been created using green concept and can be used in various applications, not limited to medical, but also can be used in electronics as well as in sensor. So why, when we discuss about green synthesis, why we need to focus in terms of the extraction? As I mentioned, you can use whatever that you have in that leftover in your kitchen, right? But you need to know in terms of the extraction method. So the extraction will affect the formation of the nanoparticles in the green synthesis process. So basically, we would like to have a look in terms of what are the natural compounds that can have effect in the final properties of the synthesized nanoparticles. So there are a lot of things that we need to consider when we discuss about green concept. Of course, for this, we need to have a look in terms of the reaction kinetics. What are the parameters? Because sometimes each plant or plant extract, they have one parameter that give more yield compared to another. Maybe you can have a look. Here I just give two, for example, temperature and pH. The other thing is impurities. Okay, so here is the example on how can we utilize green nanomaterials in scaffold. For example, there is a study by Ali Reza. So they studied the effect of green synthesis CiO2 nanoparticles, collagen and HA scaffold for bone regeneration using in vivo model. There is also studies conducted utilizing silver nanoparticles, impregnated nanocollagen as scaffold for soft tissue repair synthesis, characterization, and in vitro investigation. We also have chitosan sealed fibrium scaffold with green synthesized metal oxide nanoparticles. So that's why I think this topic is still a lot more we can research, because I think maybe later on I also would like to ask Dr. Aminatun and team here, because we have a lot of nanomaterials that synthesize using green synthesis. So maybe I can pass to the team here to further enhance the study on the scaffold. So what is the effect if we change different type of green nanomaterials in the scaffold formation? Okay, so as I mentioned, in our group, we are focusing also on hydroxyapatite. Currently, we try to derive the from the seashell nickel, because they have what we call calcium carbonate. And then from here, we basically can also have a look in terms of how the crystallinity can also affect the cell affinity. So basically, in our group, we are now focusing on how can we turning the marine waste into medical value. So here is example of the nanocomposite scaffold. So we have, for example, PCl, ZNO, or PLA graphene oxide composite. We can use this composite for various applications, for example, antibacterial, enhanced tensile. In terms of the properties, it can enhance the tensile strength and improve the osteogenesis. And when we have the nanocomposite, of course, similar to synthesis of nanomaterials. After you synthesis, after you prepare, you need to do what we call characterization. So here you can use either SRD, FTIR, or SEM. Okay, so for the future, we hope that for this smart system, we can have what we call self-healing scaffold with AI guided, because now I think we are in the era of AI. So I'm really looking forward if more material scientists that can utilize AI in helping us to create more what we call self-healing scaffold. And we also would like to focus on the conductive scaffold with electrical cues for the nerve growth, because I think now we also have a lot of issues related to nerve regeneration and integration. Of course, we can also integrate with expert in sensors or biosensors for the healing monitoring. Okay, so in terms of the fabrication of the scaffold, briefly, currently majority of people using electrospinning for creating what we call nanofiber network. Apart from that, there is also researchers that try to use 3D bioprinting, but sometimes when we discuss about 3D bioprinting, we need to also think of the cost. Okay, so by having 3D bioprinting is good because you can create more complex, more architecture, and you can also looking at the patient-specific scaffold. We can also utilize what we call additive manufacturing for sustainable and precise scaffold formation. So again, when we have the scaffold, the next thing is we would like to evaluate the toxicity of the scaffold that we prepare, especially now because there is a lot of nanomaterials that been included in the scaffold as well. So before we integrate our nanomaterials into the scaffold, we need to test the how toxic is the nanomaterials itself before we can put them into the scaffold. So when we discuss about the biocompatibility, we can use brine shrimp, zebrafish, or cell line as a common method for toxicology. And of course, here is just the simple assay, because in our group, we synthesize green synthesis of nanomaterials. So usually we try to use brine shrimp because it's so cheap. And one more, they also helping us. Apart from our vision to create materials, we also need to have a look what happened after the materials been used. Okay, whether the materials will harm the environment or not. That's why we can get the data or information from brine shrimp assay. Just to share with you, in our group, we try to create the green synthesis nanomaterials, which is iron oxide, and we try to compare with the chemically synthesized iron oxide nanoparticles, and we test the toxicity using brine shrimp. So we can see that the cell viability, the shrimp viability can be, we can say that there is no toxicity for the green synthesized nanomaterials compared to the chemically synthesized. So here is our previous studies related to the scaffold. So I think this work together, together with Bu Aminatun. So basically, we focusing on the fabrication and compatibility evaluation of the PCL hydroxyapatite collagen-based fiber scaffold for anterior cruciate ligament injury. So basically here, we also conduct what we call cell viability assay, the degradation rate, the mechanical strength, as well as the physicochemical characterization. So maybe in future, we can enhance this project by adding green nanomaterials. Next, we also have another study on the mechanical and thermal properties of the nanohydroxyapatite. But this time, at that time, I didn't give the hydroxyapatite from my makers. So maybe that one we can further collaborate with the team here to see what is the changes if we change the nanohydroxyapatite with the nanohydroxyapatite that we create using Naker from Malaysia. Next, we also have a look. This is my final year project students. Okay, so basically we try to have a look in terms of the effect and sintering process of the Naker-based hydroxyapatite scaffold for bone tissue engineering. And before that, yes, as I mentioned, during my PhD, I'm focusing more on scaffold-based carbon nanotubes. And of course, before this, I also try to study how the cells basically able to learn the nano pattern. And I also focusing, as I mentioned, I also focusing on the scaffold for drug delivery. So here we are focusing on how can the multi-wall carbon nanotube affect the enzyme. And this one we are focusing on the use of the scaffold for tissue engineering and liver-specific function. So here we can see how we characterize our cell material interaction, or how cell interact with the scaffold that we create. I'm not sure if we can play the video for the align and smooth BKP. So here you can see, yeah, the other one. Yeah. So this one is how the cell sensing the smooth surface. The other one, we have the video. If you can click on the other one here. Yeah. So the other one is how the cell basically sensing the nanoscale structure. Okay. So apart from cell sensing, we also need to have a look in terms of what are the protein that we express. How the cell express the protein on the smooth surface compared to the surface that having a nano pattern. So future work, we hope that we can, as I mentioned, we can use AI to design the optimization of the scaffold, and maybe we can also integrate the scaffold with tissue or tissue on chip. Before this, we have like lab on chip, right? But now we can also have look how can we create tissue on chip. And next, of course, we would like to have what we call a smart biodegradable implant. So, of course, there is some challenges. For example, when we discuss about scaffold, the challenges is the biocompatibility testing and the long-term degradation. Of course, the second thing is how much does it cost, and the reproducibility as well as the regulatory approval if you would like to move from lab to clinical or bedside. And of course, there is a need for interdisciplinary collaboration. Okay. So before that, I also would like to share in terms of the scaffold characterization. I think I would like to share with you that we can also use synchrotron. So for example, we have synchrotron in Jordan that can do like tomography. So we can see what happened after we coating our scaffold with materials, or we can also see if we have like PCl, hydroxyapatite, collagen, right? So what is the ratio? What is the, how homogeneous it is? So basically we can use the synchrotron. So for this one, this one is in Jordan. So I mentioned to Bu Ami, the application open up to 17th of November. So you can have a look at the website. Okay, so basically once you get this opportunity to characterize your sample, it will give you a lot of benefits. And one more thing, because this can also considered as what we call international grant. Okay, so this is the IR, okay, synchrotron IR. If let's say if you would like to focusing more on the drug delivery, nano encapsulation and everything by using the synchrotron IR, basically we can map where is our drugs, where is our polymer, and we can also do in terms of the function, looking at the function, and you can see how the drugs, whether it is homogeneous or not. Okay. Next, we have Dr. Fariha currently leading the BITS beamline. So BITS beamline is, as I mentioned, is focusing on the 3-dimension tomography and X-ray. So basically we can see what is inside the scaffold and how the scaffold, if you have like the coating and everything, you can see, and then you can do the reconstruction. Of course, I would like to conclude and share with you the vision forward. So to conclude, nanotechnology empowers a scaffold by making them more intelligent, adaptive, and more biocompatible features. And of course, when we're creating anything, we need to also have a look in terms of the sustainability and safety. And of course, when we discuss about smart scaffold, we would like to enhance. It's not only make the scaffold that smart. How about the one that exposed to the scaffold, which is the cell? How the cells basically looking at the smart scaffold? Are they happy? Because on our side as a material scientist, we say that, okay, this is already smart scaffold. But when you introduce to the cell is totally not happy. So we need to also have a look in terms of the cell adhesion, the tissue interaction, and of course, the control regeneration. So as I mentioned, we need to work with people from various backgrounds, physicists, material scientists, biomedical engineers, so that we can translate the innovation into clinical impact. And for the future, we would like to focus on what we call green regenerative medicine. And now I think people everywhere is talking about planetary health, right? So now we would like to focus on the sustainable innovation that care not only for people, but also for the planet. So with that, thank you so much.
Okay, thank you so much for a very interesting presentation as always, Doctor. And I would like to invite all the participants to ask any question. Is there anyone? Okay, we have one, Pak Heri. Do we have another one? Okay, so we can start from Pak Heri.
Thank you, Senator. Nice presentation, and this is quite interesting when we are talking about the materials science and also its applications in terms of the biophysics. Physics is the source of everything. We start the materials in advance. We start also the AI at the end of the current technologies. You mentioned that AI is very important at the moment in terms of how to expand the interpretation of the projection of the material science. My question is, because I had the experience how to use the AI using the image processing from the XRT or STM or FEM, but the problem is, for me, is actually because we need to have the expertise for the interpretations. And if we go around the published articles, then it's not going to be very consistent, because someone interprets in this way, but the other one interprets on the other way. If it's possible, because this is kind of the collaboration that we need to look at for what we're interested into our activities. If your research and with Professor Aminato have done with all of the XRT or SEMOTM, the image processing one, and you already mentioned that what kind of interpretations you made, and then you sent to us on our research group. We are actually a different research group with Professor Aminato, but we are very interested to the AI, how to interpret and how to recognize the pattern so that we can do whatever double check, can do comparison between what's in the experimental side and also in the computational side. So if it's possible, I will be very happy to get the constituent and very comprehensive interpretation, so that it's not going to be meaningless when we interpret our AI with any specific categories, but it's going to be very beneficial. Thank you very much.
Thank you so much, Pak Hari. So I think, yes, I think we need to work with you. And in terms of, I just would like to share, because last month I went to Beijing and Wuhan University. So basically at Wuhan University, the postgraduate students, basically they are creating their own AI optimization. Because, of course, I think it's good, because I think Malaysia, Indonesia, we have similar issues in terms of limited of funding, right? So when you have the AI for optimization, basically you know already, For example, the scaffold, which type of scaffold, what is the size? So basically we can save a lot of things. So maybe in terms of the images, we can collaborate with you. And then maybe if I have the opportunity to also connect you to researchers in China, I'm more than happy to. So that I think maybe from my side is more on the nanomaterials, who are me on the scaffold, and then you on the AI, and then we have another expert on the optimization. Yeah.
Okay. That's good.
Thank you. So I think, yes, you have another question?
Can you please first introduce yourself and proceed with the question?
Thank you so much for the explanation, Associate Professor Che Azura. Let me introduce myself. My name is Anindya Chandra Faiza. I'm from Master of Biomedical Engineering. From my undergraduate thesis, I am research about cellulose nanofiber extracted from oil palm trunk, but I haven't explored about in tissue engineering. How can cellulose nanofiber extracted from oil palm trunk or oil palm can be utilized as a green biomaterial for scaffold fabrication, especially in tissue engineering? I think that's all. Thank you.
Okay, so thank you so much for your question. So I think you created already the fabricate the cellulose nanofibers.
Yes.
Using oil palm.
Using oil palm trunk.
Okay. So your research until which stage?
Until
characterization. How about cell material interaction?
Not until the cell material correlation, because the application I am using it for the sensor, FA sensor.
Okay. So I think basically you have already the basic data apart from characterization. Maybe you can look in terms of the toxicity and try to like make a cell tissue interaction. But you need to focus on, let's say for the cellulose nanofibers, which area are you would like to focus on the nerve? Then you can put cells from the nerve, whether they're growing or not. Because for nerve you need to make it conductive. But maybe if you focusing on other type of area, maybe bone, so then you can just put a type of cell lines for the bone and look how the cells basically on your material. Because that one is it nano?
Nano.
Yeah, okay. And then you can do also a lot of adjustment of your nanofiber cellulose.
Is it possible to make it as a scaffold? Because
yes,
my research paper is.
Yes. Okay, thank you.
Okay, thank you. Another challenge for the.
I think we have one question, right? From the chat. Are there any 3D printing machines in Malaysia that use hydroxyapatite material to fabricate bone scaffold? So far, we have been used dipping method in which a PLA-based bone scaffold design is immersed into HA. So in terms of 3D printing, I have my friends that having 3D printer, but I think he also didn't doing hydroxyapatite yet. Yeah. But as I mentioned, last month I have 2 days in Beijing and we went to Tsinghua University. So Tsinghua University, they have this 10th level of innovation center. So basically they have more than 15 3D printer for medical application. So maybe I can in touch with them. So maybe we can have a look if we can also using our hydroxyapatite to work with them.
Mm-hmm. Yeah, because here hydroxyapatite is the ceramic, right? So in terms of the temperature needed for it to be, structured into a certain function, it's quite a challenging one. All right. So we still have a time here, and we still also have our dearest guest, which flew all the way from Malaysia. So anyone want to ask any question, please? Is there any more question? No? Okay, maybe one question from me, if I may. In terms of the AI itself, like, can you elaborate more which part of the AI is potential for us, the material scientists, to develop further? I mean, is it only for the design one or even for, like, because what I know is nowadays we do the modeling one, right? So how is the AI can help us in terms of modifying the material itself?
Okay, so as I mentioned, the first one is focusing on the optimization before we start to fabricate our scaffold. And the other thing is, of course, now if we have our scaffold, we just test for the cell material interaction only for our optimized scaffold. But what happens to the non-optimized? And in terms of like cell interaction, usually we just look at 0 day, 3 days. But what is happening between 0 and 3 days?
I see. So like the monitoring
Yes,
one.
monitoring one.
I see. Okay. All right, that's a very interesting one. Okay. Another question maybe from the online participant as well as for the offline participants. Is there? No? And for that, I think we can conclude today's session with Dr. Chacha. And thank you very much for having us here. It's such a pleasure to meet you again here in person. And yeah, I think that's all for today's session with Dr. Chacha. Wassalamualaikum warahmatullahi wabarakatuh.
Feel free to email me. So maybe I think I will ask Dr. Intan to also put my email in the Zoom. So if you have anything, you can simply email me. Thank you.
Thank you.
Okay, thank you very much for Ms. Intan Firdausi and especially Professor Azrahani for that fascinating session.
We would now like to proceed with the presentation of a token of appreciation to our speakers. May we invite Dr. Siswanto to come forward to present the token of appreciation to Associate Professor C. Azrahani. To Dr. Siswanto, the floor is yours.
Okay, and now we move to our final plenary session for today. Plenary session 4. It is my pleasure to welcome back our moderator, Mr. Heri Trilaksana, Bachelor of Science, Master of Science, PhD.
Mr. Heri Trilaksana will introduce our first keynote speaker, Professor Pat Wheeler from the University of Nottingham. To Mr. Heri Trilaksana, the session is yours.
Good morning, everyone. While we are waiting for the preparation for the techniques, welcome to Professor Pat Wheeler from Nottingham University, and it takes your time because you just arrived. I know that's a bit frustrated flight from Jakarta to Surabaya with an hour delay. So just take your time. So we are just trying to make a brief introductions about and how long you've been collaborating with us in Alumni University, in particular physics department. I think from my recall that in 2022, that's the first coincidence. I do like to say that was the first coincidence when I tried to send an email to him, and then suddenly he replied in the less than 30 minutes, and he said that, okay, I'm on the way to Jakarta. What? And again, it happens again for the second in 2025. After the shift of these international conferences, then I just try to confirm that whether you're still available or not. Yes, that's on the way. I'm going to Jakarta. What kind of the coincidence for the second? But okay, that's grateful for us. We had Professor Pat Millers in this conference, and I would like to introduce him in brief, very brief, okay? So, Professor Pat Millers received PhD degree in electrical engineering and the matrix converters at the University of Bristol, England, 1993. Yes. And then he became the lecturer in Nottingham in 1996. I think it's about 30 years next year, yeah. And also it's currently researching power electronic converters, power converters and power system application, and also more electrical aircraft. From my memory, when I visited her laboratory, there's a Boeing aircraft, a very huge propeller there sitting there around, and then what? Okay, that's quite interesting. And then now he's actually the head department, or no? I wasn't. Okay. All right. So the next time and screen is yours, Pat. I think that's enough, right? Yep. Excellent.
Okay. Right. Thank you very much for being here. It's been a little bit of a rush because my flight from Jakarta got delayed a little bit.
And also don't forget, we do have a lot of participants on the camera because online. Okay?
So where do you want me to be?
You can run smoothly here, or also you can, because I think it's too close to your screen, right? It's better for you to stand here so you can quite twist it, right? Excellent.
Okay, I'll stand over here.
Yeah, that's fine.
See what's going on as well. That's good. Right. So I'm from the University of Nottingham in the UK. If you don't know where Nottingham is, it's in the middle of England. So we are as far away from the sea as we can get on our small island. We're famous for two people. We're famous for somebody called Robin Hood. So you may have seen the films with Kevin Costner and people like that. And actually, Robin Hood would never have wanted to come to Nottingham because his enemy, the Sheriff of Nottingham, lives in Nottingham. And he would have been killed if he'd come to Nottingham. We still have a sheriff today. She's a lovely lady who wouldn't treat outlaws quite as badly. The other thing we're famous for is our soccer team, our football team, which is Nottingham Forest. Back in the 1980s, Nottingham Forest was the best football team in the whole of Europe. Since then, we have been down to the third tier, the third division of English football, and come all the way back up. And last year, we finished 6th in the top division, and we're back in Europe. So Brian Clough was one-time manager of that football club, and so he's another very famous person who we know very well. Now, I'm from the University of Nottingham, and within my faculty, we deal with a lot of technologies around sustainability. So we look at advanced materials and manufacturing. We look at healthcare technologies and well-being. We look at sustainable energy, I'll talk about today, sustainable cities and the environment, and sustainable transportation and mobility. So these are application areas for our technologies. And when I looked at this conference and looked at the topics of this conference, I realized just how much overlap there is between the work you do here and the work of this conference and those technologies that we have as the fundamental technologies that we are looking at and the applications we're looking at. So that's what we do. Now, I'm head of something called the Power Electronics, Machines and Control Research Institute. We have about 200 people and we do a lot of work in transportation, electrification and energy conversion. The one thing I realised when I joined the University of Nottingham 30 years ago is when we start looking at these application areas, it's not about one type of engineer or one type of scientist. We need lots of people with lots of different skills and lots of different ways of thinking about things and solving those problems. So yes, I'm an engineer, but I'm an engineer who works with a lot of other people to work in different application areas. That motorbike is one of the application areas, and I'll talk about that in a moment. So, in terms of who we are and what we do, I lead a group with about 25 professors, about 70 postdoctoral researchers, over 100 PhD students, and a number of visiting scholars, visiting PhD students or visiting professors at any one time. We have a lot of different underlying scientific research areas where we're looking at packaging, new materials, cooling methods, so thermal integration, lots of modelling methods, electromagnetic modelling, modulation theory comes in there, physics of failure, where we're characterising new materials and new methods and looking at how a device or a system will fail based on those materials. And then we apply those technologies in a range of application areas. So transportation and electrification is one area. Renewable energy and future electrical networks is another. Aerospace is very big for us, but we also work in areas like high energy physics applications. So we work with places like CERN in Europe and Los Alamos in the US, looking at particle accelerators and so on. We're also lucky in that the UK government and my university has invested in us. So we opened a new laboratory in March 2021, so nearly 5 years ago, where we've got big facilities. We've got over 5,000 square meters of laboratories, and we can work at power levels for propulsion systems up to about 5 megawatts. That building is not big enough, and you can't see it in that photograph, but next door we're building a new building looking at hydrogen technologies and the materials and technologies we need as we move into hydrogen as a way of storing energy for propulsion systems. So that's just looking at that building. The main photo there was taken before we moved in. I know that because the laboratory is tidy. There's no boxes, there's no equipment, everything is in its place. That only happens when a building is brand new or when it's about to be demolished. That motorbike is electric, and yes, I have ridden it down that lab. So within that building, we have 3 laboratories. We have the Power Electronics Laboratory, where we do a lot of work on the characterization of materials, the analysis of how we put those materials together, and the lifetime testing. So looking at why things like power supplies will fail. And they always fail not from an electrical problem, but from a materials and a fatigue problem. So all failures in electrical devices are always because of material properties, thermal properties, and fatigue. But also in there, we've got things like magnetic testing facilities. We've got a 3D X-ray place where we can do 3D X-rays of objects to see what's happening inside. and clean room facilities for building up test samples and so on. Our main laboratory is the middle one, where we have test facilities up to about 100 kilowatts. And that's where we do a lot of our work on electrical machines and drives. Speak about that in a few moments. And then we have the Wolston High Power Laboratory, where we can work at voltages up to 11,000 volts and power levels up to about 5 megawatts. So that's where we do testing on very large systems. Now, before we go any further, one of the problems we're trying to solve at the moment as society is the one of using fossil fuels. And most of us drive cars which use gasoline, petrol, diesel, and that's causing a problem for the planet. It's a very good time to be talking about that because, of course, COP30 begins next week in Brazil. The planet, most countries in the world are looking at the temperature rise of the planet and what we can do to reduce that temperature rise. Now, I like history, and at the moment, everyone thinks electric cars are a really good new idea. They're not a new idea. The first electric vehicle was recorded by a guy called Jedlik in Hungary in 1828, 200 years ago. And just think about that. 200 years ago was the first thing that looked a bit like an electric vehicle. I come from the UK, and in the UK we like to think we invented everything in the world. And so the history books in the UK quote Robert Anderson of Scotland with the first electrically powered carriage. He'd created an electric motor and he replaced the horse with that electric motor. If we then look at what happened next, by 1912, electric cars were replacing steam-powered cars. So the steam engine was at first replaced by electrical power and by electric vehicles. By 1928, all production of electric vehicles had finished because somebody called Ford had come along and he designed the Model T Ford, which was the first affordable gasoline petrol car. And that destroyed the electric car industry. If Ford had not come along and somebody had developed the electric car more fully, maybe we wouldn't have the problems we have today. We wouldn't be using so much oil. However, scientists and engineers of today now need to solve that problem that they did not solve 100 years ago. We've got to produce cars that have a good range and that are affordable. And so that's our goal today. When we look at that problem, it's not just about the cars themselves. In fact, it's not about the cars themselves. We can produce those today. I see them on the roads around the world. But the other thing we have to do is to get the energy, the clean electrical energy, to those cars to charge them up, and to the trucks and the buses and maybe even the aeroplanes. And so there's a big move into how do we store electrical energy, what materials, what systems do we need for that? It's a lot of electrochemistry, but also what are we going to do in terms of charging those cars and getting electrical energy, the places we can generate it, to the places where people actually want to charge their cars. And that energy problem is a bigger problem than the cars themselves. We've been used to using tankers to move gasoline and diesel around countries or across seas. Electrical energy requires a new way of thinking if we're going to do that same transmission of that electrical power to the places where we wanted to use it. And there's lots of different things we can think about. One area I work in is the idea of microgrids. So small electrical energy networks which have the ability to be autonomous or the ability to be part of a wider electrical system. So if we think of the electrical system on a boat, that's a cruise liner shown there, then that is a microgrid. It has an electrical system with generators, users, people charging their mobile phones, propulsion systems driving that boat forward through the water, and all of that is happening using electrical energy that is generated on board that ship. So boats or ships are very good examples of a microgrid system. And aeroplanes are the same. There's no wire connecting an aircraft to the ground, yet it has, in the case of a Boeing 787, a 1 megawatt electrical system. But we can use the same principles for homes, for houses. The example in the bottom right there are the energy homes at the University of Nottingham, where we have 8 houses that are fed with a DC low voltage microgrid. All the applications you use today, your TV, your mobile phone, your computer, all run on low voltage DC, yet we distribute electrical energy as a high voltage AC. Why do we do that? Because of history. So most things in our houses, lighting, entertainment, and so on, only require low voltage DC. It's only when we get things like air conditioning and heating that we actually need those higher powers that the high voltage gives us. And that's what we're demonstrating in those energy homes. So we have this concept of a microgrid. The other area I look at for microgrids is when we're looking at energy access, going to remote communities where they don't have a connection to the main electrical grid, and we can then connect batteries, maybe PV panels, maybe hydroelectric, to an electrical system to give them things like lighting and communications. One of the really interesting things that happens when you give a community electrical energy is people have more time to study and more time to learn. And the outcomes, particularly for women, are far better if those communities have access to electrical energy, because people have the time and the ability to study and to better themselves and to learn more about their environment and more about how they can live their lives in different ways. So energy access is an important area that this enables. During the pandemic, I actually did a project in a rural area where they didn't previously have a connection to the electricity grid. This wasn't really energy access for a community. This was energy access for a small agricultural site. It's actually a vineyard where they make wine in the hills in Chile. And traditionally, they've used a diesel generator. So they've taken gasoline and put that into an engine and generated electricity on the site. And we were trying to prove that with just 3 PV panels and a battery, we could power that vineyard from renewable energy, and they didn't need to transport gasoline to the site, and they didn't need to create that noise and that pollution. And it works. It's still working today with equipment we built during the pandemic. And you can see the equipment there on the bench. That's still working there today and still powering that vineyard. So just a little way in which we can make a difference. On a slightly larger scale, I mentioned the new building that my research institute has at the University of Nottingham. And we have a 5 megawatt supply from the electrical utility grid. Now, when I built this building, I phoned up the UK government agency and I said, we're opening this building. It was in the middle of the COVID pandemic, but we were opening the building. And they said, that's great news. That's really good to hear. And they said, but your building is net zero, isn't it? And I said, no, we're going to use lots of power from the grid. We've got test facilities, combined power of about 20 megawatts. And this was a problem because the government has net zero targets. So they did what governments do. They gave me some more money. Very nice of them to give me some more money. And they said, can you make that building a little bit more energy effective, a little bit closer to net zero? So we took our high power testing laboratory and we looked at how we could do that. And the way we can do that is we put solar PV on the roof. It's a big building, so we've got a lot of space to cover with solar PV panels. I've then got a 1 megawatt hour lithium rechargeable battery, and we've got a hydrogen electrolyzer, high pressure hydrogen storage, and a hydrogen fuel cell. So I can store 2 megawatt hours of energy. And we connected those together using a DC microgrid. So I've got the PV panels on the roof, I've got the hydrogen storage system, and I've got a battery energy storage system. Now, what's interesting about those two ways of storing energy, the battery system, if I want to increase the capacity, I have to buy a complete new battery system. So it doubles the cost. If I want to store more energy in hydrogen, I just need to buy some more storage bottles. Very low cost, because I already have the electrolyzer and I already have the fuel cell. Fuel cell technology, by the way, is fascinating. The materials and the processes and the efficiency they're now getting is great. Now, so the battery has a better performance in terms of efficiency. The hydrogen system has a better performance in terms of the cost of storing that energy. So we're going to compare how those two things perform over the next 5 years and see which one is better in which different way. Now, when we installed this on the building, I went on TV in the UK to explain what we were doing, to explain the future of this technology and why this was a good idea. 2 people phoned me up at 9 o'clock the next morning. This went out on the news in the evening. One was a company called Amazon. You've heard of Amazon? Yeah. Amazon were interested in this because they wanted to put PV panels on top of their warehouses and to run all their delivery vans from electrical energy. But they need to charge the vans at night, not during the day. So they can generate lots of electricity during the day, store it in hydrogen, that was their interest, and use either the hydrogen or the electricity to charge the vans at night. So Amazon are now installing this technology in the UK. They're not interested in saving money. They're interested in publicity. So their interest is actually in using hydrogen and using green energy and using electric and hydrogen vehicles for delivery. More people will buy things from Amazon. It's not about the cost of energy. The other people who phoned me up was the local energy utility company who were very unhappy that I was connecting all this equipment to their network without their permission. We had a license to do it, but they didn't like that. Okay, when I came into the room a few minutes ago, you were talking about AI, artificial intelligence. I happen to have some slides about AI and how this affects our energy system. When we look at energy systems, renewable energy is intermittent. the wind doesn't always blow, the sun doesn't always shine, seems to here, but certainly in the UK, it does not. We've got this increase in demand, we've got electric vehicles coming in, and all the time we're trying to reduce cost and reduce carbon emissions. So we've got a big problem in how to develop our systems. One of the things we've been looking at is how we model those systems. So we're looking at digital twins on those electrical systems. So we're looking at the multiple vectors of renewable energy, storage systems, thermal energy systems, and trying to come up with a way of modeling the energy systems we use and we rely on in our homes and in our industries. And when we do that, when we start looking at this digital twinning, we've used it in a number of different areas. We're looking at it for scheduling, we're looking at it for modelling the energy markets. The price of energy is dynamic in the UK. The cost you pay, the price you pay for electricity changes depending on demand. We're looking at physical devices. We're looking at what we call third-party services. When you have an electrical energy system, you get extra payments if you can offer services like black start if there's been a power cut and so on. And we want to try and come up with a real-time modelling of that energy system that takes account of the scheduling, the predicted use, the forecasting in terms of wind and sun, and all the other parameters that we don't know within that system. And when we start looking at smart grids and we start looking at monitoring our use of energy, we start needing to have lots of sensors. We need to know what users are doing. We need to have smart meters in homes and in businesses so that minute by minute we know what's happening in our systems. But just sensing and controlling things is not enough. We need to have that information quickly. And this is where communications comes in. On your mobile phones, if you look at the top, you'll all see a little thing that says 4G or 5G. I notice here it's 5G. That gives us real-time communications. So we've got the Internet of Things, all these sensors and control we have in our electrical systems. We have real-time communications to the 5G communications. And so we've got lots of information, happening very quickly, lots of different and information coming to us very rapidly. Now, if we then put a human being, we then put a person in that control loop, the human being fails. We can't process the information quickly enough. We can cope with uncertainty. We're very good at that, but we're not very good at processing information quickly. And that's where AI comes in. It can be used to process information despite the uncertainty we have in those systems. If we knew everything about the system, we don't need artificial intelligence. If it's a deterministic system where everything is known and predictable, you don't need artificial intelligence because there's nothing to predict. When we need it is when things are slightly unpredictable. So what we're not allowed to do in the UK is to start taking our AI tools and applying them to the utility grid that supplies everybody in the country. So what we do is we emulate that grid using hardware in the loop techniques and in this case, looking at real-time voltage stability. So in this particular example, we've got the grid modeled by hardware in the loop. We've got real-time voltage stability enhancement as our goal, and we've embedded AI controllers in order to do that. Now, I don't believe results until I see some practical results coming from equipment. I'm an engineer, and in engineering, it's practical results that we always like to see. And this is a practical result. So the purple line there is the voltage of the system without any control. So this is an electrical system with renewable energy on the grid working without control. And you can see that that voltage is varying quite a lot. The dotted line you can see at 0.983 is the prescribed threshold. So that is the point in which the voltage is considered to be good. So my voltage needs to be above that. And as you can see, with the uncontrolled system, the voltage is too low. So we gave this problem to a very experienced power system design engineer who spent months working on a controller, and his best control was the blue line you can see. It doesn't work all the time. The voltage is still going below that line. And he said, that's fine. That's what we would expect. There's unpredictable things happening in the electrical system, and so my controller is going to fail sometimes. We then designed an AI-driven algorithm, so using artificial intelligence, and we got the bed result. And you'll notice that that stays above the line. The AI algorithm is better at coping with the things happening in the system that are not predictable. So the wind decreasing, even though the forecast was for the wind to stay constant, the wind might decrease. And the system has coped with that because it can react more quickly to things that are not predicted within that system. So just an example of how we've used AI, in this case, as part of a control system to cope with that unpredictability, to cope with the things that we don't know. And it's done a very good job. Now, if we go back hundreds or thousands of years, people lived near the source of energy. So people would live near a river if they wanted to mill corn for flour, because the river provided that energy. Today we live in cities and the energy tends to be coming from elsewhere. So we need to be able to move energy from where it's generated to where we want to use it. Traditionally, we've always done that with an AC system. Why? Because an AC system can use transformers to change the voltage. If I increase the voltage, I reduce the current, and I get lower losses when I transmit that energy over a large distance. We've done it like that for about 150 years. But something's changed. We can now convert the voltage for DC systems using power electronics. I'm a professor of power electronics, so this is the technology that I understand and I can do. Now, power electronics is more expensive than transformers. Okay, so we can use that power supply, that power electronic technology, but it's going to be more expensive. But when we transmit electrical energy over large distances, we find that a DC system is cheaper to install because the cabling and the infrastructure are going to cost less. So the picture in the top left there shows the equivalence of a DC overhead line system and an AC overhead line system for the same power. There is obviously less material and fewer conductors in the DC system. And what we find is that depending on the distance we want to transmit that electrical energy, then there's a break-even point. Usually about 800 kilometers over land. Not much interest to you here in Indonesia, but maybe in some parts of the world. Or 50 kilometers if we're taking electrical energy under the sea. Now, we'll come on to why we might want to do that. One of the things we looked at in Europe was that there's different places around Europe where we can generate electrical energy in different ways. So on the coastline of Europe, we might want to generate electrical energy using wind power. Up in the northern Europe, we might want to generate electrical engineering using hydroelectric. There's some questions about whether hydroelectric is environmentally friendly or sustainable, but we might want to do that. And in the south of Europe, there's great potential for solar power, and even going down into North Africa. And so the idea was to connect not just cities together using DC, but to connect countries together. Now, I know in Indonesia you have lots of islands. So think if you connected all the islands of Indonesia together with a DC network so that you can trade electrical energy between the islands, depending on who's generating more energy and who can generate energy in the most sustainable way. Okay, in Europe, we're just looking at connecting various countries of Europe together. And so the idea is that we have lots of offshore wind, lots of PV, lots of different countries, and we have this backbone of a DC system. The vision was to have a European supergrid by 2040. That was the vision in 2010. Since then, we've had Brexit, where the UK has left the European community. We have a big problem in terms of the politics as well as the cost. But we have made a start on this. And you'll notice that the start of this DC system has always been under the sea, connecting different parts of Europe together using the sea as the easy place to put the cables. Why has that happened? Well, the land in Europe is very densely populated. It's very difficult to build new electrical systems on the land. The sea is not so populated, and it's very easy to lie cables on the seabed, but very expensive, which is why it's DC, not AC. So we've already connected the UK to France, to Belgium, to Ireland, and to Norway. And then you can see various other connections there between Sweden and Finland and mainland Europe. So we're now able to transmit electrical energy between those countries so that we can generate electrical energy in the most sustainable way. And that's a very good thing to be able to do. When we do that, I don't know if you can see that system on the screen there, but we could put wind farms out in our sea. The sea off the coast of England is very shallow. The North Sea is a very shallow sea. And we can then connect, or we can then collect that electrical energy, transmit it onto land, about 160 kilometers typically, using a DC cable. And then we have to convert it back from DC to AC to feed into our electrical system. Every time we convert electrical energy from AC to DC, high powers, we have to use power electronics. It's a good time to be a professor of power electronics. That conversion is exactly the same as the power supply for your laptop or your mobile phone does, but rather than doing it at tens or hundreds of watts, it's doing it at tens or hundreds of megawatts. So same idea, just a lot higher power. And we've been doing this for a long time. The first time this was done was almost 60 years ago to get power transmitted from England to France. And the station for that actually still exists. It still works. And it's the picture on the left there. The problem is it takes up a lot of space. And in England, space is expensive. Land is very expensive, particularly in the areas where you want to do this. So we've been looking at modern power electronic ways to actually make this smaller. And the building you see on the right is now being built, is how we would do that today. And that building is about the size of one building from the picture on the left. So we've reduced the site down to 10% of what was required 50 years ago. That's quite a big saving in space. We could do the same, by the way, for your laptop power supply, but it would be more expensive and you're not prepared to pay for it. So how are we doing that? I'm not going to give a power electronics lecture. I know you're not power electronics engineers, but we have lots of different ways in which we use power electronics to convert electrical energy and to make these systems work. And we get really nice complicated circuits like this one, where we're using the modern switching power electronics, using new devices. We've got a new material we've been using for the last 10 years called silicon carbide, which we've used to replace the traditional silicon devices. That means that we are operating far more efficiently, lower losses, and so on. So we're making things smaller and lighter using those technologies. Now, I mentioned cars at the beginning, and I mentioned the importance and the history of those. We've also been looking at aeroplanes. And why have we been looking at aircraft? Well, the aircraft industry contributes quite a lot to the greenhouse gases that we see. And it's a difficult problem to solve because aviation fuel works very well. I'm able to fly from London to Indonesia in a little bit over 12 hours, 2 aeroplanes. But it takes a lot of aviation fuel to do that. And so Europe likes roadmaps. The European Union loves roadmaps for technology. And this is the roadmap they have for the aircraft industry. So the top dotted red line is the line we would follow in terms of emissions. This is a million tons of carbon dioxide, but most of the emissions you get follow the same trend. And between 2010 and 2050, that would have doubled if we'd taken no action. The good news is that we started doing research in this area about 30 years ago. And we've already got known technologies that are making aeroplanes lighter and more fuel efficient. So we're making the aircraft structures out of carbon fiber rather than out of metal. And that's making the aircraft lighter. We're making the engines more efficient, and that's helping. But also things like operations, where we have modelling techniques so that air traffic control can control when aircraft take off and when they land, and how fast they fly to maximise efficiency. By the way, the easiest way to improve the efficiency of an aircraft is to go more slowly. If you've ever studied aerodynamics, that will be obvious to you. So the green technologies are already known, but it's not enough. We're still working on additional technologies, hydrogen, biofuels, and so on, because the goal is that by 2050, we will be at 50% of the emissions of 2010, despite the fact that the number of aircraft will have doubled. So we're looking for an industry that's going to go up by a factor of 2, and we're going to halve the emissions from that industry. Now, this is a big problem. Today we are sitting here in 2025. The average lifetime of an aeroplane is 25 years. The aeroplanes that are coming into service today will still be flying in 2050. So the aeroplanes we bring into service over the next 10 or 15 years haven't got to be just 50% better, they've got to be even better, even more fuel efficient than that. So we have to find these ways of using hydrogen and electricity to drive these aircraft in order that we meet that goal. Europe, by the way, is putting a lot of money into this. We're part of a €4 billion program, so about 3.8 billion being spent on trying to achieve the technologies needed for this goal. Now, we look at how that might span out and look at the different classes of aircraft. Today, we can already fly on a little one-person, two-person aircraft, which has got electric motors on the wing. We can do that today. When we look at the aeroplane that brought me to Indonesia, I need electrical power of about 10 megawatts, not a few tens of kilowatts. And to do that is going to take a lot longer. Now, in my labs, we've been looking at this problem. And we've been building electrical motors using the latest materials, the latest magnetic properties, and so on. And what we found is that we're building demonstrators, and those demonstrators are getting higher and higher in power. The largest we've built is 4 megawatts. So you've got that timeline of these new aeroplanes coming into service, and you've got that timeline of the demonstrators we've built over the last 10 years in our lab. And you'll see that the gap between the demonstrators and the aircraft is getting longer and longer in time. Now that is essential. The larger the aircraft, the longer it takes to develop it. The longer it takes to make sure that aircraft is going to be safe. And when you're looking at a large aircraft that might carry 300 passengers across an ocean, it takes between 20 and 25 years to develop that new aircraft. If I don't have the technology demonstrated today, it won't go on an aeroplane in 2045. So we have to be demonstrating that technology today if it's going to be flying in the future. So, very good way to think about it. I also like the diagram on the right-hand side there. It shows that we can make the electrical drive systems today that have the right lifetime, that have the right efficiency. Power density is nearly where we want it. Volumetric density, not quite so good, but we're getting there. But they cost too much money. And so the one thing we have to do with the materials and the manufacturing is to make it lower in cost and therefore meet the requirements of those systems. So we're looking at various ways in which we might create the propulsion systems of future aircraft. But the basics is we need some energy storage. That might be a battery system, that might be a hydrogen fuel cell. But we need to be able to store energy. Gasoline or aviation fuel is very good at storing a lot of energy in a small space. When we do that with a battery, at the moment, those batteries are too big. We do it with liquid hydrogen, that might work. We then need to convert that electrical energy into an electrical motor that will spin the propellers on the aircraft. And that's the trend that we're looking at today, is to put electrical machines on the wings of the aircraft. They will be smaller and lighter than the gas turbines are today, so I get less drag on my aircraft, so I get a higher efficiency. And then we're looking at a power electronic converter to drive those electrical machines and to interface to the energy storage. It might be a battery as shown here, it might be a hydrogen fuel cell. Now, to make this happen, lots of technologies have to come together. We're looking at new low loss magnetic materials. So different steels that we might use in an electrical motor that have different magnetic properties. Maybe even materials that are printed in 3D printing or additive manufacturing, as they like to call it. We're looking at cooling techniques. That problem of getting the heat from the inefficiencies from where it's generated to somewhere where we can dissipate it. We're looking at integration. How do we integrate everything together in that propulsion system? That's not a new idea. If you look inside your mobile phone, you take your mobile phone apart, you'll find that the heatsink to cool down the electronics in your mobile phone is the back of the phone, it's the glass at the back of the phone. They integrated the thermal system into the aesthetics of the mobile phone. We can do the same with big, large systems as well. We just need the materials and the properties to do that. So we're looking at materials, we're looking at topologies, we're looking at manufacturing, we're looking at thermal design. All those technologies have to come together if we're going to do this job. And that leads us into looking at new technologies and when they might be applied. So the bottom scale here is technology readiness. So on the left-hand side, technology readiness level scale 1 is when a professor has had a good idea. Those of you who do research as PhDs will always know that your professors have good ideas. They might be good, they might not. Okay, so that's technology readiness level 1. Someone's had a good idea. Technology readiness level 9 is like your mobile phone. It's when you've got that idea has been proven and it's a product you can go and buy. Okay? And that's at the right-hand side of that screen. So the new magnetic properties are currently at technology readiness levels 7 and 8. We can go and buy them, we can go and use them. They're still improving, but they're there. It's quite low down in that chart because their impact is significant, but not very, very large. Superconductivity is a great idea. It's going to have a high impact. It's going to make things smaller and lighter, but it's not ready as a technology today. We're beginning to see it move, and technologies can move up this chart very quickly. Additive manufacturing is the same. It's got a lot of potential, but the technology needs to be developed. Thermal materials are somewhat further up. The new thermal materials we're seeing have better properties than previously. They're more controllable in terms of manufacturing and so on. And wide bandgap semiconductor devices using silicon carbide and gallium nitride materials in electrical semiconductors. It's going to have a massive impact on all electrical systems, and it's coming into use at the moment. In my labs, we like to build things. This is a demonstrator we built at 4 megawatts. So that 4 megawatt machine is enough to put on the wing of a regional aircraft and to fly between the cities of Europe or to fly between the cities of Indonesia with maybe 100, 120 passengers on your aircraft. So we've been able to put these new materials into an electrical machine and to demonstrate that that works in practice. One thing people always ask us is how small are things going to be in the future? And I always think that this is usually business people and commercial people thinking that scientists and engineers can somehow predict the future, that we somehow know what is going to happen in 10 years' time. And actually, what we know is what we've developed today. We know what technologies we would like to develop in the future, and we know what's happened in the past. So we can do some prediction based on looking at those trajectories. And this is just looking at the power density of electrical machines and how we can make them smaller and lighter using those technologies. We can do exactly the same for power electronics. I mentioned before that the power supply for your laptop or your mobile phone could be a lot smaller if you were prepared to pay for it being smaller. If we do a lot of integration of that power supply, it would be so small it would fit inside your phone or inside your computer. And that's something that we can do. We can make the power electronics, we can make your power supply really small and really light. The materials for doing that, the techniques for doing that are very expensive at the moment, but we can do that. So during the pandemic, I was asked to look at this problem and tell people how small can we make a power supply. And this was the chart I came up with. The answer was, it depends. If it's standalone, like your power supply to charge your computer or your mobile phone, it's going to get a little bit smaller. If we integrate it inside your computer, we can make it a lot smaller. And that's that blue line that disappears into the future. And the reason for that is that integration is something that allows us to have miniaturization. But it's expensive. So it depends what you're prepared to pay. I don't think laptop power supplies and phone power supplies are going to get very much smaller because we're not prepared to pay the extra cost. So just to finish, I thought I'd look at an example. I started talking about electric cars, and we work with a lot of different companies who work in making electric cars, buses, lorries, trains, but they're all very careful about their technology. They won't let me travel around the world to talk to you about their technology. However, I do run a race team in the university, and we do look at electric transportation, and we look at it using a very powerful big motorbike. So this is being built by students at my university, built 4 or 5 of these, and we're looking at building electric superbikes to go racing. That photo was taken when we won the European Championship a few years ago, and that smoke is not exhaust, that smoke is the rider burning out the back tyre. So maybe not perfectly environmentally friendly. So this motorbike is capable of speeds up to 320 kilometers an hour. We currently hold 5 world records for straight line speed, but the bike is designed to go round a racetrack. It has 200 kilowatts at the back wheel. Your car has about 30. So this is a powerful bike. And it's faster around a Formula 1 racetrack than a BMW Superbike. Why BMW Superbike? Just because our rider rides both our bike and BMW bikes. And that's not me riding the bike, that's a professional rider. I may have ridden it, but I can't race. I'm not very good at that. So why did we go racing? Well, it's exciting for the students to start with, but it's great for promoting electrical vehicle technology. If we want to raise awareness of the new technology, you need to make it exciting. Then you end up on social media and on TV. When you go racing, you can also push the boundaries of technology. We had a PhD student who designed a new electric motor for the motorbike for his PhD. He finished taking his results on a Friday afternoon, and we were racing on that bike on the Saturday with his motor on that motorbike. So we can insert new technology very, very quickly. It doesn't matter if it fails when you go racing. That's racing for you. Okay, if you're going to build 1 million cars, you need to get the technology right first time. If you're going to go racing, you can test new ideas and new ways of doing things. The other thing I like to do is not to make things easy. So the first time we went racing at the Isle of Man. The Isle of Man is a small island off the coast of England, and they close the roads for 2 weeks each year. They've been doing this for 125 years, and you race motorbikes around that island. And when you do that, you find that it's a very, very tough place to go racing bikes, a very exciting place to generate that new technology and to demonstrate it. As well as doing this with motorbikes, we've also been doing work with solar car racing and with something called Formula Student. The world of solar car racing is a great one. There's lots of new technologies, lots of materials going into the PV panels, into the motors, and into the structures of those cars. This is the car we've built in Nottingham. That is a rendering of that vehicle, but it looks almost exactly the same as that in reality. Formula Student, again, is an electric race series where people are putting these vehicles together. So, lots of things we can do with our students to make life very exciting in terms of demonstrating the technology. So, what I'm hoping you've got from that talk is that transportation electrification is happening, technology development is essential, materials are essential. We're looking at new materials for hydrogen fuel cells, new materials for batteries, new chemistries for batteries, as well as for the vehicles themselves. Electrical machine technology is key, but electrical energy storage systems have to improve, and our electrical power networks will require significant investment if this is going to work out. So, thank you very much for listening. I hope you've all found something interesting in my presentation, and thank you ever so much.
Thank you, Brad. Just have a seat. We will have a question and answer. Please raise your hand if you want to complete your questions. Students, teachers, yeah. Okay, one from Brian.
Okay.
Thank you. Introduce yourself, mention your name.
Thank you, Mr. Patwiller. My name Alif from, I'm a basic student. I have two questions. My first question, as we know, electric cars are starting to become more popular in Indonesia. It is said that electric cars support renewable energy. However, if Indonesia still has many environmentally unfriendly power plants, such as coal, oil combustion, and other, can this be considered renewable energy? So what is the performance of EV that are starting to be replaced by hydrogen vehicle? Then my second question, battery are one of the most important thing in EV. As we know, most vehicles still use lithium battery, which are very sensitive to environmental condition. And the cost of replacing a battery almost same as the price of a new car. Is there a solution to this? Can solid-state battery be a solution to replace lithium-ion battery? Thank you.
Okay. Thank you very much for those questions. They're both excellent questions. I actually give a whole talk about battery technology sometimes and what's going to happen. I like history, as I said before, and battery technology, rechargeable battery technology, has evolved through time. Most of us are familiar with the lead-acid batteries in our car, and if you ever lift out the lead-acid battery in your conventional car, it's very heavy. If you replace that with a lithium battery of the same capacity, you'll find it's a lot smaller and lighter. And if you look through history, there's always been an evolution of the chemistry in rechargeable batteries. What's interesting is that we're overdue that change in battery chemistry. Now, you'll know when that happens because you'll charge your mobile phone once a week, not once a day, because new batteries will have a higher storage capability. What is that chemistry going to be? Well, if I knew the answer to that one, I would be very rich, probably as rich as Elon Musk. And I probably wouldn't necessarily be here to talk to you today. But I think something around sodium is likely to come out. There's a lot of promising things there with sodium, with solid state, but it depends who you ask and what money they're trying to get for research. So there are a lot of promising technologies for those batteries. The chemistry will change. It won't be lithium forever. Exactly what it will be, I'll leave that up to people who are going to have to invest a lot of money to make that happen. But I think sodium. So that's a very, very good question and something that hopefully will sort itself out. When we get that new chemistry, as I said, your mobile phone will need charging once per week, not once per day. And the whole problem with range of your electric vehicle compared to the weight will go away. Now, you mentioned cost. The purchase cost of a battery is the same as a car today. The problem is we've got used to buying cars which sit and do nothing for most of the time. If we can actually use public cars like the, I think there is it Grab you use for your taxi services, Uber in the UK, and the car is on the road all the time, it's the cost of the energy that's important, not the purchase cost. And I think we're going to see a move in the next 10 years away from private car ownership to using vehicles so that the vehicle is driving all the time, not sitting in a car park depreciating. The first question you asked was about the energy. And one of the things we see in Europe is the energy mix over the last 10 years has changed. We've gone from a lot of fossil fuels to a lot of renewable energy. I live 3 kilometers away from the last coal-fired power station in the United Kingdom, and it closed last year. Okay, so 2024, we closed the last of our coal-fired power stations. Countries can do that. We can change that energy mix. And we've gone to a lot of PV solar. We still use gas. We still have nuclear, and we have a lot of wind. So last summer, we went through 2 weeks in the UK where all our energy came from renewable sources. 20 years ago, we couldn't do that. We've had to invest lots in that energy transition. So I would encourage Indonesia to encourage people to move to electric vehicles and electric transportation, but at the same time, please force your government to move to renewable energy. And then you solve that problem.
That's a strong statement, right? So that's fine. Okay, so the next question is coming from the chat box. In your opinions, is that from Ari? Yeah. In your opinion, what type of smart grid technology has the greatest potential to be implemented in Indonesia or Southeast Asia within the next 5 years? I disagree with the extensive use of the electric vehicles that depends on large number of batteries. It's as it will inevitably increase nickel mining activities. All right, so there's
right. I'm going to take that as two.
After we push for the government, then you disagree with the idea, right?
Yeah, that's okay. What type of smart grid technology? Well, that's an interesting question. The communications, the measurement, and the real-time control are the big things about a smart grid. Knowing what's happening in the system in real time is very, very important. And I'll give an example. I spend a lot of time in Chile in South America, and they have a control center for their electricity grid. They have measurement and 5G communications in every substation and every generation station in the country. They know the capacity of every line, they know the temperature of every asset. When I visited that station, I saw an old-fashioned telephone on every operator's desk.
Twisting.
With a twisting dial. And I asked what they were for, and they were so that they could phone up the power stations to ask them to turn on and to turn off.
Wow.
So they missed part of that smart system in that there was a human being and a traditional telephone in that loop. So they could measure everything in real time, Internet of Things. They got the communications using the 5G communications, but they failed to get the smart control and the smart information going back. There was no reason for that telephone. They could have been using a 5G communication and it could be instant, but they weren't doing that yet. So to me, the critical thing with the smart grid is that you combine the information, the knowledge, the sensing, and the communication with real-time control. That you remove the human being from that control loop, and you definitely remove the analog telephone from that control loop. It's got to be a complete closed-loop system, because if you've got real-time information, you need to use that in real-time control. Now, the extensive use of if we're going to have good energy efficient transportation, we are going to use earth resources like nickel, like lithium for our batteries and so on in doing that. That is sort of inevitable. However, it does mean that we use the energy resources more efficiently. I can build the electrical drivetrain for an electric vehicle with an efficiency of 97, 98% if I want to. So we can get very efficient systems. What we have to also do is to think about the life cycle of those materials. How we minimize the amount of mining we need to do by making sure that when we design systems, we can reuse those systems. So how do I design a battery with a longer lifetime? How do I design that battery so that its second life in maybe a less demanding application is easy and cheap to implement? And how do I design it so that I can recycle those materials and get them back and reuse them in a future battery? So yes, we are going to have to mine lithium, nickel, various other rare earth materials. But if once I've mined them, I can reuse the systems that they're in, and I can recycle those systems when they get to the end of life. So my battery has a 10-year initial life, maybe a 10-year second life, but it's also been designed so that I can get that nickel back at the end and build a new battery out of it, and I can do that efficiently and cost effectively. Then I would argue that rather than mining new materials in the future, I should be recycling those materials out of those systems. But we have to think about that when we do the initial design, not when we got to the end of life.
Yeah, that's quite makes sense. All right, any other questions? No? All right, let me give a pause to Professor Pat for the nice sharing and the knowledge, and we are going to be ready for the lunch break and then continuing with the parallel session. Okay, I hand it over to the website.
Can I just say thank you very much for inviting me to speak? It's fantastic I can be here today. And I notice I'm wearing the same shirt as you. So but thank you very much.
Yeah. And the next session is going to be the offer for the certificates to Professor Miller, who's going to be handed over. I will do.
We would like to proceed with the presentation of a token appreciation to our speaker. May we invite Dr. Iris to come forward to present the token of appreciation to Professor Miller.
Yes, the head of department. None? Okay, let's be Professor Siswato, you can do it. So that's the former department of department. Give me a second. Camera ready on. Cheers.
Thank you very much, Dr. Kevin Wirakana and Professor Pat Wheeler for concluding our plenary session with such a strong presentation.
And don't forget for students, because we have a special session for talking and sit and chat with Professor Pat Wheeler after 1:30. Okay, ready and see you in the special room we already organized. Bye for now.
Okay, ladies and gentlemen, we have now concluded all four plenary sessions. In a few moments, we will begin the parallel sessions, which will run for 1:10 p.m. until 4:55 p.m. Please note that this session will be held in a hybrid format. And after this, we will have a long break for 20 minutes, started from now until 1:10 p.m.
Thank you. So the file was very large, so I wanted to
Here at Faculty of Science and Technology, Universitas Airlangga, the sessions are divided into 5 rooms. Please check your conference guide for your designated room. The rooms are hosted by Room 1, Dr. Prihartini Widianti, Master of Health Science. Room 2, Osmalina Nur Rahma, Bachelor of Engineering, Master of Science. Room 3, Dr. Riris Rolaningtyas, Bachelor of Engineering, Master of Engineering. Room 4, Ercisario Edo Yunata, Bachelor of Science, Master of Science, PhD. And Room 5, Erwin Sutanto, Bachelor of Engineering, Master of Science.
For participants joining us online, you can access the parallel session through the links provided on the conference website or in your registration email. We will now have a break from 12:50 to 1:10 p.m. The parallel session will begin promptly at 1:10 p.m. Thank you.
Your bank account.
Ini kok saya ganti gitu
Kenapa?
namanya?
Monggo jenengan ganti ini. Nah, monggo diganti.
Where now the transition to renewable energy, the demand for functional energy converting, which they drive the demand for functional energy converting, the efficiency of the perovskite-based solar cell was improved dramatically from 3.8% in 2009 to 20.7% in 2023. Barium titanate is one of the key material in this field. A model piezoelectric can wash tuned with cation doping such as Fa, Co, Cu, Al, Sn, and Ne. In figure 1 has tetragonal barium titanate structure showing with lattice parameter E equal B not C and small Te displacement along the axis. Before exploring the fun effect, BAT3 must accurately reproduce experimental structure. That's why we use computational study using density functional theory. DFT often show deviation from experimental structure because depend on just exchange relation and pseudopotential. This research compares 6 combination and pseudopotential combination to identify lattice parameter and bulk modulus based experiment. The 6 combination is in table 1. To make sure a model is reliable, we follow a systematic workflow.
In our research workflow consists of 5 steps. In the first step is structure preparation. In the structure preparation, we will want to build our model. In this model, that is the tetragonal Ba3 primitive cell model. To build this model, we need the experimental value. That's the lattice parameter and atomic position for experimental data. In the table 2, we can see the experimental Ba3 lattice parameter and atomic position. In this table, we can see the lattice parameter in x direction equal to the lattice parameter in y direction equal to 4. And we can see the lattice parameter in z direction equal to 4.024. And another parameter is the atomic position. In this parameter, we get the information, the position of the coordinate of atom in the crystal structure. Now, after we can build this model, we want to use this model to convergent test. In convergent test, we have the purpose. That is to determine the optimal DFT parameter, such as the energy cut wave function, energy cut throw, and key point mass. When this parameter will convergent, this parameter will convergent when the change of energy less than 2 milli-electron volt. In the table 3, we can see our result of convergent test. In table 3, we can see the key point we use is 6 times 6 times 6, and energy cut wave function we use is 85 Reinberg, and energy cut throw we use is 880 Reinberg. Now, after we get the optimized DFT parameter, we will use this parameter to optimize the structure. Now, in this step, we will optimize the structure using the exchange correlation pseudo-potential combination. We can see in the table 4, that is the 6th combination exchange correlation pseudo-potential we use in this research. Now, the purpose in this step is to determine the equilibrium lattice parameter and atomic position for each pseudo-potential and exchange correlation. Now, after we get the optimal structure, we want to calculate the bulk modulus. In DFT calculation, to calculate the bulk modulus, we first give the distortion in crystal structure. In our model only have 6 variants of distortion. That is the D11, D33, D44, D66, D12, and D13. As we know, after this crystal structure get this distortion, the crystal change the form. Now, after the crystal structure have changed the form, the lattice parameter on the crystal structure will change. The change of lattice parameter in the crystal structure can be formulated by R action equal to R times D. When the R action is the lattice parameter after get the distortion, R is the lattice parameter before get the distortion, and D is the distortion. Now, the D will be substituted by D11, D33, D44, D66, D12, and D13. Now, after we get the structure, after get the distortion, we want to calculate the total energy in the system. Why? We want to get the elastic constant in the from this equation. Why we want to calculate when to get the elastic constant? We want to calculate the bulk modulus. In the equation 7, we can see how to calculate bulk modulus. In this equation, we can see the bulk modulus can we get after we know the constanta elastic. Now we have been get the constanta elastic. Now we want to evaluate this model. Why we want evaluate this model? We want to identify the exchange correlation for the pseudo potential combination best matching with experimental data. Now the one parameter one we use to evaluate this model is the lattice parameter. In the table 4, we can see the percentage error, the lattice parameter, and bulk modulus relative to experiment. In this table, we can see we have 3 base models. The first is PBE rel KJPO and PBE rel KJUS. Have good accuracy with 0% error at calculate the lattice parameter in X direction and Z direction. Now we have another exchange correlation, that is the PBE RR KJUS. In calculate the lattice parameter in X direction and Z direction have accurate only less than 1% percentage error. Now after we get the 3 base model, we want to calculate 3 base model. We want use this. We will use 3 base model to calculate another parameter. That is the bulk modulus. In calculate bulk modulus, in the table 4, we can see the percentage error of lattice parameter and bulk modulus relative to experiment. Before we get the 3 base model, after we calculate the base modulus, we only have 1 base model. That is the PBE RR KJUS. Because in calculate the bulk modulus only have 30.4% percentage error. Next.
So the conclusion from the comparison of 6 exchange correlation and pseudo potential combination for base lattice parameter PBE plus rel KJPO, PBE plus rel RR KJUS, and PBE RR KJUS because lattice parameter error below 1%. And base bulk modulus, PBE RR KJUS gave the small bulk modulus deviation and the best overall agreement with experiment. So PBE plus RR KJUS choose the reference for future state because PBE is more suitable for solid state system and remaining consistent under structural deformation. This combination is stable and representative baseline for exploring local metal dopan effect on PaTO3 atau tetanan piezoelectric. So this research funded by the expertise-based research grant from Institute of Technology Sumatera, thanks to the Research Center for Quantum Engineering Design for the support, all simulation were carried out using the Riven cluster facility. So that is all we would like to do present. If there are any shortcomings, we sincerely apologize. I will return the session to the moderator. Thank you.
Okay, thank you very much for your insightful and informative presentation. We truly appreciate and acknowledge perspective you have shared with us. Okay, right now we open the floor of the question. If anyone has a question, please raise the hand. Okay, please. Any question? Okay, I have a question for you. because I have concern research for validity panel. In your presentation, in your explanation, you determine determination for the lattice constant A, B, and C. Yeah, lattice parameter. In this study, what method we use to calculate the lattice parameter?
Okay, thank you, sir. What method to calculate lattice parameter? Okay. To calculate lattice parameter in our study is using DFT calculation, supported by quantum espresso. In experimental value, if we have solid structure have form like crystal. In experimental value, we have the lattice parameter in experiment. Now we want to calculate using mathematical model. That is the DFT calculation. Now after that, we want to comparing the lattice parameter after calculation with mathematical model. Kita compare with experimental value. That's
okay. The characteristic values of the lattice parameter of variability panel, A, B, C, lattice constant. You have compared with the reference secondary opinion the values of A, B, C to define the structure, crystalline structure of variability panel. In this study, we define the structure tetragonal or rhombohedral. Tetragonal. Tetragonal, we can define tetragonal structure, crystalline structure from the lattice constant. You have compared the value with the reference about the sanitation. Ya. Hasilnya itu ya nggak apa-apa kita pakai bahasa. Selama ini saya concern di variability kita. Dia adalah piezoelectric material. Okay, you can prepare it, you can synthesize by physical and chemical method, method solder preparation, solder preparation. So I found the lattice constant when I calculate with lattice scalar equation. No? In this study, saya tidak melihat hal itu. Nilai itu apakah sudah sesuai untuk karakteristik tetragonal? Jangan-jangan dia rhombohedral.
Boleh ke structure preparation. Untuk menjawabnya, untuk struktur tetragonal, kita punya karakteristiknya sendiri. Itu lattice parameter in sumbu x sumbu x sama dengan lattice parameter dalam sumbu y. Nah, tapi tidak sama dengan sumbu z. Jadi kayak kubus tapi ada kayak apa? Nah, kemudian kita setelah punya hasil secara eksperimen, nah itulah kalau dengan menggunakan quantum espresso nantinya kita nggak perlu mengerti lagi, kita nggak terlalu konsen lagi terhadap matematis yang di dalamnya. Jadi sudah ada di dalam software. Jadi di dalam quantum espresso juga ada berbagai macam sebagai overview, ada berbagai macam jenis metode matematika di dalamnya, seperti ada biasanya semi empiris, ada jenis dari exchange correlation juga, dan ada yang meta GGH, ada GGH, ada LDR. Jadi setiap jenis exchange correlation ini akan menghasilkan tingkat akurasi yang berbeda-beda juga. Gitu. Nah, untuk yang kami peroleh saat ini untuk membuktikan apakah lattice parameter yang sudah kita temukan ini sudah valid atau belum, kita lihat dari hasil yang kita dapat dari hasil eksperimen, yaitu apakah lattice parameter di dalam sumbu X sama sumbu Y yang sudah sama, dan sumbu Z-nya lebih besar daripada sumbu X dan sumbu Y.
Okay. One more question. What the meaning of the bulk modulus in this study? Your sample in solid phase or solid phase? Okay, this.
Apa sih arti dari bulk modulus? Jadi untuk arti dari bulk modulus ini kemampuan suatu benda untuk ditekan. Kemampuan suatu material.
No. I mean, what the physical meaning of the modulus bulk? Because bulk modulus is parameter intrinsic of the volume channel. This is a characteristic and not properties. You know, this is physical characteristic of blah blah blah. Mechanical, optical, or what?
Untuk yang di sini itu mechanical.
Yeah, good answer. Jadi modulus bulk itu adalah, tapi fase yang diuji bulk modulus itu biasanya untuk fase gas. Kalau dia fase padat itu adalah elastik modulus. Kalau dia fase cair, kita mencari antara incompressible material dengan material yang viscous, itu namanya shear modulus. Jadi any three type of the modulus. Ya, nah ini yang hati-hati. Kalau bulk itu untuk gas, biasanya kalau elastik modulus itu adalah fase padat, kalau shear modulus itu biasanya cair biasanya. Okay, thank you very much.
Terima kasih, Pak.
Give your host for presenter. Okay, for the next, I invite you, Mr. or Afiar Astuti Nova from ITERA. Okay. Bisa.
Sama kayak yang tadi. Sama kayak yang tadi. Jadi kalendernya sebetulnya jangan 5 menit ya.
10 minutes divided by 2 part, 10 minutes for presentation and 5 minutes for discussion. Okay, sorry, because tidak ada yang bertanya, jadi saya ya, tolong begini. We have 7 participants in this room. Okay, please go ahead.
Assalamualaikum warahmatullahi wabarakatuh. Thank you for coming to my presentation. Let me introduce myself. My name is Afiar Aulia Astuti, and I'm from Institut Teknologi Sumatera. Today I will be presenting to the result of my research is which is titled Identification of PD2+, a chosen site on biocard derived from plant oil was using FNCO calculation. The background is my research is plant oil was. Plant oil was contains lignocellulose, which can be processed into biocard through pyrolysis. Biocard has porous structure and active functional group such as hydroxyl and carboxyl, which enable it to bind heavy metal. Heavy metal, such as lead, are prone to contaminating household water, especially in areas near industrial zone. They evaluate the effectiveness of BIOCAR in binding PB plus. A BIOCAR model with well-defined active site is required to facilitate the identification of PB2+. Problem statement is BIOCAR contains different active sites, making the identification challenging and the most energetic. So variable site for PB2+ absorption remain unknown. This study aims to determine the energetically preferred absorption of PB2+ ions.
Orator, please.
And on plant oil was defined BIOCAR to computational method. The computational method, there are 5 workflows in this study. The 5 sets are 1 structure preparation. Will the plant oil BIOCAR structure model? Plant oil-based BIOCAR is respected by the C32H8, which is derived from empty fruit but bunch plum BIOCAR. BIOCAR possesses an aromatic ring from one with several oxygen containing functional groups such as hydroxyl, carboxyl, and carbonyl group. The absorption site consists of 10 sites with the PB2+ distant at the BIOCAR absorption site being 3 angstrom. Two structure optimization of plant-based BIOCAR structure. Software Gaussian method Hreffer and basis set 631 GDP for the CHO and line L2DZ for the PB2+. Obtain the optimized structure with the lowest energy. C. Check the spin multiplicity. The spin multiplicity check is applied to obtain the global state space. And 4. Calculate the absorption energy. Absorption energy at energy art equal a dot minus a BIOCAR plus a metal ions. The next 5, identification the absorption site. Obtain the absorption site with the lowest energy. Okay. The result and discussion in calculation and determination of the ground state of BIOCAR and the metal ions. Table 1, comparison of the relative energy of each system based on spin multiplicity. The energy comparison indicates that the BIOCAR PB2+ metal ion system exhibits its lowest energy at the single spin state. The spin state of the BIOCAR metal ion system is successful calculated in the singlet state, whereas the triplet state does not converge during the calculation. Therefore, the single spin state is used as the basis for calculating the metal ion absorption energy on the BIOCAR. Next, geometry optimization of the PB2+ ion on BIOCAR. The figure 3, geometry optimization of PB2+ absorption at 10 site on BIOCAR derived from plant oil wash. From the optimization absorption site, the BIOCAR PB2+ ion can bind to 5 different sites on the BIOCAR surface. This selected site in 2 2, 5, 6, 8, and 10. Represented and more stable and geometry this state configuration. The reason of the geometry optimization indicates that Pb2 plus ions can be absorbed at points different set of Bayesian model surface. The most stable interaction is found at the carbonyl group with an absorption energy of -7.72 electron volt and a distance of 1.9 angstrom. The heavily negative absorption energy indicates that the oxygen atom in the CO group acts as an electron donor toward the Pb2 plus ions. Therefore, the number of CO group is the Bayesian structure, so we consider to exchange its ability to detect heavy metal. In conclusion, this study successfully identifies the absorption site of Pb2 plus ions. The plant oil was based Bayesian using computational method. The carbonyl group is identified as the main active site, exhibit the most stable interaction with the absorption energy of -7.72 electron volt in the Pb2 plus absorption process and the biofilm surface derived from plant oil. Knowledge funded by the expertise-based research grant from the Direktorat Penelitian dan Pengabdian kepada Masyarakat, Direktorat Jenderal Riset dan Pengembangan Kementerian Pendidikan Tinggi, Sains dan Teknologi melalui hibah dosen pemula. Special thanks to Dr. Febstian Kusdi, PhD, and Research Center for Quantum Engineering Design for guidance the computational support. All simulations were carried out using Ribbon cluster facility. That's for me. Thank you.
Okay, thank you, Abia. Now we open the question. Is any question? Present? Hello? Roger? Any questions? My student, please. Oh, no comment. Why? Prof. Aminatul? Maybe? Okay. Okay. I have a question. I'm moderator.
Yeah.
But okay. What the goals? Identification of PB cation in this study. What the meaning, absorption site of Yoka derivative form on which using AB initial calculation. Okay. What are those? Yeah. Okay, please.
Tujuan saya di sini yaitu melihat situs mana pada struktur geokar itu yang memiliki situs yang paling negatif secara energi. Nah, ketika energi itu paling negatif, untuk kedepannya untuk mendesain suatu struktur jawaban mungkin bisa ditambahkan situs CO karena pada saya ini situs CO yang memiliki energi paling negatif.
Why CO? Mengapa harus CO?
Mengapa harus CO? Karena dari hasil kalkulasi CO ini menunjukkan memiliki energi paling negatif ketika dia berinteraksi dengan PB itu. PB 2.
Can you menunjukkan rumus kimianya? Ya, ketika diberikan bond, saya campur aja soalnya dia begini.
Untuk
ya, PB12 itu kation.
Yeah.
So, any CO kation orangnya. Kation. Okay. Combine PB and CO in the chemical formulation, you can CO PB12 kation. Oke. Iya kan? CO itu nanti akan di remove atau filler? Bagi filler ya. Ya, sebagai pengisi dari itu tadi. Iya.
Jadi CO itu dia bagian dari gugus fungsi.
Oh, functional group.
Ya.
You trace using by FIR, okay? FIR. Mana FTIR-nya, display FTIR? Ada? Oh, tidak ada. Oh, simulasi.
Iya, simulasi Gaussian number.
Oh, Gaussian. Tetapi saya kasih catatan, saya dan Prof. Ami ini adalah dosen material. Jadi untuk melihat gugus fungsi itu secara teoretikal kita punya yang namanya hasil uji FTIR. Kenapa harus FTIR? Karena dia sangat spesifikasi dari serapan itu hanya pada panjang gelombang infrared. Untuk melihat apa? Ya, serapannya itu apa?
Untuk yang
ya nanti di situ ada bonding terjadi melalui kation dan anion dalam bentuk vibrasi atau vibrage. Nah, kalau dia strong vibrage, ya dengan mode vibration apa? Misalnya stretching, bending, wagging, itu adalah karakteristik dari ikatan. Jadi misalnya ini CO, ya ikatan rangka. Ada juga CO ikatan yang dikira itu, ya itu pasti vibrasinya, getarannya pasti berbeda. Oke, ya itu sebagai masukan satu. Kalau kita begini, kalau kita hanya mengandalkan simulasi, itu kan aproksimasi. Sama dengan kalau saya katakan experimental result itu hanya digunakan sebagai data dengan banyak error, Berarti kalau kita ingin menjadikan itu satisfying datanya, berarti kita harus kalibrasi dengan teoritis. Jadi kalau hasil eksperimental dibandingkan, compare, sama-sama punya error. Nggak bisa hasil eksperimental, sama dengan hasil simulasi. Oke, itu masukkan aja. Jadi makanya nanti kalau ya, basic teorinya harus diungkap. Ya, oke. Makasih. Thank you very much. Kita lanjutkan. Ayu Tiarawati, please. Itera. Anwar, ya, oke. Bimbingan siapa ya? Ferdian. Ferdiannya datang. Oke, please.
Thank you for the opportunity. Let me introduce myself. My name is Ayu Tiarati from Research Center and Quantum Engineering Design at ICPIAM Universitas Airlangga. Today, I would like to present my research entitled is Evaluation of the Accuracy of Kopman's theorem approach in the calculation of ionization potential of simple magnetic component of a computational study. This is our table of content I would like to present in this session. First is introduction, second is computational model, third is result and discussion, fourth is conclusion and acknowledgement. I will begin with why is ionization potential important. Ionization potential is one of the parameters used to determine a molecule's ability to donate electron. The lower ionization potential, that means the easier molecule to transfer electron. That means the higher the antioxidant activity. The ionization potential is a important parameter in predicting the antioxidant activity of phenol derivative. According to previous studies, it is commonly calculated using density functional theory. However, despite its widespread use, the FT calculations are often computationally demanding. Kopman theorems provide a simple method for estimate ionization potential compared to the FT-based calculation. Kopman's theorem, which equates the ionization potential to the negative value of the orbital energy, has traditionally been applied to calculate ionization potential using the molecular orbital theory. Molecular orbital theory previews us with just an approximation, and the result of this approximation is not quantitatively reliable. So our problem statement is the Kopman's theorem approach accurate in calculation the ionization potential of phenolic derivative? Our research goal is evaluate of the accuracy of the Kopman's theorem approach in calculate the ionization potential of phenol derivative. This is our workflow. First is molecular model. We investigate 11 phenol derivative molecules where were classified into the two groups. The group 1 is molecule with only OH substituents. The group 2 is molecule with OH and CH3 substituents. You can see the base structure from the figure 1. This is the list of all molecules in group 1 that we study. There is any benzene, phenol, 1,2-dehydroxybenzene, 1,3-dehydroxybenzene, 1,4-dehydroxybenzene, 1,2,3-dehydroxybenzene, 1,3,5,3-dehydroxybenzene, 1,2,4-dehydroxybenzene. And this is the list for molecule group 2. There is any 2-methylphenol, 3-methylphenol, 4-methylphenol. Next is our calculation is based on geometry optimization. Optimization of phenol derivative for neutral and ionic molecules. All calculations are done in the gas phase using Gaussian 16 software. We use basis 631 plus GDP and 2 methods, which is B3LYP and H-REFO. The geometry optimization is performed to obtain the ground state geometry and total electronic energy. This is how we calculate the ionization potential. We can calculate ionization potential with 2 ways. First is with different energy between neutral and ionic energy as represented in equal 1. And then we can calculate ionization potential with negative energy of highest occupied molecular orbital or HOMO obtained from H-REFO calculation equal to This is the way to represent our Kaufman theorem approach. Next is evaluate the accuracy of Kaufman theorems. We compare the ionization potential calculation from the three methods with experimental data. Next, we move with our result. Validation of computational method based on ionization potential average error for all methods. In figure 4, we can see average error diagram for each method. Among the three methods, the Kaufman's theorem approach showed the smallest average error, 1.73%. It kept the highest accuracy in estimate the ionization potential. So we can say that Kaufman's theorem offered the most accurate method for calculate ionization potential among the test approach. This is the computational cost to calculate ionization potential for all methods. We can see the figure 4, average computational cost to calculate average potential using different methods. From the figure 4, F5, among the three methods, the Kaufman's theorem approach is high and average computational cost 18 times lower than the TLYP and 3 times lower than Hartree-Fock. Although Kaufman's theorem involves an approximation, its computational simplicity makes it an efficient alternative for estimating ionization potential. This is our conclusion. The Kaufman's theorem estimate to show a lower computational cost compared to BTLYP with a higher level of accuracy. The results show that the Kaufman's theorem is a computational efficient and reliable alternative for estimate the ionization potential of panel derivative. And the Kaufman's theorem also offers a simple approach and it's relatively cost-effective in terms of computational. I would like to express my sincere gratitude to Research Center for Quantum Engineering Design, which enabled the computational part of this research. All simulations were carried out using the reference cluster facility. That's all for me. Thank you.
Okay, thank you. Thank you, Ayu, Tiara, etc. Now, you open the mission, please. Who's want to discuss? Okay, in bahasa, please, Prof.
Itu untuk apa ya? Bagaimana menentukannya, untuk apa, dan relation antara computational cost dengan ionization potential.
Terima kasih untuk pertanyaannya. Jadi computational, saya boleh menjawab dengan bahasa Inggris?
Iya, bahasa.
Computational cost ini kami gunakan untuk mengestimasikan waktu lamanya yang dibutuhkan untuk menghitung potensial ionisasi. Nah, jadi karena kami menggunakan simulasi, kami menghitung elapsed time, di mana untuk B3LYP untuk mendapatkan ionisasi potensial itu membutuhkan dua input file, yaitu input file untuk molekul netral dan molekul ionik. Sedangkan untuk Hartree-Fock juga sama, membutuhkan dua input file untuk molekul netral dan molekul ionik. Tapi untuk pendekatan Kaufman's theorem itu hanya membutuhkan satu input saja, yaitu untuk molekul netral, karena kami menghitungnya menggunakan pendekatan yang berbasis dari energi negatif, energi homo. Nah, untuk kenapa kami butuh untuk menghitung cost komputasinya, untuk menghitung dua input file ini membutuhkan waktu yang berbeda, tergantung dengan metode yang kami gunakan. Semakin banyak input file yang kami gunakan, maka semakin lama waktu kalkulasinya. Nah, yang pertama ingin kami lihat adalah akurasi dari si Kaufman theorem di sini. Nah, jika dilihat dari sini, Kaufman theorem itu memiliki akurasi paling tinggi dengan error paling kecil, yaitu 1,73. Selain itu, kami juga mempertimbangkan untuk cost komputasinya. B3LYP ini membutuhkan waktu 18 kali lebih lama dibandingkan Kaufman theorem dan Hartree-Fock. Apakah menjawab
hasil ionisasi potensial?
Jadi kami menghitung rata-rata errornya untuk semua molekul.
Dari sekian teori pengebukan itu lebih akurat dengan ionisasi potensialnya di mana ya sebenarnya?
Kalau dengan
ionisasi potensial untuk apa saja?
Untuk memperkirakan untuk molekulnya ini.
Thank you, Prof. Any more question, please? One more. Roger. Okay. Ya. Gunakan bahasa Indonesia saja kalau kamu. Ayo. No problem. Take it easy. It's okay. Oke, dari saya. Ini tiga ini adalah presentasi tentang komputasi. Nah, kalau kita tidak paham, membingungkan atau membingungkan, ya seharusnya kalau hal-hal yang sifatnya komputasional itu harus ada flowchart. Ini tidak ditampilkan. Kemudian tadi you menyebutkan mention about quotient equation, ya quotient formulation, quotient mark tanda tanya. Itu untuk digunakan apa? Apakah dia sebagai algoritma numerik dalam software yang digunakan itu, atau bagaimana?
Dia bukan algoritma numerik yang ada di dalam software.
Karena you tidak menampilkan. Padahal ini bahasa program yang sebenarnya you mau komparasikan, ya komparasi tadi bahasa program, ya kan? Harusnya itu didisplaykan. Ya, itu masukan. Jadi bukan result dalam histogram diagram data. Paham? Itu tidak berbicara secara saintifik, secara ilmiah tidak tergambarkan. Anak SMA juga bisa membuat histogram, kan gitu. Bahkan anak SMP kalau menggunakan data-data itu bisa. Nah, sebagai seorang peneliti seharusnya itu tergambar di dalam sebuah metode, ya. Metodologinya seperti apa? Itu yang tidak saya lihat. Karena saya sering menggunakan Gaussian equation, Gaussian formulation. For what? For analysis histogram for the distribution crystalline particle, crystalline analysis. Jadi saya menampilkan equation persamaannya. Jadi nanti di situ ada distribusi-distribusi yang lain, Lorentz distribution, Gaussian distribution, mana yang lebih exactly, yang lebih pas secara ilmiah. Ya, jadi kalau ini kan nggak tergambar ini. Ya, kalau orang komputasional itu harus memperlihatkan algoritma. Ya, algoritmanya itu apa? Flowchartnya bagaimana? Ini kan membandingkan, studi banding ya, antara dua metode komputasional atau apa?
Antara BGDLYP, Hakrepon, dan pendekatan kos.
Sementara yang kamu displaykan ini hanya hasil dari apa?
Dan DFT dengan
mana hasilnya? Ada dari itu. Apalagi kamu bermain-main dengan rumus kimia, gitu ya, yang secara bonding ikatan itu banyak aproksimasinya. Tadi di presentasi pertama itu, ya, yang kedua dilanjutkan, itu bagaimana kita melihat karakteristik ikatan itu, tidak hanya dengan pendekatan simulasi, ya, itu. Jadi tidak bisa. Nah ini result and discuss. Validation of computational method based on ionization potential operates in zero for algorithms. Ya, ini tiba-tiba dia muncul histogram. Ujuk-ujuk muncul histogram lebih tinggi. Bagaimana kalau saya manipulatif datanya? Ayo. Boleh kan? Ini kalau didisplaykan dalam bentuk artikel paper ini question mark tanda tanya. Karena tidak ada alur ceritanya kok tiba-tiba ada histogram. Karena kalau saya manipulatif datanya saya bilang ya lebih tinggi. Kan boleh aja. Boleh nggak kayak gitu? Tidak boleh. Tapi supaya tidak boleh, kita itu kan eksak, pasti. Jadi karena kita pasti, selalu ada argumentasi saintifiknya. Itu frame kita sebagai orang eksak. Kalau keluar dari itu ya nggak apa-apa. Berarti kita bukan orang saintifik. Jadi asumsi, opinion, persepsi itu boleh, nggak perlu. Tapi konklusi tanpa kuantitatif yang kamu lakukan tadi, algoritma itu kan kuantitatif. Baru muncullah kualitatifnya, better, ya, full, etc. Dan lain sebagainya. Nah itu dari saya masukan, ya, kritik. Harusnya Pak Tetian ada di sini untuk bantu menjawab. Tapi sudah dikomunikasikan dengan Pak Tetian? Sudah. Okay, thank you. Any more question, please? One more. Belum? Okay, enough. Thank you.
Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Ya, saya banyak ngomong karena waktunya terkadang ada yang singkat, ada yang panjang. Nanti kita selesainya cepat. Okay, next for analysis and photon output those of linear accelerator. And infinite, ya, bla bla bla. Is imatus solid. Mana? Oh ini. Saya pikir peserta partisipan presenter.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. First, praise be to Allah Subhanahu wa Taala that's allowed me to be here today. Before starting our presentation, let me introduce myself. My name is Naimah Sonika, and with my partner Zulina Ayin Nova Masuri. And this opportunity will present about our research article analysis of photon output dose of linear accelerator, Linux Electa Infinity and Electa Precise based on the IAEA TRS 398. This research aimed to evaluate and compare two Linux model used in radiotherapy, focusing on how accurately they deliver phantom dose according to international standard. And then
So radiotherapy is a medical procedure used to treat cancer and by destroying malignant cells, inhibiting their growth and preventing recurrence. External beam radiotherapy commonly use a linear accelerator or LINAC, which deliver high energy photon beams precisely to the tumor target while minimizing exposure to surrounding healthy tissue. However, variations in linear second beam output pose a critical risk to treatment accuracy and patient safety. Absolute dose verification using EIA at TRS 3998 is essential to ensure the prescribed dose is delivered correctly. Despite this, comparative data between Elekta Infinity and precise Linex are still limited, creating an urgent need for studies that evaluate model specific photon output and support safe, effective cancer treatment. Before moving to the experimental, it's important to understand what has been discussed in previous studies and how this research fills the exciting gap. So, several authors, such as Azizal Fauzi and Macfiros et al. Next. And the problem formulation. What are the results of the absolute dose measurement for the photon modality on the Elekta Infinity and Elekta Precise Linex using the TRS 398 protocol? And the second, how do the absolute dose measurement results for the photon modality on the Elekta Infinity and the Elekta Precise Linex comply with the ICPIAM 40 guidelines? And the research goals for number one, to determine the results of absolute dose measurements for photon modalities on Elekta Infinity and Elekta Precise Linex using the TRS 398 code of practice. And the second, to determine the conformity of absolute dose in photon modalities of Elekta Infinity and Elekta Precise Linex using the ICPIAM 40 protocol.
And then before moving to the methodology, let's review about the trial review. First, about the linear accelerator. Linex is a device that uses high-frequency electromagnetic wave to accelerate charged particle in the form of high-energy electron through linear tube. Now, difference between Elekta Linex model in Elekta Infinity and Elekta Precise is this difference might influence the photon output dose, which is the focus of this study. And then the absolute dose. Absolute dose represent the actual radiation energy absorbed per unit mass of tissues measured in gray. And its accuracy is essential to ensure that the tumor achieves the prescribed dose safely. And then IIEA TRS 398 is international standard for absorbed dose to water determination in external beam radiotherapy. Ensure accurate and reproducible dose delivery is so important and then critical for safe and effective radiotherapy.
And methodology. The study was conducted at the Radiotherapy Department of RSPAL Dr. Ramelan Surabaya in Indonesia during January until February 2025. All measurements and verification were performed in accordance with the IAEA TRS 398 code of practice for dosimetry. And the second, equipment and materials. We use Linex Elekta Infinity and Linex Elekta Precise and thermal ionization chamber, and then PTW beam scan water phantom and PTW transfer software, PTW Unides thermoelectrometer and thermometer, barometer, and environmental monitoring sensors.
These tools were used to measure, correct, analyze, and the absolute potent output dose. This is our research process, starting from preparation stage until data analyze. After data collection and analyze, on this slide, I will explain the presentative dose or PDD, analyze research for both Electa Infinity and Electa Precise. At 6 MV photon energy, but curves increase until they reach the Tmax point, the slowly decrease. This is typical for photon beams. For the correction, absolute dose output data of photon modality in Electa Infinity Linux, correction based on the temperature pressure correction KTP, and then keypole or polarity correction. And after applying this correction, the true beam output or M0 was obtained. This is make sure that environmental and instrument effect were minimized. And this step confirmed that the setup was correct before calculating the dose. So to determine the value of A0, A1, and A2, the reference data can be obtained from the table below. And then determination of the corrected dosimetry reading during measurement or MQ. Based on the MQ, we measure determination of dose Z-trap and determination of absorbed dose at the PDD, which is Z-trap 74%. So the dose deviation was only on 0.796%. And then with the same methodology in Linux Precise, the depth of maximum dose was on 0.998 centigrade, and then dose deviation is on 0.1440%. So based on the data analyzed conducted to measure the absolute photon output dose of the Electa Infinity and Electa Precise Linux, the result obtained are as follows. The absolute photon output dose of the Electa Infinity Linux at the depth of maximum dose was found to be 1.008 centigrade with a deviation of 0.7% after adjustment. That's value become 0.998 centigrade with a deviation 0.014%. So to verify the conformity of the measured absolute photon dose from the Linux modality, it is necessary to compare the obtained absolute dose calculation value with the quality assurance standard established by the ICPIAM TG40 protocol. Based on the table, the deviation value obtained for both the Electa Infinity and Electa Precise Linux fall within the ICPIAM TG40 tolerance limit of either 2%, indicating compliance with the acceptable quality assurance criteria. So that's all for our presentation. In conclusion, accurate dosimetry is very important to ensure patient safety and successful radiotherapy treatment. Thank you very much for your attention. Then, Wassalamualaikum warahmatullahi wabarakatuh.
Please, patient, please. Okay.
Baik, perkenalkan nama saya Albert, silakan. Saya ingin bertanya mengenai probability. Boleh ditunjukkan sebentar?
Ya.
Probability ini saya ingin bertanya, saya belum pernah. Nah, apa sih arti dari puncak dari probability ini yang paling maksimum, paling minimum? Apa ada hubungannya sama kemampuan dari si radioaktif tadi membunuh sel kanker? Apakah ada hubungannya? Nah, untuk yang pertanyaan pertama itu, yang kedua, apakah untuk PDD ini sama kayak kita lagi mengkalibrasi suatu alat supaya aman untuk digunakan sebelum digunakan ke pasien?
Baik, terima kasih banyak untuk pertanyaannya. Jadi berdasarkan kurva PDD yang ada di sini, di mana di sumbu X di sini menunjukkan kedalaman ya dalam satuan milimeter dan juga di sumbu Y-nya itu merupakan presenter depth dose gitu ya. Jadi ini merupakan apa namanya bentuk hubungan antara kedalaman penetrasi dari radioaktif yang kita tembakkan terhadap presentasi depth dose atau tingkat dosis yang mengenai suatu jaringan. Di mana di dalam grafik PDD ini kita tahu ada beberapa puncak yang terlihat di situ, kemudian dia melandai seiring dengan berjalannya waktu pada kedalaman tertentu. Jadi pada prinsipnya dalam teori BIM atau apa namanya proses radioterapi gitu ya, ketika suatu sinar foton yang misalkan dihasilkan oleh linek itu ditembakkan dari kolimatornya, kemudian mengenai misalnya material yang ada di couch atau meja pasien itu gitu ya, dalam case praktik medis artinya adalah pasien, maka sebenarnya ketika ketika sinar foton itu ditembakkan, dia akan mencapai dosis maksimalnya pada kedalaman tertentunya saja. Dan kedalaman tertentunya itu digambarkan oleh kurva yang dimana presenter depth dose-nya itu mencapai puncaknya. Kemudian seiring seiring dengan bertambahnya kedalaman gitu ya, dia akan mencapai titik landai, titik minimalnya kembali. Seperti itu mungkin. Apakah menjawab untuk pertanyaan yang pertama? Oke. Kemudian untuk yang pertanyaan berikutnya, apakah ini sama dengan kalibrasi seperti yang pada alat-alat pada umumnya gitu ya? Sebenarnya untuk pengukuran presenter depth dose ini merupakan salah satu bagian dari kalibrasi yang harus dilakukan gitu ya pada setup alat linek yang akan digunakan agar kita tahu apakah pada kedalaman tadi kita sempat mention juga ada istilah DWZ max. Jadi ada acuan referensi di mana pada kedalaman maksimal itu seharusnya dosis yang dikeluarkan itu adalah sebesar 1 centigrade. Nah, dalam bisnis yang kita lakukan ini, kita ingin make sure apakah betul bahwa ketika QA dilakukan pada kedalaman Z maksimalnya itu dosis yang dihasilkan itu adalah sebesar 1 centigrade atau tidak. Apakah sudah menjawab?
Masih ada waktunya nggak? 1 minute more. Oke, please.
Tadi kan sama kayak kalibrasi. Nah, kan sel kanker itu kan betul-betul di kedalaman yang sama. Apakah mungkin dia di kedalamannya beda-beda, kalau misalnya dia kedalaman beda, atau kalibrasi dulu. Nah, kalau dia beda, apakah nanti grafik kalibrasinya apakah berbeda juga atau gitu?
Oke, baik. Terima kasih atas pertanyaannya. Jadi memang tentu saja sel kanker itu punya kedalaman yang berbeda-beda dalam tubuh manusia gitu. Itu juga yang menyebabkan dalam treatment pemberian untuk penyembuhan kanker menggunakan linek itu kita bisa menggunakan 2 modalitas, yaitu foton atau elektron. Dalam hal ini yang kita uji itu adalah modalitas foton. Jadi untuk kanker-kanker dengan kedalaman yang tidak terlalu dalam dekat dengan permukaan, itu modalitas yang digunakan adalah elektron karena daya penetrasinya lebih rendah dibandingkan dengan foton. Ini yang pertama. Kemudian tentu saja dalam setiap kasus kanker akan ada variasi kedalaman, letak dan lain sebagainya. Nah, seyogianya dosis maksimal yang dicapai ketika tertentu itu hanya istilahnya maksimalnya akan selalu di titik itu. Nah, oleh sebab itu, ketika sebelum melakukan penyinaran kepada pasien, diperlukan yang namanya treatment planning system. Di mana di dalam treatment planning system itu, kita fisikawan medis itu akan melakukan analisis gitu ya, dari segi sudut-sudut tembakan yang digunakan itu harus berapa derajat, apakah dari arah anterior atau dari arah posterior, ataukah dari arah sudut lateral dan lain sebagainya, dengan maksud dan tujuan agar dosis maksimal itu diterima oleh tepat pada bagian kankernya, bukan pada bagian organ atris atau organ jaringan sehat yang ada di sekitarnya. Seperti itu.
Oke, thank you. Ya, terima kasih. Ada dia sobat. Ini bagus ya. Nah, dengan siapa satunya? Surya. Oke. Thank you very much.
Oke, terima kasih. Yang dari kami.
To enhance mechanical performance. This research aims to investigate how its internal geometry of a scaffold, especially straight and spiral raster design, affect its structural, mechanical, and surface properties when fabricated using FDM 3D printing with PLA material. Let's see. Let me begin with the introduction. Meniscus is a critical fibry cartilaginous structure that enables load distribution, joint stability, and shock absorption. Meniscal tears are commonly injuries that frequently lead to osteoarthritis. Current treatments such as meniscectomy or allograft face limitations such as including donor scarcity, immune rejection, and poor integration. Technological solution like FDM-based 3D printing enables creation of customized scaffold that replicate native meniscus complexity, addressing biological and structural limitation of conventional graft. The mechanical consideration is implant tissue modulus mismatch in traditional approaches cause uneven stress distribution. 3D printing offers architectural control to overcome these challenges. Although many scaffolds have been developed, most of them still fail to accurately replicate the native meniscus. FDM 3D printing allows design customization, but its nozzle resolution limits for precision, typically ranging from 250 to 525 micrometers. Scaffold with straight lattice scaffold are brittle, high stiffness, and less flexible. Meanwhile, the spirals or curved scaffold have better flexibility and porosity, but weaker on load bearing. The effect of raster-inspired geometry, straight versus spiral, on mechanical and morphological properties of polylactic acid or PLA scaffold is not yet fully understood. This gap forms the basis of our research. The material and methods we use is we are using polylactic acid filament with diameter around 1.75 millimeters with printer using AnyCubic Cobra 2, the fused deposition modeling printer, 3D printer, and using software SolidWorks 2025. The with printing parameters are nozzle using 0.2 millimeters, temperature 200, ranging from 200 until 210 degrees Celsius, with the temperature band 60 degrees Celsius, the speed 50 millimeters per second, and layer height around 0.2 millimeters. Then we characterization the scaffold like the as we can see from the slide. The scaffold design, we can see from figure 1, the straight raster have linear orthogonal struts used to promote high stiffness and predictable load response. The straight raster also channels stress along straight path with tend to fail in a brittle manner. Meanwhile, the spiral raster or curved helical struts provide the greater flexibility and even stress distribution, inspired by triply periodic minimal surface or TPMS geometries that is researched before by Miracle of 2021. The spiral raster enhance the adaptability and resilience under complex loading. Both design use equal material volume and infill density, ensuring the geometry alone governs mechanical performance. The contrast illustrates how architectural curvature can shift behavior from stiff brittle to flexible ductile response. Next, we characterize our scaffold using morphological analysis using scanning electron microscope, as we can see from figure 2. We can see from the straight raster have aligned smooth struts with uniform pore openings, with pore around 200 until 250 micrometers. Also display layer precision and consistent structural alignment. Meanwhile, the spiral rasters have curved interconnecting pores ranging from 300 micrometers, show continuous interlayer connectivity, promote fluid and cell passage. Both designs show high printing precision and minimal layer defects. Morphological connectivity is crucial for nutrient and chondrocyte migration. Pore size fell within the optimal biological window ranging from 150 until 500 micrometers for meniscal tissue engineering, according to Song et al. At 2018. We move on to the porosity result. The spiral raster curve infill path create open channels, resulting in higher porosity that falls within the ideal range for cartilage scaffold. This improved porosity enhanced nutrient transport and tissue integration, matching the findings of Torres Sanchez at 2017, which showed that optimal pore ratio improved mass transfer and chondrogenic potential. In contrast, the straight raster denser packing restricts this benefit but improve its mechanical strength that we can see from the table. Next, the tensile test result show that the geometry directly influence the tensile response, where the straight raster linear struts lead to high stiffness and concentrated stress. Consistent with polylactic acid scaffold study by Sarah et al. 2013. In contrast, the spiral raster provides flexibility similar to native meniscus around 100 until 300 megapascal and demonstrate distributed deformation matching the observation of flexible meniscal graft behavior by Ambra et al. 2024. Next, the compressive trend show that the straight raster support a higher load but fractures early, exhibiting brittle fracture behavior typical of rigid lattice. In contrast, the spiral raster sustained greater deformation before failure, as its helical design enabled superior strain accommodation, despite being matched with Lee et al. 2022. Then, this ability to endure significant deformation is essential for withstanding the cyclic compression typical of knee biomechanics. So this slide present the graph of tensile and compressive stress that I explained before. We can see from the figure A is straight raster tensile test, B is spiral raster tensile test, C is compressive strength straight raster, and D is compressive strength for spiral raster. Next, we move to wettability analysis. The wettability analysis shows that spiral raster have hydrophobic phase with the degree around 95.3 degree, shows that slow wetting but swift for long-term nutrient delivery. Meanwhile, the straight raster show that the hydrophilic phase with degree around 90.9 degree show that fast wetting from 90.9 to 80.5 after 60 seconds. So it's ideal for initial cell attachment. The surface in future work, the surface modifications such as polydopamine, hydroxyapatite, or graphene oxide can enhance hydrophilicity without sacrificing mechanical strength, according to Wang et al. 2020. The comparative and structural mechanical discussion is the spiral raster demonstrate higher porosity around 57.91%, flexibility and an elastic model and 32 megapascal, close to the native tissue meniscus that is around 100 until 300 megapascal. Straight raster achieve higher stiffness around 1050 megapascal and strength, but reduced strain tolerance, resulting in brittle failure under load. The increase of porosity of the spiral design, consistent with the Mirkalov et al. 2021 and Lee et al. 2022, contributed to enhanced stress distribution and delay crop propagation. The morphological analysis from SEM showed that interconnected curve pores in the spiral pattern allow better energy absorption and mimic meniscal anisotropy, as supported by Grimare et al. 2018 and Manjunath et al. 2021. Overall, the spiral geometries balance structural stability and deformability, offering superior biomimetic potential compared to the straight configuration. The biomedical implication, imitation, and future work are the biomedical implication. The spiral raster mimic the anisotropic behavior, mimic anisotropic mechanical function of the native meniscus, balancing compressive resistance with elasticity. Its porosity, around 57.91%, supports cell infiltration and nutrient transport, while it is moderate wettability with 89.6 degree, its initial addition. The design is suitable for personalized implant through parametric FDM modeling and geometry tuning. The limitation in this work are the pure polylactic acid degrades slower than native meniscal tissue regeneration. Only static meniscal testing, such as tensile and compression, was conducted in this research. In vivo biological assessment are still required. So, for the future work, I assume that the applied bioactive surface coating, such as PDA, HA, GU, to enhance bioactivity and hydrophilicity. Perform cyclic and fatigue testing to assess long-term mechanical stability. Next, the conduct biocompatibility studies using chondrocyte or fibrocartilage cell. Next, they explore multi-material and graded scaffold for region-specific mechanical behavior. From the explanation, we can conclude that the design impact scaffold architecture critically determine its structural, mechanical, and also biological performance. The next is the spiral advantage, such as structure with high porosity around 58% with interconnected spiral design advantage is structure with high porosity around 58% with interconnected helical pores and mechanics is ideal for stiffness around 332 megapascal, matching the native meniscus tissue. The function is also excellent stress distribution and mechanical adaptability. Meanwhile, the straight raster characteristic has a lower porosity than the spiral raster, and due to the straight raster, it has the high stiffness but limited flexibility. The biological is faster rating suitability for initial cell attachment. The optimal solution is raster spiral architecture, provide the best balance for meniscus regeneration. For the future work, implement bioactive surface coating, evaluate the performance under cyclic loading, advance toward clinical application. These are references that I use. That concludes my presentation. I sincerely apologize for any mistake or inaccuracies. Thank you for your kind attention. And now return to the moderator.
Thank you, Anidia, for your presentation. Now we offer this Bishop. Claudius, yourself.
My question is, earlier you mentioned that lower stiffness sometimes more preferably rather than, for some tissue from some tissue regeneration. So when does the lower stiffness is needed, and when do we need the stiffness?
Please answer.
Thank you for the question. The lower stiffness in this experiment we use as the native meniscus is around 100 until 300 megapascal. So according to the native meniscus, in this research, the lower mechanical strength is used to demonstrate the distribution deformation with for the scaffold, because meniscus itself boleh dimix nggak? Boleh dimix nggak? Boleh dimix. Karena dari meniscus sendiri itu dia kalau misalnya terlalu kaku atau stiff, nantinya nggak akan dia kan kalau misalnya meniscus itu di lutut, dia kalau misalnya terlalu menekan itu bakal cepat patah. Sedangkan diperlukan juga itu flexibility karena kegunaannya untuk menahan tekanan dari lutut itu sendiri. Makanya pada penelitian ini diperlukanlah mechanical strength-nya itu ataupun mechanical strength-nya itu yang diikuti adalah sekitar dari 100 hingga 300 megapascal mengikuti dari native meniscus itu sendiri.
Okay, your response? It's okay? Enough? Okay, thank you. One more. Mommy, can you display the figure tensile strength? Can you tell about this figure? What the conclusion do you have?
The conclusion I have, jadi pertamanya itu adalah untuk pas dari straight raster yang tensile itu kan dia ditarik. Nah, ketika desain scaffold itu ditarik, nah dia akan mencapai pada titik patahnya. Nah, titik patahnya itu pada saat yang paling tinggi itu dan langsung pada untuk straight raster dia memang lebih terlihat pada titik patahnya, yaitu kita bisa lihat itu sekitar di 0,12. Kalau di spiral raster itu di sekitar 0,06 sekian. Nah, awalnya itu kalau misalnya titik patah berarti awalnya dia bisa kembali bentuknya untuk kembali ke seperti semula ataupun elastisitas.
The conclusion, this is a material determinant for ductile or brittle.
Brittle untuk yang di straight rasta.
Why?
Karena pada saat dari grafiknya itu dapat dilihat dia pada stringnya itu lumayan tinggi, yaitu mencapai hingga 0,1. Dan bisa dilihat juga dari penjelasan yang
Saya pakai bahasa aja, jadi tarik kesimpulannya keliru. Jadi yang namanya material ductile itu harus melewati fase elastis, fracture. Kalau dia tidak melewati plastis, maka dia brittle. Any plastis region, berarti dia brittle. Okay. Thank you.
Good afternoon, everyone. First of all, thank you for the opportunity to present our study about the study of degradation and mechanical properties of braided catgut surgical suture. This research was conducted together by Putri Adilian Nurfaisa, Professor Dr. Aminatun, and Mrs. Tia Hikmawati. In a few next minutes, I will guide you through why this research matters and what method we use, and then how our results actually reveals that braiding can actually improve the surgical suture. As the advance of the market growth for biomaterial in 14% just annually, this highlights the need for safe, efficient, and then regenerate materials in clinical applications. But the problem is, for a biomaterial to be able to degrade, it needs to maintain the balance between mechanical rate and then degradation with the healing time of the tissue itself. For the conventional materials, it struggles with to maintain the balance between the mechanical properties and degradation with the tissue healing itself. So one of the biomaterials that we want to bring in this study is the surgical sutures, which is catgut sutures. Catgut sutures itself is a surgical sutures that is made from collagen natural fibers, which if we talk about the biocompatibility, it has been ensured because it's been produced and marketed outside, and then our body can enzymatically degrade it, so there's no residue in our body from these catgut sutures. For the price itself, it's also less costly rather than the synthetic absorbable sutures, because the synthetic one, like polyglycolic acid or polylactic glycolic acid, is expensive, thus is not compatible when you compare it with catgut sutures. The problem with catgut sutures, it's rapid and unpredictable degradation, especially in body fluids or in our body environment. So what if this catgut sutures, the one that is affordable and accessible, we can actually improve it so we can use the wider application of it, and then so it can be used in a wider application such as ligament or maybe tendon repair, which the healing time is longer than the usual skin or like a wound in our skin or maybe in dental application. Thus, to overcome this limitation, we use the braided suture approach, which is proven that it can enhance stress distribution.
from this stress distribution, it can actually share the load into different filaments because it contains from many filaments. Thus, it reduces the localized strain, and so the material will not suddenly or abruptly degrades. And the next thing is, from the braided structure itself, it's proven that it can increase surface area by improving the frictional stability and improving with the contact of the body itself. So the uniform degradation will not suddenly rupture or breaking inside of our body. By this overcome limitations, we're looking up from the previous studies, which we know that pH or body environment has effect significantly in degradation of the materials, and then the braid structure in sutures can actually improvise the mechanical performance, and then lastly, the chemical and mechanical properties in some biomaterials needs to be compatible with what application we want to use. Thus, we have the objectives of our results to analyze, evaluate, and assessing the relationship between braid number, degradation behavior, and mechanical integrity of catgut USP 3 sutures. 3 per O is the size of the sutures. So here is the materials and methods. First of all, the braiding itself. We need the catgut sutures itself, and then we make the variables of the braided to 1, 6, and 12. 1 contains of 1 filaments of the catgut itself, so there is no braiding in it. And then the 6 and 12 braids consist of 6 filaments of sutures and 12 filaments of sutures. After the braiding process has completed, we immerse them into the PBS solution, and then we incubate it in 37 degrees Celsius to simulate the body environment. For the test, for the morphology test, before the immersion and the incubation, we have to observe it by digital microscope and then measure the diameter size. Then after that, we can immerse it into the PBS. So we know that before we put it into the body, and then after we put it into the body simulation. Then after that, we incubate it for 4 weeks, and once a week, we have to dry it, and then we analyze the morphology, structure, and then the diameter size. The same thing happens in the degradation and mechanical, where before the immersion and the incubation, we have to measure the weight, and then we have to do the mechanical test. Then we immerse them in PBS, and then for once a week, for 4 weeks, we have to dry them and measure the weight loss and also test the mechanical strength. So here is the results of the morphology test results, which we know that the week 0, the one in the left, is before the immersion to the PBS. It shows like a pitch black or really dark brown color. And then over time, in week 4, we see that the color, it becomes transparent or like lighter brown. This indicates that there is collagen breakdown and loss of compactness of its filament itself. And the discoloration indicating that the collagen in each filament has a loss of compactness, and then the collagen is degrading. Thus, it makes the one that is compact and dark collagen filaments looks lighter and transparent. We also see the loosening of the braid in the week 4 in 6 braid and the 12 braid in the right one. We see that there is a loosening of the braid, where in week 0, we don't see any gap between the braids. But later, after immersion of 4 weeks, we see the gaps between one of the other filaments. This suggests because the degradation of the collagen itself, it reduced intermolecular bonding and fiber swelling into the filament itself. So the fiber, each of the filament in the braided one actually swelling, and it caused loosening of the braid. But the important thing that we know, the loosening of the braid doesn't mean that the size means it's getting bigger, because after the diameter size or the quantitative measurement was being sized, we see that every type of braid has a decrease or like a reduction in diameter size. For one braid, it has 20% of reduction. For 6 braid, it has approximately 6% of reduction. And for 12 braid, it gives approximately 2% of reduction. This shows that even though the loosening of the morphology that we saw, each of the filaments actually degrade and getting smaller. So even though it's loosening, it's still getting smaller as a whole braided surgical sutures.
Then the reduction in diameters, this corresponds with fiber erosion in each filament, and the mass loss with slower shrinkage in denser braids. As we see, the 12 braid just reduced into 2% approximately, and this is due to their compact structure. So because each of filament like hugging or intertwined together with tightly, it limits the fluid penetration. The fluid penetration itself comes from the PBS, the body simulations that we have. Here is the degradation test results, which actually supports what we see before in reduction of the diameter size. We see that for the one braid, the blue one is the most above line. It has in just 1 week, it reduced into 8%, and then for 4 weeks, it has already lost its mass for 30%. Meanwhile, for the 12 braid, it's not even lost 15% of its mass loss after 14 weeks of after 4 weeks of immersion in PBS. This actually supports some of proof the theory of higher structural density, which is in this case is increasing number of braid decreases the permeability of the body fluids itself, thereby reducing rate of mass loss. So fewer braids results in looser structures, which allowing easier fluid or PBS penetration into the collagen itself, and then it makes degradation faster, whereas more braids create a denser structure that limits fluid penetration and slows degradation. From the mechanical test that we have over here, this is the ultimate tensile strength, which means that this is the most stress or force that it can get before it rupture or it has a biomaterial failure. So we can see that there is sudden drop from 211 megapascal to 70 megapascal just in the forward. This means that it cannot withstand the force within prolonged time, so it's not compatible for healing time period that needs a longer time. And as we see, the flatter curve indicates that there is lots of stiffness, which making it mechanically weak because it cannot withstand any force and just degrades abruptly. And this broken collagen network may be caused because stretch easily but it actually tears suddenly. So there is no elasticity, this is brittle, and it tears suddenly after some sort of force that was given to the suture. Next, for the 6th braid, as we can see over here, it has a different, really different curve as before. There is an increase in week 1, which is from 76 to 90 megapascal, and this might happen because the fiber tightening after short-term hydration, because it was put into the PBS solutions before gradually decreasing. And as we see before, it has a flatter curve, and this one has a steep curve, which makes this material actually stiffer and then more resistant to stretching. Thus, it can actually withstand force within some longer time period and might preserve integrity better than the one braid. And this increase of ultimate tensile strength, indicating that intensification on compaction of fibers as water was absorbed and was lost. So 6 braid actually gives some potential to be used for prolonged time rather than one braid because it can withstand force for some period longer time. And lastly, in 12 braid catgut sutures, as we can see over here, there is if we compare it with the 6th braid, it actually not that the curve is not really as steep as the curve in the 12. It's because that this strip actually protect the inner. So the 12 braid actually has the stiffness from the first. The 12 braid actually a stiff biomaterial already. However, the 6th braid actually they stiff over time when it is put into the body simulation. So making it that 12 braid catgut sutures has a slower degradation and preserving properties. But then because of the longer degradation rate, it may cause residual material, which for something as biodegradable and bioresorbable material for our body, it's not good when it leaves residual because it may cause inflammations and hindering the tissue regeneration. So what we conclude from this research is the first one, the mechanical properties of catgut are strongly influenced by braid number and immersion time. Then we know that the braid structure directly affects the mechanical and degradation properties, which the loosely braid actually gives the faster degradations and loose mechanical integrity, thus is not suitable for something which needs a longer healing time. Then the tightly braided sutures resist degradation but are stiffer, so it can actually put as a longer healing time tissue regeneration. And then we conclude that the 6 braid configuration provides an optimal balance of moderate degradation, with sufficient strength and maintain flexibility, making it suitable for biomechanical application such as patellar tendon reconstruction that may need a longer time to heal. From this work, we know that maybe the degradation rate or maybe the mechanical testing might seem to be similar to some of healing time with like tendon or ligament, but still needs to be testing for the suitability for the, for example, patellar tendon repair. So because this is just like the potential of its being to be used in heavier applications. And then including standardized measurements to compare braided sutures against conventional sutures and other applications. So we know that if we compare this with the, let me take an example like polyglycolic acid, this braided catgut sutures able to replace it and be short-term alternatives for the better or improved sutures in heavier application. I think that's all what I present today. Thank you very much for the opportunity and the attention. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Adelia, Sutra, and the gang. Okay, we now open for the question. Please. Ladies first.
About so application involving heavier or lot verification. What kind of structure material are commonly implied, and how do their mechanical and biological limitations, like tensile, strength, or elasticity, highlight the need to improve or redevelop cut structure for enhanced performance and usability?
Thank you. Please, Dela, your answer.
For the first questions, can I repeat the questions first? The questions is about what types of sutures that usually used in surgery. For surgery itself, actually catgut sutures has been used from a long time before, but the use of these catgut sutures is limited because its ability to withstand force and healing time is so limited. Like it degrades actually for maximum 12 days, when we know that the body itself has to heal for about like approximately 2 until 4 weeks. So for heavier applications, like with some organs that needs like that has denser or should I say heavier, like if we compare our skin to our liver, our liver might be heavier, thicker. Then so it must have a different quality and mechanical strength to withstand its environment. For the next question, I can repeat.
How do their mechanical and biological limitations
For the
catgut structure? The mechanical and biological limitations for catgut.
For the catgut sutures itself, because it is suitable for subcutaneous application. So the most we use for catgut surgical sutures usually used for dental, And then skin, Moscow skin is like a couple layer under our skin. So the limitations, of course, because of as I said before, the degradation rate is fast because it is used for something that heals fast. The healing rate for our skin and then the healing rate for our inside organs like intestines or something like that is different, right? Because its ability, different organs has its own ability to heal. That's why the limitations of catgut surgical sutures is it can be used in broader applications. And for the biological one, I think this is more highlights the mechanical limitations of it.
Okay, your response? No? Okay, satisfying? Yes, thank you. Adam, for your presentation. Give applause. For the last presentation, I invite Sri Kusmiati. Please.
Nggak bawa ini, Mbak. Nggak mau pakai partikel. Ayo boleh. Ini ya, partikel.
Oh, ada lagi?
Iya, bisa.
Saya yang keluar di sini gimana?
Habis ini. Ini.
Warahmatullahi wabarakatuh. Good afternoon, everyone. In here, I want to present synthesis and characterization of anomalous breeze. Isun ke kami. Yes. The silicon titanium dioxide as a material testing for diffuse optical tomography. For introduction, breast cancer is the most common malignancy in women worldwide. Early detection significantly reduce mortality and treatment costs. Limitation of conventional imaging seperti X-ray, MRI, PET, radiation exposure, high cost, limited actions, and then diffuse optical tomography over a non-invasive, low cost, and safe imaging alternative. From the problem statement, DOT system required calibration material of phantom that simulate real tissue properties. Gelatin phantom degrade quickly. Silicon-based phantom are more durable and stable. Need for breast phantom with controlled filtering and absorption to mimic tumor tissues. For research objectives, to synthesize and characterize a silicon titanium dioxide breast phantom with tunable optical properties for DOT calibration and sensitivity testing. For research methods, in this flow chart, this flow chart illustrates the overall research process beginning with the preparation of tools and material, followed by the synthesis of the silicon titanium dioxide breast phantom containing anomalies with varying titanium dioxide and textile dye concentration. The optical observation coefficient was then measured using the Lambert-Peer law to determine the optimal optical composition. The most stable phantom was subsequently tested using the diffuse optical tomography system consisting of 16 light source and 16 detector to collect light intensity data. The recording data were processed through a reconstruction algorithm to generate absorption image
analyze optical stability, and evaluate the optimal composition and system sensitivity for detecting the small anomaly size. This figure is experimental setup for the OT system. We have near laser sensors, and then objectable rotation mechanism, and then silicon detector. We use Torlab PDR, and then multimeter, and then the detector table rotation mechanism, and microcontroller to control the object table and detector table. This is a composition of silicon, titanium dioxide, and textile dye matured for panel fabrication. After curing, a sample was characterized for its optical observation coefficient using the Lambert-Beer relationship. This equation, where V0 is the reference detector voltage, V is transmit voltage, and X is the sample thickness. The obtained observation coefficient were plotted against titanium dioxide and dye concentration to evaluate the correlation between composition and optical response. The DOT system then scanned its phantom using all 256 source detector B, and the resulting voltage data were processed using a linear one-step reconstruction algorithm to produce two-dimension absorption coefficient maps. The reconstruction images were analyzed based on contrast uniformity, boundary definition, and anomaly detectability. The result and discussion is the appearance of the phantom solid titanium dioxide and the concentration of weight, the opacity and color intensity of the sample increasing titanium dioxide concentration caused the phantom to appear aperture, while higher dye concentration depends its color due to greater absorption of visible light. These qualitative observations are consistent with studies reporting that the scattering coefficient increased with titanium dioxide content, while absorption increased with dye concentration. The optical absorption coefficient, this is data from the absorption coefficient of each phantom was measured using a Lambert-Beer relation. The measured results are summarized in table 2. And then the results show that decrease as the concentration of titanium dioxide and textile dye increase. This confirms that the optical properties are tunable and that higher concentration of scatter and absorption lead together overall light attenuation. The relationship between concentration and mu A is depicted in figure 4. Figure 4 is relationship between titanium dioxide concentration and optical absorption coefficient. And then this is a reconstruction image analysis. As shown in the figure, the phantom with 0.06 gram titanium dioxide produce the most distinct anomaly region, exhibiting the best definite optical contrast and edge sharpness. The 0.045 gram sample produce weaker contrast due to insufficient scattering, while the 0.075 gram sample generate excessive scattering that reduce image clarity. The optimum titanium dioxide concentrate in 0.06 gram. This provides the best balance between absorption and scattering for DOT image reconstruction. For reconstruction image analysis, this is the small detectable anomaly 5 millimeter confirm the high sensitivity of the system and the suitability of the phantom as a calibration material for DOT device. The result corresponded with recent studies demonstrating that optimized silicon titanium dioxide phantom provides sufficient scattering contrast for high resolution optical tomography. The conclusion is silicon titanium dioxide based with phantom was successfully synthesized and characterized as a test material for diffuse optical tomography system. The additional of titanium dioxide and textile dye enable controlled manipulation of scattering and absorption properties. Closely replicating the optical behavior of these tissues, experiment results demonstrate that the optical absorption coefficient decreased as the titanium dioxide and dye concentration increased, with the optimal composition achieved at 0.06 gram titanium dioxide. Second, image reconstruction using the DOT system revealed that this optimized phantom produced the highest contrast and most distinct anomaly boundaries. The system was able to detect anomalies and as small as 5 millimeters diameter, confirming the high sensitivity and accuracy of both the phantom and the DOT instrument. In summary, the developed silicon titanium dioxide phantom exhibits stable, reproducible, and tunable optical properties, making it a suitable calibration and validation material for non-invasive optical bridge imaging technologies. This finding contribute to the advancement of affordable and prices optical tomography system for early breast cancer detection. Thank you.
Okay, thank you, Sri Kusmianti, your once presentation. Now we open for the question. Any question, please? One more? No. Just only one, okay? Only one question. Any question, please? Question? Oh, okay. What's what? Okay. Can you explain the figure about the absorbance by disease? Yeah. The disease. Yeah. Thank you. What conclusion we have? Correlation what the axis this concentration versus absorption. Ground versus absorption. This is result from UV test. No. What? The old. Can you tell what the conclusion?
The conclusion is the concentration so that absorption coefficient is decreased titanium dioxide and textile concentrationnya increase.
What the meaning? The slope, trend slope, tend to the negative series of this figure. What the meaning? Gradient or slope of this curve is negatively. Why? Okay, silakan.
Anomali yang berbeda dengan bagian yang sehat, maka dia berdasarkan perbedaan konsentrasi yang akan dilihat dengan DOT tadi itu sebagai apa yang berbeda. Hingga adanya anomali dan itu akan terdeteksi. Soalnya berbeda untuk ini akan ada batas, jangan terlalu konsentrasinya yang membuat tidak akan ada kepastian.
Anomali apa maksudnya?
Ya pura-pura jadi kankernya.
Oh,
Di antara bagian
jadi correlation antara konsentrasi dalam hal ini gram dengan absorbasi itu reciprocal, berbanding terbalik. Ya, anomali.
orang kanker itu kalau kali darah Pak.
Ya, ya, ya.
Bagian yang kena kanker itu kan sehingga ketika dia dikenai akan memberikan fokus dan yang berbeda dibandingkan yang sehat.
Oh, I know. Ini sebenarnya seharusnya absorbasi versus wave number, ya karena itu serapan. Kalau ini korelasinya antara massa dengan absorbasi. Jadi maksud saya begini, Ibu. Jadi setiap uji itu punya karakteristik. UV vis terhadap sinar UV, FTR terhadap terhadap IR, XRD terhadap sinar X, etc. dan lain sebagainya. Itu maksud saya. Nah, begitu ya. Jadi untuk anomali aja. Ya. Oh, kalibrasi atau apa ini? Oh, enggak. Iya. Ini ada empirical result atau theoretical result? Empirical, ya. Jadi konklusinya gini kalau saya. Jadi massa itu makin besar pengurangannya loss mass-nya, maka serapannya makin kecil. Berarti sinar yang ditransmitasikan lebih besar. Kira-kira gitu ya Bu ya? Harus ada analisis lebih lanjut ya. Nah itu yang tidak tergambar, makanya saya bertanya. Ya, oke. Jadi tidak salah saya tanya ya. Oke, bukan menguji Bu ya. Ya, tapi kan selalu ada isu penambahan. Thank you. Ya, oke. Saya rasa cukup ya. Oke, thank you very much. I want to give the closing statement for our parallelization presentation. Thank you for attending today's parallelization. We sincerely appreciate the speaker for the insightful presentation and all participants for their active engagement. We hope that the discussion and share knowledge will be valuable and inspiring. Okay, see you next time for the session. Thank you very much.
Distinguished guests, researchers, and participants, we have now arrived at one of the most anticipated moments for today, the announcement of the best presenter. As we all know, throughout today's session, all presenters have delivered a series of insightful and engaging presentations. Each presenter has shown great effort and enthusiasm.
Starting from breakout room 1, the best presenter goes to Kayla Ramadhani Hakim et al. With the paper ID ICPIAM 01. And from breakout room 2, the best presenter goes to Faiza Rizkia Ramadhani et al. With the paper ID ICPIAM 04. And from breakout room 3, the best presenter goes to Kusuma Widi Wardana et al. With the paper ID ICPIAM 10. And from breakout room 4, the best presenter goes to Mr. Fabian Rushdie et al. With the paper ID ICPIAM 40.
And from breakout room 5, the best presenter goes to Interwenano Hasenti Eka Rosiatin with paper ID ICPIM 51. And from breakout room 6, the best presentation goes to Alivia Fazrati et al. With paper ID ICPIM 44. And from the offline panel session, the best presentation goes to Windarno Monfarid et al. With paper ID ICPIM 34. We would like to express our deepest gratitude to esteemed keynote speakers, all moderators, all presenters in the panel sessions, and every participant for your valuable contribution and active participation.
Our sincere thanks also go to the entire committee and our supporting institutions, Universitas Airlangga, Universitas Jember, and Institute Teknologi Sumatera for making this event possible.
On behalf of the committee, we sincerely apologize for any shortcomings or inconveniences you may have experienced during the conference.
We hope this conference has been a fruitful and inspiring forum for all of you. We look forward to seeing you again at the next ICPIAM.
I am Irfan Atandika and my partner.
Hairunisa Kolan Aziza.
Thank you and good afternoon.
Yes.
Yes,
Ya, boleh.